participant section?
I think don't think.
All right, I guess we can get started. Good morning. Welcome to the third day of BuildSys and the first day of, the third day of Census and the first day of BuildSys. My name is Fred Jang. I am a associate professor at Columbia University, and I'm serving as the general chair for BuildSys this year. It is a tradition that on the last day of Census and the first day of BuildSys that we have a joint keynote on a topic of mutual interest between the two communities. So it is my pleasure to introduce our keynote speaker today, Kaming Whitehouse. Kaming is well respected in both communities. He has published many impactful papers, including 9 papers at Census and 8 papers at BuildSys. Kaming is a principal research scientist at Amazon and a professor at University of Virginia. His work has been featured in media such as the New York Times, the Wall Street Journal, Popular Science, Slashdot, TechCrunch, and Wired magazine. He received an NSF Career Award. He is a CIVL scholar and was named the Commonwealth's Endowed Chair of Computer Science. He has received many Best Paper Awards at various conferences, including Census, BuildSys. He has also served as general chair and the TPC chairs for many conferences, again, including Census, BuildSys, as well as UBCOM, IPSN, and EWSN. He was the inaugural director of LinkLab, a world-class center in cyber-physical systems at the University of Virginia that houses nearly 150 researchers. At Amazon, he is working on new product initiatives with broad social impacts. The technology he has developed are running on millions of embedded devices around the world. And with that, let's welcome Dr. Kaming Whitehouse.
Oh. Hello.
Hello, good morning.
Thank you, Fred, for the introduction. I am totally jazzed after that video. That is amazing. I think, let's see, I'm sharing a screen. Am I live?
Yes, your slide is on the big screen here.
Great.
It still says test. Oh, okay, great.
Great. Yeah, thank you again for the introduction, Fred. It's truly an honor and a pleasure to be here. I've been coming to BuildSys and Census since the very first conferences, and I look forward to being on site again one day once this pandemic is over. These conferences have tremendous impact on academic work and industry, and I say this especially for the new folks and the students in the group. There is huge opportunity for impact in the years to come. So I'm looking forward to that. As Fred mentioned, I work as a professor of computer science at U Virginia since 2006. I joined Amazon in 2018 as a scientist, where I've been developing signal processing and machine learning algorithms for new product initiatives. And both of those have been really amazing journeys of growth and learning in multiple different dimensions. And if you're curious about Amazon or the differences between industry and academic life, feel free to reach out. If you haven't heard, we're hiring. But today I want to convince you that there are some really juicy and important problems in the area of perception, where if sensing is the collection of data, perception is the interpretation of that data. And furthermore, that the problem of perception is critical for the Internet of Things moving forward, where the Internet of Things is the concept that the physical world should be digitally connected through the internet, enabling a sort of network effect where instead of n physical objects and processes, we have n squared relationships between them. So every traffic light and every industrial valve or dial would operate with much greater context of the things around them that they are affecting and being affected by, revolutionizing industries and transforming our lives from smarter homes to smarter management of energy in the environment. It's been about 20 years since the introduction of smart dust, and 10 years since HP declared it to be the decade of sensing. And ARM predicted 1 trillion Internet of Things devices by 2035. 1 trillion is about 1 sensor for every 3 square meters of the planet's surface, and over 100 sensors per person. Indeed, the Internet of Things, or the IoT as people call it, is growing at a tremendous clip. Around 2008, it crossed the threshold where there were more connected devices on the planet than humans, and today includes an estimated 50 billion devices. I surveyed my own home recently and found over 70 connected devices, from my car to my front door to my garden hose. And many of those devices have 4, 5, sometimes dozens of sensing points each. So I literally have hundreds of sensors at my service on a daily basis. And by some measures, like this one, the vision of the IoT is here right now, which raises the question, why my smart home still feels so dumb. Don't get me wrong, I love that my front door automatically unlocks when I come home, and then my garden hose delays the watering when it rains, but that's just automation. It's not smart. And this lack of smartness is not just a problem for home automation. Industry leaders from manufacturing to agriculture cite challenges creating value from their data. Gartner says the IoT is in the middle of a so-called trough of disillusionment. They estimate 2 to 5 years before the Internet of Things reaches the so-called plateau of productivity. But they don't answer the most important question, why? And what can we do about that? And that is a question for this community to answer. So let's go back to the automated home as a driving example for this talk, although I think you'll find that many of the challenges and opportunities generalize across many domains of the IoT. At its simplest, automation includes 3 things: sensing, decision-making, and action. There was precipitation of about 0.1 inches. That's above threshold. Delay by 24 hours. Sensing, decision-making, action. Sometimes the intelligence is higher. Sometimes we have learning, like you seem to like the temperature 4 degrees cooler when you go to bed. Sometimes we have planning, like charge my car to 100% by 7 o'clock in the morning. But these don't qualify as smart, at least not in my book. What we're really missing is perception, the ability to integrate and interpret raw sensor data to create a richer understanding of the world. And this right here is a canonical model of autonomous systems: sensing, perception, planning, action. For autonomous vehicles, for example, the sensing stage produces images, LiDAR, radar. We can't make steering and braking decisions based on JPEGs and point clouds, however. We need to first integrate and interpret that data to understand the location of roads, pedestrians, and other vehicles. And that same concept, moving from sensing to perception, applies for the home as well. We need to convert the raw data that we have on the left, like door lock activity, smart TV activity, motion sensors, into the understanding that we want on the right. Is anybody home? How many people? Who's home? Where are they? What are they doing? And what things are they using? These are the basic concepts required to understand the home. The concepts that you and I use when we interpret the state of the home, like, is the heat on? And is that desirable or a waste of energy? Is the oven on? And is that dangerous or helpful? And yet my smart home has all of the sensor data on the left, but can only answer one of the perception questions on the right today, and only sometimes at that. It's fair to say that the smart home is facing a fairly large perception gap, the inability to turn data into information or understanding. As Henry Thoreau said, it's not what you look at that matters, it's what you see. So let me walk you through an evolution of thinking about perception in the home by my research partners and I, starting back over a decade ago, up through today, and what we see going into the future. What you can perceive depends on the sensors you have. So I'll talk in terms of different sensor suites that I'll call versions 1 through 5. Sensor suite is a set of sensors that can be deterministically installed into any home to convert it from a normal home to a smart home, just as autonomous vehicles have a sensor suite. And they started out pretty kludgy, almost more sensor than car. But over the course of many years, became both more streamlined and more effective until today, when at least some autonomous-ish cars look just like normal cars. And we hope for that same kind of evolution with a smart home sensor suite. So let's start with version 1.0. This is a single sensor that snaps in underneath a doorway. We called it door jamb. It has a number of sensors embedded in that enclosure, one of which is a motion sensor. It also has a doorway sensor to see if the door is open or closed, temperature, magnetometer, and light sensors inside, and an ultrasonic rangefinder that points straight down to the ground. And so when a person walks under the door, it measures the distance to the top of the head and can tell that this particular person is 5'6", whereas this other person is a little bit taller, around 6'2". And it's also slanted just enough to give an asymmetric sensing region, so we can tell that a person walked into or out of that doorway. Now, knowing just a single doorway doesn't help us do a whole lot. We don't care about the doorway itself. What we want to know is where the person is in the house. And so to get there, we assume a person installs one of these sensors on every doorway in the home. And we don't know the shape or the floor plan of that house. We just see a big bag of sensors. And the data reveals each time that the same person of the same height walks from one doorway to an adjacent doorway. And that allows us to build this adjacency graph where every pair of adjacent doors has an edge. And each clique in that graph can be converted into a room. So we get a graph of rooms that are connected to each other through doorways. And then we pull out that magnetometer sensor in that package to try to tell the orientation of the door. One is facing north, another one's facing south, others are facing east. And we do that for every doorway. And that gives us a constraint on how these rooms fit together, but not enough constraints to actually reconstruct the floor plan of that house. So there's one more thing we use, which is that light sensor in that door jamb. And that light sensor helps us to identify windows. So as the sun moves across the sky, you get a different light profile in a room based on which direction the windows are facing. So rooms with an east-facing window will have more light generally in the morning, south-facing window, more light in the afternoon, and west-facing window, more light in the late evening. And north-facing windows won't have a spike at all. Using those sensors, we can now identify which rooms have windows in each direction. And of course, that constrains the adjacency graph between the rooms again, because you can't have a window, a wall with a window on it adjacent to another room. They're always exterior walls. And so now it's fully constrained and we can reconstruct that floor plan in the house. And if we go back to the original floor plan, we can see that it is topologically equivalent. The room sizes are not the same, but topologically it's the same. And so basically, that is our sensor suite 1.0. We can know whether somebody's home. We can know how many people are home, who is home, and to some extent where they are. Now, we don't have a great way of identifying where they are on the map. Those rooms are not labeled in any way. So we might say room number 1 or room number 2. That's better than nothing, but it's not as good as saying kitchen, bathroom, living room. And so we want to fix that. And in order to do that, we add 2 more sensors to our sensor suite. So this is our V2 that we started working on in 2013, where we add 2 sensors. One is the electric meter and one is a water meter. And these are in a lot of homes already. They are internet connected in many homes and can provide some amount of data in homes. A power meter or water meter can be really helpful to identify the things that people use if those things consume electricity and water. And for decades, people have approached this problem by trying to disaggregate the power measurements at the energy meter. The meter measures energy consumption of the whole house, so that's a blind source separation problem. How much did each appliance contribute to the sum of energy in the house? And this approach has proved quite challenging even after decades of work, especially for low wattage objects like light bulbs. Their energy consumption can easily get lost in the noise. Trying to detect a 100-watt bulb, which is a high power bulb, by searching for exactly 100 watts would produce a large number of false negatives, because due to noise, the effect of a light bulb would rarely be exactly 100 watts. However, if we use a range like 90 watts to 110 watts, that would produce a large number of false positives. Many appliances create transitions in that range. And so if we tried to look for a range of values, we'd get a large number of positives for that particular object that we're looking for. And this is one place where data fusion can become helpful. So let's take a light sensor, for example. If we add a light sensor here, we can detect light bulbs using both the power meter and the light sensor. And both will produce a large number of false positives, but that's okay. They can be filtered out as long as those false positives are not correlated. And so let's see how we do that. We filter that in 3 steps. First, we set our threshold to be pretty relaxed, so we get a high recall, or basically low number of false negatives, but less precision, so high number of false positives. Then we match the light transitions with power transitions. Anything that looks similar or even remotely similar gets a match. But anything that doesn't have a match, such as this 42 lumen transition, is eliminated. It's clearly not a light bulb. It could be just natural light, somebody's pulling a shade, or something else. Then we match the on transitions with the off transitions, the positives with the negatives. And in those cases, the lumen and the wattage both should match approximately. In this case, we have 3 possible matches. 2 possible matches, 46 and 90 matches with 39 and 105, or 46 and 60 matches with 39 and 60. But there are a few others that don't match at all in terms of on-offs. And so we eliminate those 2. Then finally, we take all of our possible matches and consider them all as a big group and look for recurring patterns, because a real light bulb should be detected repeatedly. We put all of the on-off pairs into a table and look for recurring instances with the same room location, light intensity, and power level. And those are what we call clusters. So we're basically using a clustering algorithm here, and those clusters are turned into actual light bulbs. In this case, we detected a 40 lux 100-watt bulb in the kitchen and a 60 lux 150-watt bulb in the bedroom. And we can do more than just identify that the bulb exists. We can also track its energy consumption over time. And so we evaluated this approach in 4 different homes, shown here as homes 1, 2, 3, and 4. And the graph shows a comparison between this approach called LightSense and its estimation of the energy consumption versus the ground truth energy consumption for each bulb. And you can see the relationship is quite high. The accuracy is above 90% in this case, which is, again, light bulbs are one of the most challenging appliances to detect using just a smart meter. But it became quite simple once we started using data fusion. And so again, this is a perception problem where the sensors are inadequate. Neither the light sensor nor the meter would be sufficient to detect those bulbs alone. but together it becomes a simple problem. And we can do this not just for light bulbs, but for any appliance in the home. So if a person were to work, if we often see, a toilet flow and a sink flow when a person walks into that south room, then that room probably has a toilet and a sink. And if we often see a light bulb and a TV when a person walks into that northeast room, then that room probably has a TV and a light bulb. And we can repeat that for basically all of the electrical and water fixtures and appliances in that home. So not only did we detect them, but we located them in the house on that map that we've built in the version 1 hardware. Then once we've mapped out the appliances, we can also create labels for each room. So rooms with toilets and sinks are probably bathrooms, whereas rooms with a fridge and a microwave are probably kitchens. If people use a room at night, it's a bedroom. And if people never stay in that room, but they walk through it often, it's a hallway. So now we have a semantic label for each of our rooms. And if we put that all together in real time, we get a system that looks kind of like this, where a person walks into the house, turns on the television, and the system is able to detect that the person walked in, TV turned on, a light turned on. The second person walks in and walks through the room, and the system detects that the first person is still sitting in the first room while the second person walked into the back. They pour some water, turn on the microwave, and the water fixtures and microwave are detected. Person leaves the field of view of the camera, but is still being tracked as they walk into a back room. And so this system here is basically what we get out of our sensor suite version 2.0. We now have semantically meaningful names for each room. And we can detect the things that people are using as long as those things consume energy or water. But we cannot detect usage of things like cabinets or windows or drawers that do not. We can also detect who is using those things as long as there's only a single person in the room. And if there are more than one person in the same room, there's some ambiguity about who used that object. And so to address these limitations with Sensor Suite v2.0, we add a new sensor, a smartwatch. Now, generally, a smartwatch can't be used to detect things like opening a door or pulling a drawer due to the noise created by just normal hand movements, things like gesticulation. But again, this is a place where sensor fusion can help solve the problem. The basic insight behind this approach is that interactions with the same object often have the same gesture. You flick a switch, you pull a door, you turn a knob. So let's dive into that in a little more detail. When you flick a switch, your hand moves upward. When you pull a door, your hand moves backward. And when you pull a door, the angle of the arm is at a different height, depending on whether it's a fridge, freezer, sink, or microwave, washer, dryer. These all have different angles. And the orientation of the hand also changes based on the orientation of the object. Sinks, stoves, fridges, washers, and dryers, doors, cabinets, windows, they all have a fixed orientation. Sometimes it's east, and sometimes it's south. And then finally, you need to be in the room to use an appliance. Except for the rare occasion where somebody shoots a remote control through a doorway, you need to be in the room to turn on the sink and in the room to open the door on the fridge. And these 4 features are what we call the object hallmarks: the direction of movement, the angle of the arm, the orientation of the person's body, and the room location, or the location within the home. And if you combine these 4 features, you actually can do a pretty good job of creating a timeline of the object usage for an individual person. Flip the switch, open a door, turn on the toaster. And we can also fuse this timeline with events from a power or water meter. So for example, if a person performs a light flick gesture and a 70 watts of usage is detected on the power meter, we can now attribute that 70 watts of consumption to that person. So that's basically our version 3.0. We can detect a more complete range of objects and who's using them with higher accuracy. And at that point, we've checked off the high level pieces that I think of as perception in the home. Who's there? Where are they? What are they doing? What are they using? But the story doesn't end there. There's more work to do in perception by layering on additional information sources. And the possibilities really are endless. But now that we have a proof of concept, I want to turn to the question of how do you streamline and simplify the sensor suite the same way that people did with autonomous vehicles. And so let's start looking at our sensor suite version 4.0. In this suite, we try to replace the door jam sensor with something a bit more streamlined. In this case, RF sensors. RF sensing is a technique that's now able to provide at least some degree of motion sensing, location, and even identity of people. As you know, RF signals propagate along multiple paths to get from the transmitter to the receiver. But the receiver can only measure the total mixed signal from all of those paths. The goal of what's called multi-path resolution is to take these measurements and estimate unknown properties of individual propagation paths, such as their angle of arrival, angle of departure, and signal power. Many localization systems already use this approach to remove interference from reflections because the reflection surface is unknown. And so they have an unpredictable effect on the received signal. But in this work, we take a different approach. Instead of eliminating the effects of multipath reflections, we use them for sensing purposes. Every multipath reflection becomes an independent measurement of the environment. For example, we found that theta 2 is actually a more robust indicator of room presence than a basic motion sensor. Motion sensors can only differentiate between motion and no motion, but theta 2 can actually differentiate between an unoccupied room and an occupied room with a stationary person in it, because the reflections, the RF reflections in that space are changed and affected by that person just being there, but they don't have to be moving. Isolating the reflection increases sensitivity over just using signal strength or CSI alone, since the effect of the multipath reflection is often small compared to the noise on the line of sight path. So by separating them and looking only at the multipath signal, we're actually going to get higher sensitivity. And the reflected path can also be combined with that line of sight path to form what we call a multipath triangle. And then we can use that geometry of that triangle to locate the target node, in this case, the computer that's transmitting. To do this, we first estimate the angle of arrival of the line of sight path and the reflected path. In this case, it's theta 1, theta 2. Then we estimate the angle of departure of those two paths, phi 1 and phi 2. And this fully constrains the shape of this multipath triangle, but it doesn't constrain the size. The triangle can grow or shrink arbitrarily and still have the same 4 parameters. And at first, it wasn't obvious that whether we could use this triangle for localization. It's well known that Wi-Fi doesn't have the bandwidth for time of flight measurements, at least not without combining multiple channels. And we don't know the location of the reflecting surface. So we can't estimate any of the edge lengths on this triangle, A, B, or C. And the breakthrough was that the triangle can be fully constrained by what we call relative time of flight between the reflected path and the line of sight path. That relative time of flight basically means the edge B plus C minus A has some fixed distance, fixed difference. For example, if I know the path along B and C is 1 meter longer than the path along the edge A, then now the triangle is fully constrained, both the shape and the size. And now the target can be localized, even though we don't know the location of that surface, that reflection surface. This is what we call multipath triangulation. It's the first approach that enables what we call unilateral localization, that you can locate something without cooperation from the transmitter. In effect, it's using the multipath reflections for the same reason that conventional triangulation uses multiple access points to get two angles to do triangulation. But it's a fundamentally different technique because conventional triangulation relies on the angle side angle congruence theorem. But multipath triangulation uses what we call angle relative side angle. And you won't find that theorem in any geometry textbooks, but the fact that it can be solved makes it the first approach to do unilateral localization. Something transmits, and the receiver tries to localize it. And when I say unilaterally, that means it can unilaterally determine that node's position and orientation by receiving one or more packets with no assistance from any other node, not another base station, and not even the transmitter. And it doesn't even have to be the access point that's doing the location, that's locating things. It can be any Wi-Fi device. There are often many devices in the home that transmit Wi-Fi packets. And with unilateral localization, any node that hears those packets can determine the location and orientation of those transmitters, even if they're on separate encrypted Wi-Fi networks. This means those links can be used for motion sensing, as I described earlier, or in the case of mobile objects, for mapping out the house floor plan. Now, we still haven't identified people with RF sensing, but there are several other groups that are working on that. Other RF sensing techniques developed by a group at MIT and others have demonstrated the ability to localize and identify people even through walls using what we call weak biometrics, such as body shape, heartbeat, and gait. They are weak biometrics because they don't uniquely identify that person in the world, but they do uniquely identify them in a small group, like in a house. These approaches do require some custom hardware, but it's still a lot less kludgy than putting a sensor on every doorway. And we expect these solutions, or some combination of these and new solutions, to replace some or all of the sensor suite version 1.0 by providing the same information that it did: the presence of people, count of people, identity of people, a map of the space, and the location of people on that map. That would provide a cleaner and simpler sensor suite without loss of functionality, moving in the direction of the evolution that I was talking about with autonomous vehicles, where the suite does the same thing or better, but with less hardware or less obtrusive hardware. In the world of autonomous cars, this would be analogous to replacing a big LiDAR scanner on top of the car with some advanced radar or solid-state LiDAR that fits underneath the fairings. Same function, less obtrusive. And now, moving on to the fifth sensor suite. We'd like to replace more hardware with, in this case, data. With autonomous vehicles, this would be analogous to saying, not all cars need LiDAR. Only a fraction of the cars need LiDAR to build a detailed model of the world, and the rest just localize themselves within that model. This path, or this particular approach, has the most unknowns so far. But we do have some proof of concept for using models to eliminate the need, either eliminate or reduce the need to directly access the power and water meter data. Let's take a look at an example. The goal of energy disaggregation is to produce an energy breakdown. Think of it like an itemized bill for the energy consumed in the house. My fridge used 1.5 kilowatt hours. My dryer used 0.7 kilowatt hours. The simplest way to produce an energy breakdown is to monitor the energy consumption of each appliance individually at the plug load. But that's difficult and expensive. Instead, people have approached this problem by trying to disaggregate the power measurements at the meter. And as I mentioned earlier, this is a blind source separation problem that has been challenging. Some results show that performance improves by increasing the sample rate of the energy meter, sometimes to tens of thousands of samples per second. That gives us finer grain resolution on what's happening, what energy is being consumed by that appliance and how it changes over time in order to make it easier to recognize. The problem is commercial smart meters can't actually provide data at that rate. So if that was our solution, it would be difficult to roll out. In this work, we took a different approach and asked, what accuracy can we achieve with only one reading per month? The rationale there is that many homes already have that data. It's called the monthly energy bill. Now, it's basically impossible to tell how much energy each appliance consumed that month based only on a single number. So instead, we learn a model to predict the energy of each appliance based on a few different things. The house properties like square footage and the number of bedrooms, number of floors. These values can be found in public records. The weather. The weather is also a public record, and it's a pretty good predictor of heating and cooling usage. And seasonal patterns in energy bills. Homes that have efficient heating and cooling have less difference between summer and winter bills, whereas homes with more heat loss or an inefficient heater have a bigger difference. And so from a set of training homes that have ground truth, which means perfect information about how much each appliance consumed, we train a model. And a simple way of looking at that is that we create a table of all the homes with the data, all of the training homes. In the first row, we're showing the house properties, how many people, how many rooms, whether it has a home office. Second row shows things like weather, temperature changes over time. Then we have 4 rows in this case, but generally it's more of the energy actually consumed by each appliance. And this is a known value for the training homes, not a known value for the test homes. And finally, in the last row, we show the monthly energy bill, 12 values for each house. So how much each home consumed in total that month. Now we have this matrix. And the next thing we do is to factorize it, to learn the so-called latent factors of the appliance types, the months and homes. So basically that means try to estimate values for each appliance class and for each home that when multiplied back to each other, reconstructs the data in that table. Now finally, we add test homes to the same table. And for the test homes, we have the house properties and we have the weather and we have the monthly energy bills, but we don't have those values in the energy values for each appliance, which are the things we're trying to estimate. But we can use the values we do have to learn the home factors for those homes. And now multiply those against the appliance factors, which have already been learned by other homes in order to reconstruct the energy consumption for each appliance in those homes. So we evaluated this approach on a public data set called Dataport, which has 516 homes in the Austin, Texas region. And we used 12 months of data from those homes. And we compared against 5 state-of-the-art baselines. And evaluated using leave one out cross-validation. The results show that this approach, using only one value per month, performed better than all the baselines, which had one value every 15 minutes. It's a surprising result. We're able to achieve higher accuracy with a much lower sampling rate. Now in this graph, no single baseline was the best for all appliances. And so the bars in this graph actually indicate how much the error was reduced compared to the best of all the baselines for each appliance. So it's in a higher bar than actually any of those individual baseline approaches could achieve. Now, the basic intuition of how this works is that, yes, every home is unique. Every person does some different things, but there's also a lot of commonality across homes. And a model built on a really good information about similar homes can be better than a model built of pretty good information about the home itself. This proof of concept only used 3 pieces of information: the home properties, the weather, and the monthly energy bills. Now think about what more would be possible if we combine it with data from the actual sensor suite: motion sensing, identity, person location, person object usage. For example, certain actions like cooking and laundry are more likely to occur when certain people go into certain rooms and make certain hand gestures. Certainly more likely than when those rooms are empty or when they're not making those hand gestures. And so if we had a monthly energy bill along with a watch and some RF sensing, could we do a better job detecting not just average energy consumption of those appliances, but real-time energy consumption? If Sensor Suite version 5.0 were successful, then this starts to look like something that really could be in any home, not just in experimental prototypes. To make it work, however, we need data sets to train those models. And this is a known gap for this approach. And in fact, for the perception problem more generally. The first step to learn any model is typically data annotation. In this domain, the biggest public data set that we have is Dataport with over 1,000 volunteer homes, which is a large data set. But compare that to things like ImageNet with tens of millions of annotated images, or autonomous vehicle data sets collected by companies like Waymo or Tesla, where Waymo has over 20 million miles driven on public roadways, much of that annotated or some of that annotated, and over 20 billion in simulation, all of which is annotated. The data sets that we have today, not just for the smart home, but for the IoT in general, are small compared to the task of perception. And additionally, the Dataport dataset does not even have all of the sensors for any of the sensor suites that we discussed so far. It's only energy meter data. And the data sets that we do have that have multiple sensors that could be used for learning fusion models or perception models, those data sets number in the tens of homes. They're quite small. This is a known challenge for not just the smart home, but for the IoT in general. And I believe this is an important question we need to challenge ourselves to as a community of, is this part of the reason why we're in the trial of disillusionment, why the IoT is in a trial of disillusionment, people are having a hard time creating value from their data? Is it just a matter of collecting more data, higher quality data with ground truth and/or annotations? And how do we need to innovate in order to make that happen? With that, I do want to thank you for your time and any questions?
So we have time for some questions from both the local audience here and online audience. If you have questions and you're not here in the stadium auditorium, you can enter them on Slack. So,
thank you for the interesting talk and the history and how things evolve over time. So I just wonder, like now you work in Amazon, do you see that to some extent that gap was mitigated because now you have access? Well, not necessarily, to user data per se, but you do really have, devices in people's home.
That's a good question. And you're absolutely right. There's no access to customer data. And so it's not necessarily easier to get access to large data sets at a company like Amazon. In fact, in some ways, it can be harder. And I do think it's something where this community, the academic community, can really contribute. If you look at a lot of the open source data sets, things like ImageNet or speech recognition, automatic speech recognition, a lot of the data sets actually originally were derived from academia to help prove the case that they would make a difference. Of course, the effort is significant. Data collection is hard, annotation is hard. I think some companies have an advantage in the sense that they can make that investment, but I don't think it's just an investment question. I think this is a prioritization question from our community. So I hope that answered your question.
Thank you. Yeah, because I feel like I think there are at least two reasons. One is that the sensors are very heterogeneous. It's not like image data or video data, right? The other is sensor annotation is hard because it's not really easy to be done by a human. Unlike if you look at a picture, you can tell there's an animal or like a pedestrian sign. Like if you look at MU data, it's very hard to tell like whether this person is walking downstairs or upstairs. I felt that I haven't seen, like, even despite a lot of talking, and certainly it's important to have large data set and open data set on par with ImageNet, but I haven't seen a way to solve that problem. I'm not sure whether you have further insight on that.
I do have a bunch of thoughts about that. I don't know if we want to turn this into a brainstorming session. I'm happy to do that, maybe offline. But yes, I think there are certain specific challenges that we can actually address. Some of those include, as you mentioned, ground truth. Whereas a human can go out and annotate images, an untrained human, or speech, it's very difficult to annotate sensor data, especially when it's somewhat opaque and hard to understand what it is just by looking at the data. So one way to get around that is with ground truth sensing. So you use sensors as ground truth for other sensors. That's a hard problem, especially in the home. People don't like to have ground truth sensors in their home, certainly not at large scale. But there are ways of doing cheaper ground truth sensing. So some of those, my team has developed several of those, things like RFID based location and ID tracking, things like Doorfly that is basically a camera based system that is privacy sensitive. So it does not upload any images, and in fact cannot upload images. Uses instead thermal cameras to detect the features of a person in order to recognize them as they walk through a doorway. So things like this, if made cost effective enough, could be good ground truth sensors for things like location and identity, especially when combined with some of the other sensor systems out there, some of the RF sensors.
Okay, thanks.
We have a question from the Slack from Clayton Miller. What roles do the feelings or preferences of occupants play in this area? For example, how do the feelings of cold, hot, distracted, focused, annoyed, and etc. impact the development and use of prediction models? So how do personal preferences impact prediction models?
That's a good question. It certainly does. And if you're trying to do something like heating and cooling control, knowing that somebody has a general preference to turn the temperature down at night is different from them wanting to turn it down tonight, because tonight they're cold. And so that certainly does matter in terms of prediction accuracy. In terms of perception accuracy, it may matter less. So if I think about our own human interpretation of a house that you happen to be in and with other people in the house, who's there, what room they're in, what they're trying to do. Those are things that I think we would understand. Is that person feeling hot or cold? Is not something that as an external human in the same room, we would necessarily know. We'd probably have to ask them. So I think of that less as a perception question and more of a data collection challenge. If you did want to do automated control, how can you get feedback from people more quickly and easily in order to facilitate that control?
So we might have time for maybe one or two more questions. So Kamin, can I also ask a question about since you have been in academia for some time, and you have also now been at Amazon for a few years, could you maybe share with us your what do you feel about the differences are between industry and academia, and maybe some advices for our audiences here, so that we can work on exciting projects that are both academically exciting as well as something that we can put in millions of homes and in real products?
A good question. I think at a high level, they're very similar. In both places, you try to solve hard problems and work with great people, and that's the most important thing in any of these. For any sort of career decision. In terms of research problems, I think there are some differences, and I think the might be more too subtle of a topic to discuss right now, but there are a few ways of thinking about that. One is just in terms of size of project. I see, DARPA scale projects being run on a regular basis at Amazon, whereas DARPA scale funding in academia can be a challenge. And so when you're really thinking big, thinking huge, it can actually be just as easy to do that in academia and in an industry, if not easier to do. At the same time, thinking far out, meaning 20 years out with no immediate milestones or benefits of the value of the work is harder. That really is a place for academia to move ahead of industry and to help guide the next projects that industry is doing. And so I think of it as if you think about it as two different dimensions of size and time horizon. One is probably very much on one axis and the other is on a different axis.
Great. So with that, let's thank our speaker again. Thank you, Kamin, and thanks to everyone here.
Thank you.
Thank you. All right. So with that, we will be taking a 5-minute break, and we have two communities here. For the SenSys folks, I think they should stay in this room, and the next session should start in about 5 minutes. And if you are from BuildSys, please go to room C1A3 and we'll start our opening remarks at 10. So let's see you guys there.
Good. Well done. BuildSys has started then. Well done. Always is like that. Everyone can be yeah.
There's a bird. Oh, it's a bat?
Okay, okay. Can you hear me? Okay, okay. Okay, let's start. Firstly, let me introduce myself. I'm the Zhijun Li from the Harbin Institute of Technology. I'm now in the China, and it's an excellent meeting, but we cannot attend locally. So it's my great honor to host this this session about the low power communications. We have in this session we have 3 speakers and 3 papers. Now we can just start the first paper. The title of this paper is Morphe software defined charge storage for the IoT. Let me introduce the presenter of this paper, Danny. Danny is a professor with the Department of the Computer Science of KU, Belgium, where he leads the networked embedded software task force. He has a PhD from the Lancaster University in the UK and has since worked as a visiting scholar with the University of California at Berkeley, and a visiting scholar with the University of the Sao Paulo, and as a lecturer with the Xi'an Jiaotong Liverpool University. His research focused on the full IoT stack. In 2016, Benny co-founded SenSysBuildSys, an industry IoT company which has deployed plug-and-play IoT solutions in over 30 countries worldwide for applications that range from smart agriculture to predictive maintenance. Yeah, Danny, can you just start your presentation, and we have we have 20 minutes. Okay.
Thank you very much.
Okay.
So I should say before I begin that I'm not the first author of the presentation. Fan Yang, who kind of conceived of the idea and led all of the execution, actually left KU11 to join Bosch in Shanghai. So it was a bit more difficult for him to travel. So the honor for presenting the presentation falls to me, but it's very much a team effort, including Ashok, Sam, Wouter, and Meng Yao, who's also here with me as well today. So a bit of kind of pre-context before I get into the presentation. Within our group, we've been doing some work on energy harvesting and energy management for energy harvesting systems. We tend to focus on sustainable energy harvesting systems, which is kind of a subtle distinction, but has a rather large impact on how you architect the hardware solutions. So this is not really a talk about intermittent computing or support for intermittent computing using very small capacitors and reacting very quickly. Actually, what we like and have been trying to work on for a while are effectively as close as we can get to drop-in battery replacements, which let you do energy harvesting to extend your lifetime, but at the same time, they're going to behave, we hope, in a more stable, predictable, and easy-to-use way. The vision, whichever way you go, of course, with energy harvesting, is that we would like to dramatically extend the lifetime of the devices that we have available to us today, on the one hand. Or on the other hand, if you know your lifetime, for example, it's an industrial machine, it must last 20 years. Well, you could do that on a lithium thionyl chloride battery, that's just fine if you have low data rates. But using energy harvesting, you can dramatically expand, of course, the work that you can do. So that's the flip side in cases that you don't need that extreme long life. Similarly, when I was working with a spin-off, a request we'd frequently get in contracts would be for a guaranteed system lifetime, because companies really do care about the hassle of replacing batteries and systems, or even worse, just scrapping whole devices once the batteries run dead, which is something that I think is a terrible, terrible idea. And all of us, of course, should try and avoid. So yeah, We maybe take a slightly different path, but just like any energy harvesting work, what we're really trying to do is avoid this electronics waste and unnecessary human effort. While we love energy harvesting, we have noticed that our industrial partners aren't quite convinced yet of applying energy harvesting unless they have a very stable power source. So for example, you have a machine with a rotating element, no problem. You know exactly how much power you can draw. But in the more general case, we see that people really struggle to build systems that can manage the heterogeneity of different energy supplies, different hardware platforms. Dynamism in power supply, obviously, because energy harvesting typically comes and goes. Every source is different. But also dynamism in the software base, because it's been a long time since the community agreed that sensor networks would be static, fixed, and never change on a node. We've had over-the-air updates for a while. We are building more and more dynamic systems. So not only will your energy supply be dynamic, but typically your power draw also will, especially if you introduce an accidental power bug, for example, and suddenly see that your system's lifetime is going down and down. Now, we don't really have like an ideological opinion about whether or not systems should include batteries or supercapacitors or regular caps or both. But if there are no real great rechargeable batteries, if you want to extend lifetimes past, let's say, 10 years or so at the moment. So that means that typically you're going to have to deal with supercapacitors at some level. And that means managing small amounts of charge. And just because they're small, they're going to change quickly. What we think, completely self-serving, of course, an ideal charge storage system would look like is, number one, it would provide you with some form of charge isolation. So thinking back to SenSys from a few years ago, there's a great paper on the tragedy of the coulombs and the fact that any one buggy or power-hungry element of a sensing system can, of course, deplete the entire charge on the system. If you have a very small reservoir, it's very easy to do, and you can leave yourself with a completely non-functional system. So isolation would be great for per software task, preferably. Quick charging would also be very nice. It's well known that if you just slap a very large capacitor on your system, while you may be able to sustain a long time, it's going to take you a long time to get an operational charge. And depending on what kind of harvesting you're doing, it may take so long that you never really reach an operational status. So quick charge would be nice. We'd also like some kind of reactive behavior to power failure in the event that power is lost for longer periods. And finally, we'd like to kind of smooth away all that dynamism, or as much as we can anyway. So we'd like to present the developer with again, something very much like a drop-in replacement for a battery. Oops. We think that by kind of putting these things together and giving sensible software abstraction to support it, we can dramatically reduce developer effort. We looked around and we draw inspiration from many different systems. So this is not something designed in a vacuum. We love things about UFOP, for example, another SenSys paper, which had decentralized capacitor arrays dedicated to peripherals. What we noticed, though, was that for some of our complex peripherals, like logging accelerometers, which are already a module, the idea of statically speccing charge wasn't so easy. And in addition, we have these plug-and-play sensors where we customize at runtime. So then it would be very nice to be able to do stuff dynamically. I won't continue going through each one. I guess it's important to highlight Capybara, though. So Capybara shares quite a lot of commonality with our work in that it has a reconfigurable cap array that you can grow and you can shrink. So taking inspiration from the decentralization and the idea that you should be able to change your capacitor array at runtime, we kind of just go to the logical conclusion and allow you to not only change how many caps you're using, but also to put them into all configurations of series and parallel, and then with a bit of software intelligence to do those nice features that I talked about. At the core of Morphe, it's a hardware and a software system. So we started from the features that we want, but we did have to build some hardware around it. There's no way to avoid that. And at the core, we have this kind of capacitor array where the capacitors can be put into, I think, literally any topology. We have a series of micro switches, which are very efficient, and they let an onboard microcontroller configure that array however you want it to look. We really wanted to keep the software concepts kind of lean, because what we noticed with some of our previous work is that while it's really fun to build kind of complex abstract concepts, it's also the enemy of them being used. So we did just two things here. The first thing is a thing we call the energy semaphore. It connects to your embedded operating system. The specific requirements, I'd maybe leave until questions. We tend to connect it to real-time operating systems, where obviously it's a very natural fit. You already have semaphores. This is just another semaphore. But now it's going to tell you whether or not a task has the energy to run, as opposed to the traditional ways that we use semaphores. The second software concept we have is the energy watchdog. So all embedded developers know watchdog timers. We all have to deal with them at some point. And the energy watchdog is just what it sounds like. You can spec a task, run it, and if it exceeds the energy expectation that you have for that task, the watchdog will be triggered. Similarly, if the entire system is heading towards failure, the energy watchdog will again be triggered and will allow you to react to that. Here you can see a diagram from a hardware perspective that shows the Morphy system. It's a power module. It's not a moat. That's important to stress. So there we have at the top of the diagram, what we call the polymorphic capacitor array. That's the reconfigurable set of capacitors. In addition to the core capacitor array, there's also a backup capacitor or battery included. In actual fact, we find it very useful to include the battery, but it isn't required. You can operate just with the backup capacitor. These two power sources actually provide power to the intelligent components of the power module, and that is the power energy storage controller, in reality just a microcontroller that fits the bill, and the real-time clock right there. The only reason there's a real-time clock is it lets us push sleep power down even lower, so we can get down to some low tens of nanoamps in sleep mode, which is important because we're now saying we should shove a whole microcontroller into your battery. At the output of the whole array, we do expect that your platform has a regulator. In reality, this probably goes on the moat, not on the Morphy board as you see here, because your moats will have different requirements. We're rather agnostic to the energy harvester. We expect that this is going to be a DC supply. So if it's like a piezo or something, then you have to have the conditioning circuitry on the front end. But in terms of voltage ranges and stuff, Morphy is extremely flexible. So once you have your DC output, you should just be able to plug it in. To talk to the actual moat, there's a serial connection, currently just UART with an interrupt line to say that you want to talk. I'd love to move it to talking over the battery terminals. We aim to do that in a future version. And then on the micro itself, we have basically like a lot of syntactic sugar that gives you an easy interface to talk to the module and set your requirements. We fabricated a couple of different versions of this. So the ones that you see here, the original target was to meet a standard square 9-volt battery kind of size, like a PP3, I forget the term. We didn't quite make it, in all honesty. There's a little tiny knobble at the end of the PCB there, which is bigger than the battery, but we got pretty close. There's also as well a more demo and experimentation friendly version of the board, which is larger, and you can kind of intercept different things on it. From the point of view of the software stack of Morphy, as you can see here, all the charge management logic runs in the module. So we're taking all of that kind of pain away from the application micro, with the assumption that by separating that concern, we can do it better in one place dedicated. There's an API parser there, obviously, to read the serial port commands and send responses. And then basically, apart from that, all you have is to manipulate the switches so that you can control the array and also sense your incoming power by disconnecting it from the array, and also sense voltages at a ton of different points. So it's conceptually very simple. It is, in terms of routing, as you can see on the board, and the number of things that you have to look at, quite complex. But again, you do it one time, and that logic lives on the controller. You don't have to do it for the next mote and the next mote, and so on and so forth. The application side is a bit more interesting. On the application MCU, we've integrated for the prototype with FreeRTOS. We just need an OS that has an explicit notion of tasks. So for example, Riot would equally be okay. Kentucky would be okay. But if you're writing a while one loop, well, you'll have to do a lot of work to integrate because we need you to tell us what each part of your code is doing. So not too stringent requirements, but we do need some OS there. So the Morphe library is talking to the module. It also integrates with a scheduler to support the semaphores. And yeah, all you have to do to use it, as I'll show in a moment, is register your task. When you make a task that you want to run with Morphe, the first thing that you're going to do is to tell the power module how much charge it needs. This is a little clunky because you have to do some experimentation. And one of the, a very insightful reviewer comment that we got is that you can do this automatically. You definitely can. So you can benchmark those tasks based on how much capacitor they use, but we just haven't done it yet. We have another piece of work from a few years ago where we just did that benchmarking using the caps, and it works very well. So anyway, you register your task, as you can see at the top there. You'll get back a task ID, which refers to the task semaphore. That gets registered with a real-time OS. And then every time you come to run it, you're going to call run task in the Morphe API with a reference to that task ID. If you're able to run, you'll get back a semaphore value, which is greater than 0. We use the counting semaphore. It doesn't really make any difference right now, but we assumed in the future it could be interesting information to see how many executions that you had when you call it.
Just raise your hand.
Not sure where that came from. The other two software concepts that you have to connect to are the energy watchdog, and you do that by, sorry, everything should be on mute. Oh. Okay, so you do that by setting a bug handler, which receives as its argument the task that's buggy, and also a brownout handler. In the case of the bug handler, you can put whatever code you like in there. We have some support for blacklisting tasks. In the case of the brownout handler, you can likewise put whatever you like in there, but after that method completes, the moat will be turned off because we're now heading into a zone where we can no longer support the power consumption of the device. I'm going to have to speed up a little bit now so we can come back to how specific. So I'll go quick, but then we can come back to things and questions if it's unclear. So number one, the core feature we build on is this isolation. So Morphe can pull a capacitor out of the array. That's going to be your task capacitor when you execute. In the original version, it can be any number of capacitors. In retrospect, I think this was overkill. We used rather large caps, and actually just using one each time will do the same job. Now, of course, once you've done this and we have the energy watchdog, it means that you have a fairly good level of safety against any power bugs. And a task can drain its own cap, but the energy watchdog will be triggered, and at that point, the task will be terminated. So you can no longer drain the charge for the entire device. The second thing that's very nice that we can start to do with our reconfigurable fabric is to boost voltage when we need to. So it might just be that we have a supply with a lower voltage than we need. That happens all the time. It might be that we aren't fully charged yet. But what we can do is we can, when we charge the dedicated cap, we can boost it by connecting from not parallel, but increasingly series configurations. And so there are 16 caps on the current version of Morphe. If you only need one for your application, you could do a 15x boosting of the available voltage. A more complex feature, but it builds on the first two that you saw, is fast charging. So the capacitance of a set of capacitors in series is the reciprocal of their sum. In parallel, they just add. So what's kind of nice is we can make the cap array we can reduce its capacity when we're charging so that it quickly reaches a minimum operational voltage. And remember, that's an operational voltage, including the boost, which we can now do. And then as the voltage saturates, by which I mean it grows close to the input voltage, we can then switch to increasingly parallel configurations. So what you see is that basically we start off with the equivalent of the smallest cap we could have. And then as the voltage increases, we go more and more series again. So we're like a small cap in how quick we charge, but we can accumulate a lot more for when power fails. So you'll last longer. Delayed brownout is much the same, but it goes in reverse. So I won't spend too much time here. There is a final failure mode where if even that isn't working, it just starts to put more capacitors from the main array into the isolated array until eventually you hit brownout. Okay, so the evaluation for Morphy is rather simple. In the first case, we want to compare it against the different fixed size capacitors that we have in the array. We use the same cap in all the experiments. I don't think this is particularly unfair. We just picked a certain cap. You may prefer a different one. But unless it's very tiny, the results should generalize. As you can see, Morphy, which is the gray line here, will naturally track the charging speed of the smallest capacitor. Then, as you see, when the voltage dips right there, we go more series. We again follow the charging speed of the next largest capacitor, and so on and so forth. So what that means is by the time you get to the end, and we've acquired as much charge as we can, we've done so much quicker than the red line, which is if you just used a big cap in the first place and let it charge without any reconfiguration. So you get a little bit the best of both worlds. This graph, I can explain in one sentence. If your operational supply is below your voltage, obviously nothing else would start. With Morphy, it can. So you can see that here, as soon as we have enough voltage to execute our task, including the boost, we can run. How would this look if we then move on to more complex scenarios? Here we have, it's a lab-based scenario, which we implemented using some using a programmable power supply and then some simple test loads. We have a set of tasks with different power consumptions, and we have a phased evaluation where we increase and decrease the available power. Available power, as you can see here. So the headline from this is just that for any of the fixed approaches, and this is a decentralized array similar to UFOP, Morphy will be able to begin operating sooner simply because of the voltage boost. That's as expected. And for all of the different tasks, no matter how many capacitors they reserved, we can actually do more executions within the scope of the evaluation. So to conclude real quick with some limitations and a bit of discussion, I think that the original design is rather overcomplicated. In the paper, you'll notice all the experiments are done with 8 caps, not 16. So we really built the PCB with 16, but in the end, it was kind of overkill for what we wanted to do. It's a trade-off between granularity versus the overhead of building the thing. It works best for large capacitors. So if you use tiny ceramic caps here, it's not going to make much sense because the polling frequency you need is going to get really high. Having said that, as you can see, we can meet the form factor of the battery pretty well. And especially if we scale down the number of caps we're using, that should be no problem at all. So if you're not striving for a very small form factor, I would say it could still be interesting. Finally, and to go back to a discussion from the keynote on the first day, it works absolutely fine without a battery, this system, but it's so much nicer with a battery. Because in that case, what we do is we have a long life lithium thionyl chloride battery that is the largest kind of watch battery. And that provides all the power needed for the active parts of the module. Never runs the motor, it just does that. And that means we get the long lifetime, but extreme predictability you always get from kind of a good battery. But on the other hand, we can do way more work than if you just ran within the kind of the current you'd have over time. But it isn't required. You can just use a backup cap instead. I'm way over time, so I'm going to leave it there and talk about next steps. It's open source and online, the hardware and the software. If you're interested, please do go ahead and take a look. We're also planning to make some, so if you're interested but you don't want to build the nasty PCB, do let us know because it could be fun for us to send some to different people and let you play with them. And I guess that's it. Thank you very much.
Okay, thanks. Okay, thanks. Is there any questions? Yeah.
Hi, so I have a question regarding the charge transfer between capacitances when you're switching between your series and parallel configurations. Do you agree that transferring charge from a larger or from a cap that has a higher voltage to a lower voltage can be extremely inefficient, right? In the order of maybe 50%.
So I'd have to refer you to Fan for the exact numbers, but we picked caps with extremely low ESR values. So we made it as efficient as we could make it. And the overhead of doing it is measured and captured in the graphs. But I couldn't tell you the exact overhead for that capacitor, I'm afraid.
Okay, no, so it's just that it's known from circuit theory that when you have these two these two capacitors at different voltages, it's even independent of the resistance value. So even if you have low ESR, even if you have very efficient interconnections and your switches and whatnot, charge transfer is very inefficient. So it just seems to me, did you do any measurements regarding the efficiency to compare how much or less efficient it would be compared to a system with a single capacitor where there would not be charge transfer?
Well, in the evaluation, the second part of the evaluation, bear with me here. In the second part of the evaluation, it's compared against single capacitor systems, but there's no explicit evaluation of the efficiency now. So
it is significantly different than just looking at the voltage, though. So I think maybe in the future work, this type of evaluation of the energy efficiency overall from what you harvest to what is eventually used into the application, I think could be very helpful.
I agree. I think that there's a dimension. The dimension where we didn't do very much is like all the static local efficiency stuff. So just we talk about charge transfer efficiency. It's also very interesting to compare things like the leakage current of this versus different approaches. So there's more that can be done there. So we will keep going, and I do expect that we'll do more experiments with that as well.
All right, thank you.
Thank you.
Thanks. Some other question? Okay. Excellent work. I have a question, and it's a very good work interesting work for the Morphy. And I wonder, is there some limit of the number of the capacity in your system? Is there any limit of the number of the capacity? Okay.
Yes, I think we went too far already, because basically, as you add your extra capacitor every time, you get less proportional boosts. So I think honestly, 16 is already, there's no limit in the sense that you can keep adding them. That's the thing that you can do. That's no problem. But you have diminishing returns. So the extra boost that you get and the extra flexibility that you get goes down and down with each capacitor you add. So the next one we build will have 8, but that's just kind of a wave of thumb at an engineering decision. That's all.
Okay, thanks so much. Yeah. Thanks so much. Okay, let's start the second paper. Okay.
Are you going to use this one or those?
Okay.
Can you please stop the screen sharing? Thank you.
Okay. Now let's begin. Let's start the second paper. The second paper, the title of the second paper is Alf-Red Virtual Memory for the Intermittent Computing. And let me introduce the presenter. His name is Andrew Melini, and he is a third-year PhD student at the Polytechnico di Milano in Italy. I'm sorry. He received his master's degree in the computer science and engineering engineering from the Polytechnical de Manila in 2019. His current research focused on the enabling battery-free computation for the embedded system powering the IoT, the Internet of Things. Now we can just start, and we have 20 minutes. Okay.
Thank you for the introduction. So I'm Andrea, and today I will talk to you about Alfred, a virtual memory abstraction and compilation pipeline for intermittent computing that resolves the dichotomy between volatile and non-volatile memory, and as we will see during the evaluation, lowers the program energy consumption by up to 2 orders of magnitude. So, so the Internet of Things includes several billions of sensors that are all powered using only batteries, which must be periodically recharged, replaced, and disposed. And this, of course, introduces a significant environmental impact. So to address this problem, researchers want to remove batteries and power these devices only using the energy harvested from the environment. Then a capacitor acts as energy buffer and smooths the fluctuation of harvested energy. However, using such constrained energy source causes devices to experience frequent power failures, and they compute intermittently. So the device has an initial period where it is powered off and harvests energy to recharge its capacitor. Then it powers on and starts computing until it empties its energy buffer. And here the device immediately shuts down. And this behavior is repeated for the entire device lifetime, from which the name intermittent computing. However, we must consider that these devices are highly resource constrained. They usually execute a single application and does not have an operative system that manages power failures. This means that whenever the device shuts down due to a power failure, it also loses the computational state. And this means that in the next power cycle, the device will have to restart the computation all over again. And this not only represents a waste of energy as the computation achieved during previous power cycles is lost, but also makes devices unable to complete their workload. So to address this problem, the literature provides several techniques that are all based on the same idea. During the computation, the device pauses the program execution and saves a copy of its volatile state onto a non-volatile memory location. This copy usually contains the program counter, the stack pointer, the register file, and the main memory. Then, whenever the device restarts after a power failure, it restores the copy from non-volatile memory and thus resume the computation from where the state was saved. However, saving the state introduces a significant energy and computation overhead, because first of all, the device needs to copy all of its volatile state into a non-volatile memory location, and also non-volatile memory accesses are extremely expensive. Just to put things into perspective, if we consider one of the most popularly used microcontroller units in intermittent computing, which is the MSP430FR5969 from Texas Instruments, at a clock frequency of 16 megahertz, non-volatile memory accesses require 1 extra clock cycle and consumes more than twice the energy of volatile memory accesses. So to try to reduce this energy overhead of state-saving operations, the researchers try to rely on mixed volatiles microcontrollers that feature an internal non-volatile memory location, which is directly addressable from the microcontroller unit, and use this non-volatile memory location to directly allocate portions of main memory. As now a part of the state of the program state is already persistent, state-saving operation need to save only the volatile portion of the main memory. And as we are able to reduce the overhead of state-saving operations. However, now the program instructions that read and write memory directly access the slower and less efficient non-volatile memory. This means that overall the program energy consumption increases. And also to complicate things, the program state now is shared across volatile and non-volatile memory. And the volatile portion is saved only when state-saving operations save it. And this may introduce intermittence anomalies, which essentially consists in unexpected behavior caused by power failures that are unattainable in a continuous execution and may cause the device to produce wrong results. So for these reasons, identifying the optimal trade-off between a reduced volatile state and an increased energy consumption is non-trivial, because the more elements we decide to allocate to non-volatile memory, the lower it gets the energy overhead of state-saving operations. However, the higher may get the program energy consumption, potentially nullifying the effect of a reduced save state in the first place. And for this reason, trying to manually exploring all the different possibilities is non-trivial and may lead to suboptimal performance. And moreover, the literature does not provide any technique that automatically explore these different possibilities and identifies the most efficient mapping. So to address this problem, we designed Alfred. So Alfred consists in a virtual memory abstraction and in a compilation pipeline that automatically identifies the most efficient mapping of the program state across volatile and non-volatile memory. So Alfred virtual memory abstraction is transparent to programmers, as they do not need to learn any new syntax, and they simply need not to specify any mapping for their programs. Then, once programmers wrote their programs, Alfred instruments it with a given forward progress technique that statically plays state-saving operations inside the program. Okay. Then, as next step, Alfred translates the source program into an intermediate representation, which is essentially very similar to machine code, however, does not contain architectural dependent elements. And this makes Alfred to be architecture independent. So after this step, Alfred then partitioned the program into computation intervals, which essentially consists in sequences of instructions that execute between two state-saving operations. As next step, Alfred maps independently the virtual memory of each computation interval to volatile and non-volatile memory. The mapping that here Alfred produces is not fixed. This means that a slice of the program state may have different mappings across the same computation interval and across the entire program execution. However, this mapping is resolved at compile time. This means that Alfred does not introduce any runtime overhead to identify when, where, why, and what slice of the program state must be allocated to volatile or non-volatile memory. So for each computation interval, Alfred firstly maps all the virtual memory to volatile memory, and then identifies the memory variety instructions that must target non-volatile memory. So I will present here a very simplified example. However, of course, a more extensive description is available inside the paper. Let us consider this simple computation interval, for which, of course, Alfred considers the intermediate representation. And let us focus on the memory variety instructions that target variable A, that are line 2 and line 4. So line 2 produces an intermediate result, which is eventually overwritten by line 4 execution. And line 4 produces a final result, and it is the same result that the state-saving operations of line 6 save onto non-volatile memory. This means that this data, the data that line 4 writes, is the same data that we need to preserve across power failures. So following this intuition, Alfred makes line 4 to directly target non-volatile memory. This now makes line 6 state-saving operations to be redundant and thus can be removed. So as a result, we decided to increase the energy consumption of one single instruction, as now targets non-volatile memory. However, we are able to remove 2 instructions and we are able to save energy. So note, however, that line 2 still targets volatile memory, as it produces an intermediate result which does not need to be preserved across power failures, and thus there is no reason to also make it target non-volatile memory. Now, as next step, Alfred applies a similar reasoning, which is dual to the one that I show you, to memory instructions, and in this case, however, targets the restore operations. So just to give you an insight, in this same computation interval, line 2 is the first memory instruction in the computation interval that accesses variable A, and reads the same data that a restore operation would restore from non-volatile memory. So following the previous intuition, Alfred makes line 2 to directly target non-volatile memory, and thus the restore operations that target variable A are now redundant and can be removed, reducing the program energy consumption in a similar manner to what I showed you before. Now, as final step, Alfred consolidates the memory instructions, and this essentially consists in 2 different substeps. First, Alfred needs to ensure that memory instructions target the correct memory location. And this is because now the program state is shared across volatile and non-volatile memory. For example, line 4 now targets non-volatile memory. And so line 5, which reads variable A, now must target non-volatile memory to access the correct result. Then, as next step, Alfred evaluates the possibility of creating volatile copies of non-volatile memory location to increase the overall performance of the program. So this step essentially consists in evaluating the number of memory instructions that target non-volatile memory, and if they exceed a certain threshold, which depends on the device energy consumption, then Alfred creates a volatile copy of a non-volatile memory location and then makes target all the considered memory instructions to target this volatile copy, reducing the overall program energy consumption. Now, at the end of this step, all the memory read and write instructions automatically preserve the content of main memory, and as state-saving operations need to save only registers, as the mapping that Alfred produced ensures that the main memory is preserved across power failures. So, as I argued before, having the program state shared across volatile and non-volatile memory may cause intermittence anomalies. To avoid them, Alfred automatically identifies which elements, which memory locations are involved in intermittence anomalies, and then creates 2 different copies for each one of these memory locations and ensures an access pattern to these copies that avoids the anomaly in the first place. You can find more inside the paper. So in this case, Alfred does not introduce any runtime overhead, as also these accesses are resolved at compile time. And finally, Alfred produces the final firmware for the target device that is selected by the developer. So to evaluate Alfred, we implement a prototype into Shaptic, which is an extensible emulation tool for intermittent computing, which essentially emulates the execution of an intermediate representation of the program. And so we implemented Alfred pipeline to directly transform this intermediate representation in that Shaptic executes. You can find both the documentation and the code of our prototype at alfred.nestlab.it. For the evaluation, we selected as target platform the MSP430FR5969, which is a popularly used microcontroller unit in intermittent computing. And we extend Shaptic to emulate this microcontroller unit energy consumption. As operating frequencies for this device, we consider both 8 and 16 megahertz, as non-volatile memory performance depends on the operating frequency. And as energy source, we consider our RF energy source, which we model considering 10 measurements of real energy sources. And we extend Shaptic to simulate power failures accordingly to this model. As benchmarks, we consider an heterogeneous set of benchmarks that are commonly used in this domain, which are CRC for data integrity, FFT for signal analysis, and AES for data encryption. And as metrics, we mainly focus on the emulated energy consumption, as this indicates the end device performance. However, to investigate the elements that may affect energy consumption, we also measure the emulated clock cycles, the number and type of memory accesses, and the number of state saving and restoring operations. So for the baseline, so the literature provides a broad range of forward progress techniques that instruments the program with state saving operations. So we first design a framework that isolates the key dimensions of the state saving operations available in the literature, which essentially are 3. Where they allocate main memory, where they place, where and how they place state saving operations, and how they execute them. You can find more inside the paper. And then we combine these key design dimensions to either reproduce the same behavior of existing forward progress techniques or to explore new and interesting designs. So I will show you here the most interesting results. However, a more extensive evaluation is, of course, available inside the paper. So as first baseline, we consider a baseline that resembles the same behavior of mementos, which essentially allocates the entire content of main memory onto volatile memory. So here, Alfred overall always lowers the program energy consumption. And in the FFT benchmark, where the program state is huge, Alfred lowers the energy consumption by up to 2 orders of magnitude. And this is because as Alfred maps the memory read and write instructions to target non-volatile memory, state-saving operations need to save only the registers, whether instead the baseline need to save also the entire content of main memory. And also the overall lower energy consumption that Alfred experienced is thanks to his mapping, as it is able to map up to 90% of memory accesses to volatile memory, which is faster and more efficient than non-volatile memory. Now, as next baseline, we consider an hybrid version of mementos. And in this case, we consider the same placement of state-saving operation of mementos. However, we make the baseline to allocate the entire content of main memory to non-volatile memory. For this reason, it may experience intermittence anomalies. So we lend to this baseline the same versioning technique that Alfred uses to avoid intermittence anomalies. And here, overall, Alfred lowers the program energy consumption in all the benchmarks. However, there is very interesting results. So here, the baseline in the CRC benchmark is unable to complete the benchmark. And this is because the instructions within two state-saving operations consume more energy than the device can buffer. This means that the baseline is stuck re-executing the same portion of the program as it is unable to reach the next state-saving operation. However, this is not the case of Alfred, as it is able to lower the program energy consumption in such a way that is able to complete the benchmark. And this is thanks to his mapping, as in fact, in this case, the baseline and Alfred state-saving operations only save registers. And here, Alfred is able to map more than 90% of the memory accesses to volatile memory. And this is the and this produces the lowering of the energy consumption that grants Alfred to complete the benchmark. And finally, we consider a baseline that resembles the behavior of Ratchet, which is a forward progress technique that places the content of main memory to non-volatile memory and frequently save the state to avoid anomalies. This means that the computation intervals that Alfred considers contain very few instructions. And this limits Alfred mapping possibilities, as in fact is able to map up to 30% of the memory accesses to volatile memory. However, this is still sufficient to lower the overall program energy consumption, especially in the benchmarks where that executes at 16 megahertz. In fact, in this case, non-volatile memory accesses consumes more with respect to 8 megahertz, and as Alfred mappings is able to further lower the overall program energy consumption. So in conclusion, we argue that memory mapping significantly affects the overall program performance, and identifying the optimal trade-off, the most efficient trade-off between a reduced volatile state and an increased program energy consumption is non-trivial. So to address this problem, we designed Alfred, a virtual memory abstraction and compilation pipeline that automatically identifies the most efficient mapping of the program state across volatile and non-volatile memory. And then to evaluate Alfred performance, we implement it and we evaluate it. So this concludes my presentation. Thank you for your attention, and you can check Alfred at alfred.nestlab.it. I'm ready to take your questions.
Thank you for your talk. I struggle always a bit with the assumption that in a batteryless system, the source can go away extremely quickly and, in the order of milliseconds, and that it's, you're always going to have a power failure. I wanted to ask you if you agreed that at least for static deployments, right, when you would have a sensor node stuck in a wall somewhere, even if you have thermal, a TG, if you have a photovoltaic, even in the case of RF as you use, the environment is relatively stable, at least in the order of minutes, right? The light won't go off in the order of seconds, temperature won't change in the order of seconds. And so if the environment is stable enough, you could do away without the checkpointing, right? You can just go into sleep mode, have your data in low leakage volatile memory, and you can avoid all of the overheads that come from checkpointing. Would you agree with that assessment?
Partially. So the thing is that these devices are very tiny, very small. So usually the amount of energy that are able to harvest is not sufficient to sustain the computation. For example, with RF energy, you're able to harvest very few microwatts, if I remember correctly. And so like you're able to recharge your capacitor, but like you recharge your capacitor faster than like how you deplete the capacitor to use the energy to compute. So essentially what happens is that you recharge the capacitor slow and then you use it fast. And this creates the power failures because you're not able to refill the capacitor with energy sufficiently faster with respect to how much you consume energy. And yes, you can increase the capacitor dimension, but still, like if you're using like solar energy, yes, it's a stable energy source. But like there are cases, for example, the one that Luca talked in the keynote, where you do not have like sufficiently stable enough energy sources. For example, also with thermal energy in the SenSys paper of last year for the Mitreo deployment, the power failures were significant.
But sorry, just to clarify. So power failures. So I agree that it's easy to cause a power failure if you just try to consume way too much energy. But my point is simply that if you sleep enough and you're sure that your activation cycle is small enough, your system can stay energized, right? Because on average, your power consumption is going to be less than or equal to the input. So as long as there's this energy balance, it's possible to keep the system energized, right? Not actively consuming energy, but just energized.
So the problem is that like, even if you put the device into a deep sleep state, it still consumes energy a little bit. And so depending on the energy source, again, if you're using solar, yes, you're right. But if you're using like other energy sources, that is not the case because still like you're able, like also the deep sleep state consumes like nanowatts, nanojoules of energy, which is like still quite a lot with respect to the amount of energy.
So in your system, don't you have also deep sleep?
We use RF energy, and usually you have like power failures within 10 milliseconds.
But you use deep sleep, right? In between the power failures.
No, we don't use deep sleep.
You completely shut off.
No, we
isolate the voltage.
Go ahead with the execution, and when there is no energy left, the device just shut down.
Okay, but no, so maybe we can take this offline.
We can talk it.
If you completely isolate the voltage domain, right? If you cut it off, then it's going to be very inefficient to energize it again, right? And you lose a lot of energy by just completely disconnecting it with a relay, for example, and connecting it. So it seems to me as if you would also use the power sleep, but we can take it offline.
Yes, you're right. And we can talk it offline if you want, but like, yes, you're right. But like, you will still have like technically a power failure because you disconnect the system. So you still need some system support that is able like to decide that, oh, I completed the task or I completed the workload that I wanted to do. Now I need to shut down.
Mm-hmm.
So yes, in this scenario, the power failure per se is like controllable, but like you still need like the entire system design and system support, which is an interesting view on that. We can talk it about later if you want.
Okay, any other question?
Yeah, this is Farald at UC Berkeley. So this is not so much a question as a bit of an answer to the question about how to power just suddenly disappear. It's a very good one. And I think this is actually a vestige of where some of this work started more than a decade ago with the UW WISPs, which were computational RFIDs, where you literally had a very, very small capacitor and the RF ID reader could disappear. You could walk away, be out of range. I think it is worth re-examining a lot of these vestigial assumptions that lead to sometimes questionable design decisions and incredibly complicated power supplies, not necessarily here, but just in general, the area I think has gotten to a lot of complexity without a lot of clarity about the reasons why. And in fact, in many cases, I think looking across the layers of the system stack from hardware and hardware engineering all the way up through, programming and system support. I think a very good re-examination is in order now to explore how assumptions have changed throughout the stacks. I think it's a great question. I'm mostly just trying to give a little nuance to the history here.
Okay.
Use this or no.
Okay, let's start the third paper. The title of this paper is STEC, Exploiting the Spatial and Temporal Correlation for Event-Based Communication in the WSN. Let me introduce the speaker, the presenter of this paper. His name is Andreas. He is a third-year PhD student at the ETH Zurich, where he is focusing on the wireless sensing network and the new sensing concepts. If he is not in the lab, he is usually found discovering a new part of the Swiss Alps. Now let's begin. Yeah, thanks.
Okay, so thank you very much, and hello and welcome to this talk about STEC, a novel and event-based communication scheme for wireless sensor networks. In this talk, I would like to take you on a journey to the steep slope of the Swiss Alps. In this mountainous terrain, high above the valley floor, our group has deployed up to 32 seismic sensors in the last few years. These sensors are listening to signals from the underlying rock glaciers to detect ruptures, rockfalls, and landslides, which are caused by the heavy rain as well as the rising temperatures. The goal is that we can capture and detect significant events early on and alarm the population of the danger with sufficient time to react. However, the biggest problem we are facing is that the individual signals are not enough. We must look at the spatial and temporal correlation of the data in order to make sense of it. Only the co-detection of event by multiple sensors allows us to put the data into perspective. For example, this allows us to distinguish a strong event from a source further away and a close but insignificant one. In our scenario, we look at a single event, such as a major rock face which collapses, whose signal then propagates to multiple sensors in a radial pattern. When sufficient sensors are triggered, a large event has been detected. The exact definition of such a relevant event, on the other hand, depends on the actual application at hand. If it seems interesting, the event should be reported to a data sink to induce further actions. On the other hand, small events, which only affect a subset of the network, can easily be discarded. And lastly, sensor nodes which receive no trigger at all should remain inactive. To report the co-detection of multiple sensor nodes efficiently and quickly to the data sink, we must therefore answer a fundamental question of communication: when to send what? And while it might seem simple at first, these two questions can be answered in a myriad of ways. So let's start analyzing the problem and some reasons why this might be harder than it at first seems. Unfortunately, the common solution of periodic messages means that sensors need to wait for the next meeting point in order to exchange data. On the other hand, if sensors just send data in an uncoordinated way, messages frequently collide for large events which trigger a large amount of sensors. And the question doesn't end there. What we should send is just as important. While the fact that uninvolved sensors should remain inactive and not communicate at all is highly intuitive, it is, however, not the case for most of today's wireless networks, which frequently exchange packets just to keep synchronized. And finally, because we do not only have short-range communication, but must reach a data sink far away, the limited bandwidth of long-range modulations restricts our capability to send the data home. So what do we do? To solve these issues, we propose to treat the event as a medium which can be exploited instead of just treating it as a producer of data. By leveraging the signal correlation in both the spatial as well as the temporal domain, our problems can be simplified. For example, in stark contrast to periodic communication protocols, we base our design on a scheme which is entirely event-driven, by the sensor nodes locally originating from a major source at the same point in time. When sufficient sensors in the vicinity are triggered by this event, the sensor nodes should exchange and analyze the event locally through short-range links. As the propagation times of events is naturally restricted, and therefore nodes only wake up within a very restricted time span, we can use this to directly and inherently filter out uncorrelated sensor data. Only if the event is deemed relevant, it is reported to over the long-range link to a data sink, which can then forward the event. Because the data has been shared over the local ad hoc network first, we can already compress it there and only actually spend the high energy cost of the long-range links for the data that is relevant at the data sink. However, it is key that we focus our limited resources through local filtering. This means that we avoid wasting excessive energy on the very frequent but uninteresting cases where only a few sensors actually receive a trigger as the event is of a small scale. Similarly, sensor nodes which did not observe anything at all will not take part in the communication. While this idea might seem intuitive, making it work in practice forced us to solve 4 major problems in STEC to achieve high energy efficiency at low detection latencies. First, we must improve the core synchronization we get through the sensor triggers so that it is sufficiently precise for efficient communication. Then, we must be able to bootstrap a local network with an unknown subset of sensor nodes. Third, the ensuing communication should be swift and reliable so that a decision can be made within seconds. And lastly, we need to find a way to communicate this local decision to a data sink far away. So let's start. We start with the nodes waking up together after a sensor trigger has been received. The complication regarding the accuracy of the sensor triggers is that the signal generated by the event propagates over variant different distances and generates differences up to 100 milliseconds. To improve this using radio signals and enable efficient communication, we introduce DiscoSync to discover and further synchronize nodes. For this method, after a trigger has been received, we have each node listen on the channel for transmissions of other nodes for up to the maximal propagation distance to include all relevant sensor nodes. If no packet has been received, this sensor node is the first one to have received the event and notifies its surrounding that it is activated by sending a series of packets. If it does not hear any replies, DiscoSyncs can quickly detect a lone wake up and therefore terminate the processing of the current event. However, for a larger event, multiple sensors are active and follow a unique transmit-receive pattern based on their individual IDs. This procedure ensures that nodes discover each other with a higher probability, even over multiple hops, and synchronize to each other's transmissions early on, reducing the maximum timing inaccuracy to single milliseconds. To further ensure that all nodes share a precise time reference, we then continue with a local lead reelection. This phase consists of multiple rounds depending on the number of nodes in the network. A node only transmits a flood of packets in the current round if it is bit at the corresponding position in the ID is set. That means the first bit in the first round, the second bit in the second round, etc. If it ever observes traffic during a round where its bit is not set, it backs off from the election and continues until only a single node is elected as leader. STEC then leverages the tight time synchronization resulting from the previous phases to instantly construct a network. In order to be able to communicate in a multi-hop network whose properties are largely unknown, we leverage the concept of synchronous transmissions and concurrently flood packets to form a connected network. As synchronous transmissions have a single initiator, which starts a flood, which then concurrently propagates to all active nodes in subsequent steps, it is inherently topology agnostic. What we need, however, is tight time synchronization, as well as a schedule which is distributed by the leader. As the number of nodes is not known at the start of the round, we achieve deterministic performance by simply scheduling one opportunity to exchange data per node. Because these floods are highly reliable and broadcasted, all nodes actually receive the event, which are active. Each node then possesses the complete set of information and can process the data locally and independently. The filtering can be based on various application-specific criteria. In this presentation, we focus on the reporting threshold. This means that we define an event as significant if at least a fixed number of nodes have received it. If this threshold is not reached, the event can be dropped and all nodes return to sleep. However, if the event is deemed relevant, we must report it to a data sink. In order to avoid that multiple nodes invest the high cost to transmit the data, the leader has already assigned a reporter ID in the previous schedule. By having the active node whose ID is closest to this one transmit the data, we can guarantee that at least one node will report. Furthermore, by choosing the reporter ID uniformly at random, this particular solution prevents depleting a single node excessively and distributes costs evenly. So far, we've been only using short-range local links for energy-efficient and quick communication. However, we are not able to use a multi-hop network any further because connectivity is not necessarily guaranteed, as only a subset of the nodes are actually active and the data sync too far away. Therefore, we leverage the capability of modern radios, which provide both short as well as long-range modulation in a single chipset to directly transmit the data. To evaluate whether our stack protocol truly manages to report co-detections quickly at a low energy cost, we compare it with two previous wireless protocols. ELWB is among the state-of-the-art synchronous protocols and periodically floods the entire network to exchange data. Aloha, on the other hand, represents an event-based protocol, which does not rely on local networking and serves as a reference for purely long-range communication directly to the data sync. To compare, we simulate each protocol based on a real-world data set we gathered with 32 sensors at one of our deployment sites in the south of Switzerland, close to Zermatt. While it contains multiple tens of thousands of events, notice that they are highly unevenly distributed, with some nodes only receiving a few dozen triggers throughout the 1.5 years of the deployment. First, let's look at the energy efficiency of the three protocols. What you see here is the energy spent per event, where we plot all the 32 nodes individually in the network. Notice that the y-axis is logarithmic. As an example, node 4 has a blue bar for the energy stack requires to transmit and report, as well as a red bar for ELWB and a yellow bar for Aloha. We find that at 52 millijoules, stack allows us to significantly reduce the energy consumption compared to Aloha by a factor of almost 6, as well as to ELWB by a factor of almost 60. How do we do this? Well, this is partly based on DiscoSync's ability to quickly detect lone wake-ups and terminate the protocol early on for the vast majority of cases which only trigger a single sensor. Because ELWB schedules periodic communication, the overhead cost for nodes which only receive data every week or even less often is enormous. This can be seen by the high red bars in the figure. On the other hand, asynchronous communication directly to the data sync is inefficient as no events can be locally filtered, as shown by the yellow bars, which are equal for all nodes but significantly higher than the blue bars. We just saw that the periodic scheduling of ELWB causes high energy costs with only limited benefits. To further investigate whether synchronous communication with a larger period in between, we look at ELWB in more detail. In addition to the protocol with a period by default of 15 seconds, we also add variants with a period of 1 minute, 5 minutes, or even a quarter of an hour in between schedules. What we see here is the energy cost of the protocol variants depending on how often events actually occur. As it is per event, less frequent events means that the scheduling overhead is distributed over fewer events and therefore increases from the left to the right. We find that small events already profit from stack if they occur less than every 46 seconds. For larger events, which only happen very rarely, only event intervals below 8 hours can be more efficiently reported with ELWB. Next, we investigate the reporting latency per event. Again, we show the performance of each protocol for each of the 32 nodes. By only a bit more than 3 seconds, stack can give you early warnings with much lower latency than ELWB, with a median of almost 15 seconds and Aloha by a median of almost half a minute. This follows as stack does not have to wait for the next scheduling or communication opportunity, but can immediately communicate as soon as a trigger arises. Aloha does so as well, but it is asynchronous and directly using the long-range modulation, which results in much more frequent channel contention, as events often occur in bursts. To see how we can tune stack and its filtering, we investigate the dependency of the protocols on the reporting threshold, that is, the number of nodes required for it to be reported. So far, this threshold has been fixed at 2 sensor nodes per event. We first look at the energy per event of all 3 protocols, where we plot the worst case node in the network with a dashed line. Stack can use the increased filtering demands of a higher threshold to locally terminate earlier and thereby increase its energy efficiency. Because the LoA cannot filter locally, and because the scheduling overhead of ELWB throughout the deployment vastly outweighs the communication costs we actually send to transmit data, the other protocols cannot leverage this. For the reporting latency, we find that because more data needs to be transmitted, the detection latency slightly increases from the left to the right, but remains stable overall for Stack. To see Stack in action, we have deployed 9 of our sensors close to construction sites for 4 months. In parallel to the wireless network, we also log all events locally to an SD card and use it as ground truth. In this case, each co-detection represents a strong tremor from a construction machine, which triggered multiple sensors simultaneously. We find that Stack can correctly identify co-detections, and furthermore, our implementation matches the results we would expect from the simulations based on the ground truth. As with the previous deployment, we find that co-detections are actually rare, which cover only about 7.6% of all cases. To also test Stack on the more realistic conditions, we wanted to investigate the influence which rain has on the kinematics of active rock glaciers. What you see here is the rain intensity at our deployment site in the mountains, where we also gathered our previous data set for this experiment from November last year to the end of May this year. With a deployment of 9 nodes running Stack for 7 months, we find that the number of co-detections strongly correlates with previous rainfall. With this experiment, we can show that Stack works as intended and provides the necessary information to detect natural hazards in time to react. To sum it all up, Stack leverages the spatial and temporal correlation of sensor signals to increase the efficiency and reduce the detection latencies in wireless sensor networks. We first synchronize based on our received sensor triggers, then create a local ad hoc network in multiple phases in which we exchange and filter data, and lastly, using the same radio, report significant events to a data sync to induce further actions. We hope that Stack also caught your interest and inspired you to think differently about the symbiosis of sensing and communication in wireless sensing networks. If you would like to see our protocol in action, please visit our website where we have open sourced all scripts and hardware. Thank you very much for your attention.
Any questions?
Hi, thank you. Very good. Nice, difficult, challenging work in the mountains, I imagine. So I think what I would ask is your assumptions that the signal you detect at each node individually is an event. So the question is, what about events that perhaps are weak, but could have been detected by, say, 3 or 4 sensors working together? So you miss those because they won't cross the individual threshold for each sensor node. So what can you say about how this impacts your measuring paradigm, what you can actually do? You can detect strong events with this system, but you will miss weak events.
Thank you very much for the question. That's a very good question. The key, so there's 2 answers to this. One is that it really depends on your actual application. So you need to set the trigger thresholds correctly. We set them rather low in this experiment just to see whether it actually works. But of course, if you would like to usually only see major events, then you need to adapt. Secondly, so as you can see, we deployed them in an area where we really want to only detect major rockfalls. Like there's lots and lots of small events. Like you have small stones falling. We have ibexes up there, which actually sometimes eat our sensors. And so there's lots of things that can occur. And so you don't want to have the threshold too low necessarily in this particular environment. What is interesting though is that usually such an event where something breaks off is not just happening from one moment to the next. So you see an increasing pattern of these things occurring before it actually starts to have a major landslide, for example. And so this helps you that even if there's a single event that you might have missed because you set the threshold not perfectly, usually it's really about this longer term patterns. And of course, if there's a really strong event, like something really breaking off, then you will detect this.
Okay, great. Thank you very much.
Any other question? Oh, okay, okay. Let me ask a question. Yeah, very good work. Could you just give me some examples of the event?
You mean whether I'm sorry, I didn't quite understand whether I could give an example of an event?
Yeah. Just give me some example of the event. What kind of event can be just use your method? All kind of event.
So here we focus really on seismic events. And what we have is a sensor which detects vibrations in the ground. And as you can see, for example, we have these nodes which are on a rock, which is actually a part of an entire series of rocks, which is in very much danger of breaking off. And so an event here would be if multiple of these rocks start to slide down, they endanger the population which is in the valley, because we're here at 2,500 meters above sea level, and 1,000 meters further below, there's an entire village and drains and streets. And so we want to detect these things from breaking off.
Okay.
In general, you could also use this technique, however, for various kinds of applications. For example, we also envision that you could use something like a smoke detector, which is usually not having any events for years and years, and therefore should not constantly communicate just for nothing. And then you could detect something that, for example, somebody's smoking, so you only want to, if only a single sensor is actually activated, you want to prevent this from sending an alert. But if multiple sensors send something at the same time, then you know, okay, this is actually something we need to react to.
Oh, okay, yeah, quite useful. Yeah, thanks so much. Yeah, this is the end of this session, and wish you enjoy the conference of the SenSys. Thanks. Goodbye.
Would you like mine? Would you like mine?
Hey, I see some of this presenting authors are already here. You want to respond to me? Ryan, are you there?
Yes, I'm here.
Oh yeah. So you see the Slack, right? So I asked according to what you suggested. We shall start 10 minutes later. Would that be okay?
Yes, I think that should be fine.
Okay, sounds great. Sounds great. Yeah, it's really got delayed. So the other one, Zhiyuan, you're here, right?
Oh, yeah, I'm here.
So, well, since we are anyway free, so do you want to? I don't know if they will allow us. Do you want to test your slides? Just in case.
Well,
Yeah, you can do now. So our helper has already disabled the on-site slide, so you can try.
yeah,
Do you mind if I actually test mine first?
Yeah,
I quickly test mine.
Oh, you are the one who is. Okay, sure.
Yeah, I just want to make sure that it works
Sure,
because
why
this
not?
setup
You're
is a
the
little bit
first, yeah.
complex.
Yeah, you go ahead. You go ahead. Shrem, you go ahead. I thought you went for the coffee.
How can I not see the
Yeah, looks nice.
This is good?
Yeah, looks perfect.
Okay, great. Thank you so much.
Yep. Thank you. Okay, so Zhiyuan, your turn.
okay, sorry. Let me share my screen.
Okay, can you see my screen?
Yes, yes, yes.
Okay, I think then it's fine.
Yeah,
Okay.
looks good, looks good. Okay,
Okay, thank you.
thank you. So I see Hanting is also here.
Yeah.
Yeah, do you want to start trying your slides? Because we have a bit time here. By the way, Hanting, you have just arrived. We decided to put a 10 minutes delay because previous sessions got seriously delayed. Wow, that's a fancy slide. Yeah, this looks fine. Okay. Oh, so we got at least 2 on-site authors, right? So Hanting and Sriram, you are both on-site.
Well, I'm online.
Yeah, Sriram, you are online. No, yeah, we are from Asia. So
Yeah.
they are. I mean, Sriram is also from Singapore, but he is very great.
Okay.
Yeah.
Yeah, it's nice to be here.
Yeah, I envy you a lot.
Yeah, it's a long flight, but yeah, I think it's worth it at the end of the day.
Right.
Okay,
So
I'm just
how
gonna.
was the trip? I mean, because it's during COVID period, is it got a bit nervous during the long trip?
Yeah, I think it's okay. I mean, everyone who's been on the flight has taken a test and everything, and they're vaccinated. So I think I'm not super concerned. But yeah.
Maybe I should have, pay a trip. But anyway, yeah.
Okay, sorry. Give me a minute. I'll just be back.
Sure. Yeah. Take some coffee. All right. So yeah, I know you can't do this. Oh, you can do the sharing now.
Okay, I can show. Am I presenting the first one?
No. It's just
Oh.
you get a chance to test your slides. Otherwise, later, if there's anything wrong, I mean,
Okay.
it could delay our session.
Oh yeah, does anyone else want to test their slides before I start?
Yeah, sure. Just give the last presenting author a little bit time.
Sure, no problem.
You can do the sharing now. Oh my God.
Okay, I can.
Really? A very long delay. No. It's just you get a chance to test your slides. Otherwise, later, if there's anything wrong, I mean, it could delay our session.
Yeah, can you see the slides?
Anyone else want to test your slides before I start? Yep. Yeah, it looks nice. Just give,
Okay. Yeah, I think it's good.
No, it's okay.
No problem. Okay.
Oh my God. Okay. Really? Very long delay. No.
Interesting. I think the YouTube feed is somehow feeding back into the Zoom feed.
Yeah. I don't know because I have to open both. So maybe there was a cycle somewhere here.
I think once you mute your side, it will probably go away. I think it's just feeding back from that. I don't know how, but yeah. It's okay.
Let me. Yeah, it's fine.
Okay, should we wait for anything else, or I guess we can also start if everyone is okay.
Okay. I just see there are only just a few audience there, so if you wish, I can get us started.
I'm okay to wait a bit, but yeah, I don't know how long they'll take.
Yeah. Well, do you have anyone to go out and urge others a bit to have them back, or
I don't think we have anyone to do that now, but it's okay.
Okay. So then, yeah, let's get started. Welcome everyone. So this is our last technical session for SenSys. And so the topic here, what we're discussing here is about light-based sensing and communication. So the first presenting author is Shuyan. is a PhD candidate at National University of Singapore. He is interested in discovering novel user cases for everyday sensing devices. His current research focuses on active sensing systems such as LiDARs and time-of-flight sensors, and the security and privacy implications. So, Shiran, you can go.
Great. Just 1 second. Okay, looks good.
Yeah, go ahead, please.
All right, thank you. Just move one last thing. All right, so hello everyone. I'm Sriram from the National University of Singapore. It's been a long flight, but I'm happy to be here and thank you for coming as well. And on behalf of my co-authors, I'm presenting our work called LEPD, Hidden Spy Camera Detection using Smartphone Time-of-Flight Sensors.
Oh, sorry. Oh, yeah,
Yes.
yeah. Now it's working. Sorry, there was a bit delay. I just see the slides coming up on the YouTube. So go ahead. Sorry.
Oh, I think YouTube might have a bit of a lag, but it should be fine.
Yeah.
All right, thank you. Okay, so imagine that I show you a few everyday objects. So a water bottle, a smartwatch, and a Wi-Fi router. So what if I told you that each one of them is hiding a tiny spy camera? Can you find them? If you haven't already, try now. I'll give you a few seconds. Okay, for time that should be enough. So let's see how you did. The water bottle has a tiny spy camera inside the label. The smartwatch has one hidden under the screen. And even if I told you that the router has a hidden camera, can you possibly guess that it's inside that hole? Probably not. I guess you can start to see the complexity of this problem. And what makes this worse is that, well, both the water bottle and the smartwatch can be purchased online for less than $30. In fact, the water bottle is only $15. And if you're still cheap like me, I'm super cheap, right? Actually, we built the Wi-Fi router with the camera by just installing a $1 hidden camera module, and that was it. So this is pretty scary. And this also makes hidden cameras a worldwide problem. And what we see is that there are news articles in South Korea, in China, in US, and in India. It doesn't really matter because wherever you look, it seems that there are hidden cameras everywhere. So we can make two observations now. One is that it's really easy to covertly hide a hidden camera in an object of your choice. And secondly, that in any real world environment with maybe hundreds of objects, they're extremely difficult to find. So there is a power imbalance here fundamentally that favors the attacker and puts us, basically the public, at risk. We are essentially on the back foot. So we can say that hidden cameras are basically not only a dangerous threat, but also an asymmetric one as well. So how do we fight back? Fundamentally, one option we have is purchasing a hidden camera detector, which looks like this. So it has a viewfinder you can look through, and it also has some red LEDs at the back that illuminate the scene. Now, here's an example of the South Korean police trying to use this hidden camera detector to find cameras. You can kind of already see, firstly, that this is a manual process, and also from the poor man squatting on the ground, extremely laborious. Right? This is not fun, as you can see. So what exactly are these people seeing through the detector? Now, imagine you see something like this with your naked eye. If you're in person, you can see the object in front as well. Now, what you'll see through the detector looking at this is something like this. The hidden camera is actually in the top right-hand corner of this plug. But if you look through the hidden camera detector, there's an unnaturally bright reflection where there's supposed to be nothing. Now, that's a really interesting point. And now we should really ask ourselves, well, what makes hidden cameras reflect so brightly compared to the surroundings? We can take an example here of two objects, one without a hidden camera and one with. If we shine incoming light at both of these objects, the object without the hidden camera does something called diffuse reflection, or basically weakly reflecting in all directions. And the object with the hidden camera reflects the light back very strongly in the direction of the source, which is called retroreflection. So looking sort of closer at the hidden camera, we can see this as a combination of an image sensor and a lens that focuses light onto that sensor. So when we shine incoming light, what happens with this geometric configuration of lens and sensor is that all light goes back to the source, almost all light, very strongly. And this is called here lens sensor retroreflection. If this analogy is too abstract, you can think of a concrete example as cat eyes. I'm sure everyone is familiar with cat pics everywhere. If you shine a bright light on a cat's eyes, the geometry of the eyes will shine a lot of the light back to you, and they're much, much brighter than the surroundings. This is the exact effect that happens in hidden cameras as well. So now we should talk about the elephant in the room, in case you haven't seen it yet. The issue here is that there are many, many other reflections that are also bright in the hidden camera detector's view that aren't the hidden camera itself. So more specifically, we can talk about some of these drawbacks, including many, many false positives with this hidden camera detector, and also multiple usability concerns, including the fact that this is a manual process. There is no automation. You have to decide yourself. So this is a lot of subjective judgment. There's also a specialized device that you have to carry with you at all times. You become that one-use hidden camera guy or girl that has that in your pocket, and that is incredibly infeasible to have this one detector with you. And lastly, I'm sure that somebody who tried yesterday can also find that there's a lot of eye strain with this device. If you hold it to your eye for maybe 20, 30 seconds, it gets really tiring as well. So there are multiple issues with this hidden camera detector that we can purchase on the market. So we asked this question, whether we can automatically and accurately locate hidden cameras using only everyday equipment that we have on us at all times. So let me paint a picture. What if I wanted to suspect that something has a hidden camera, I could just take out my smartphone and it would tell me that there's a hidden camera in that region. In fact, this is exactly what we do, called LAPD, or laser assisted photography detection, which is a means to automatically locate hidden cameras using laser time of flight sensors on smartphones. So how this works is that LAPD illuminates the region with this time of flight sensors laser output, and any hidden cameras in the region will return a uniquely bright reflection. We will analyze this reflection and indicate it on the screen. That's the fundamental idea behind LAPD. Now, I've skipped over something, which is, well, what is a smartphone time of flight sensor? Now, the idea behind this is something that's increasingly common in modern smartphones like the Samsung S20 Plus, iPhone 12 Pro, even 13 Pro recently as well. And the point of this sensor is to get depth information. So how far away objects in the scene are. Well, this is really useful for stuff like augmented reality, like games, or even utilities like planning where furniture goes in your house. So augmented reality primarily. And the idea here is that we measure distances from the camera to nearby objects using laser travel time, either directly or indirectly. And as an example of how this looks, if you have this image of, let's say, a water bottle, now what a time of flight sensor sees when it looks at this image is something like this, right? Where a darker region in this image refers to something that's closer. So it really is a depth image. And the two can be combined to produce something like a three-dimensional image. That is the fundamental conceit of what a time of flight sensor is. So what are our insights? What do we gain from this, looking into time of flight sensors? Now, firstly, something really interesting is that if we look deeper into the APIs of the sensors, not only do they give you depth information, so how far away things are, they will also tell you how bright each pixel in the image is, how bright the reflection was, right? Now, we'll talk a little bit more how limited that is, but it will give you some information like the image on the right. So what this means is that we can find regions that are unnaturally highly reflective. Specifically here, these are black regions in the image, so connected black pixels. Unfortunately, I think you can tell that this is not a straightforward problem yet, because only one of these reflections refers to a hidden camera, while the other reflections are false positives. And this brings us to some of the numerous challenges that LAPD is facing. So these are some of the challenges that we are facing. Firstly, every object has a varying reflectivity, which causes a number of problems. Secondly, there are multiple hardware limitations with this sort of lousy TOF sensor. I say lousy, of course, in our application, but not in general. And lastly, every hidden camera also has a limited field of view, and we cannot see the camera outside this region. So let's look a little bit more at these challenges. Now, what I mean by varying reflectivity is that, once again, we cannot stand too close or too far from any object we want to scan. Why? So imagine, once again, this water bottle as a reference, and imagine we stand at multiple different distances from this bottle. Now, if we're too close to the bottle, what we see is that the sensor is saturated, too much light returns back to the sensor, and any hidden camera is completely obscured. If you're at the right distance, or what we call the ideal distance from this object, the hidden camera here appears in green as a small region of connected pixels, and it's easily visible at this range. Unfortunately, if we go too far, not enough light comes back to the sensor, and once again, we just don't see the camera. So there are lots of false negatives that come into play if you're not at the right distance from each of these objects. That's our first problem. Now, the second issue is that the time of flight sensors that we have now have extremely limited spatial resolution. What I mean by that is that they have almost a 320 by 240 sort of measly resolution image. This is what we get at all times. A good analogy, of course, if you're not familiar, is that given an image that looks like this, lower resolution will give you an extremely blurry picture with very few details. This means that a hidden camera actually is only represented by 1 or 2 pixels at the end of the day. So really, really few pixels. Now, this problem is additionally compounded by the fact that every single pixel in this image only has 3 bits representing it, or only 8 colors. Once again, analogously, an image like this will seem like a very sort of lousy grayscale image with very few layers to it. So these 2 issues compound to create a number of false positives where we need to filter out spurious reflections to find the real hidden camera as well. And lastly, for a challenge, hidden camera reflections, because of some fundamental physics, are only visible within a 20-degree field of view. And basically, if you're outside that field of view, you just will not find the hidden camera. It will not be visible to you. And this is, once again, a fundamental physics limitation. So given these challenges, how do we address them? So that's the point of LAPD system design, where we have 4 phases to identify hidden cameras. So firstly, we select the hidden camera object on the screen. This is a smartphone app. Secondly, the app will guide you through a series of steps to find the ideal distance. Thirdly, the app will guide you through a series of sort of a scan, I guess a scan pattern to look at multiple places in the object. And lastly, you'll be told whether that object has a hidden camera or not, and exactly where it is on that object as well. So let's zoom into the third phase where a lot of the work happens. So each frame from the time of flight sensor gives us a laser intensity image and also a depth image as well. We combine this in one big stage to basically filter out a number of false positives. So imagine, for example, we actually see the hidden camera and a number of false positives. We don't know this yet. The point of this phase is to use both physics-based, so sort of physics knowledge, and also machine learning filters to remove all of the false positives in this step. Then any remaining reflections that pass this stage are passed to a 3D coordinate conversion system. And finally, we pass it through one last filter that checks for the field of view of the camera and whether this makes sense, whether it checks out. And finally, if everything works, we will indicate whether a hidden camera is present or not. This is the overall design of LAPD. So I can only mention 2 of these sort of phases for time, but I'll just quickly go through them. Firstly, how the scan distance computation phase happens. How do we find the right distance to scan from an object? So basically, the intuition here is that any tiny hidden camera, we define these as 1 to 2 millimeters, which is very common. This will only generate reflections that are smaller than, let's say, some p number of pixels, right? So anything that's larger than this cannot be a hidden camera. There is no way, right? And this p is basically an empirically determined value based on the resolution of the time of flight sensor and also how large we assume the cameras are. So we have this sort of threshold p. Now, what we do then is we ask every user to stand within 20 centimeters of the object to saturate the whole sensor, and we ask them to slowly move backwards. What happens over time is that you get to a point where all reflections in the scene are smaller, or at least as small as a hidden camera can be, and that's considered the ideal distance. So for those of you who like graphs, of course, the idea is that the further you get away from the object, the smaller the largest reflection becomes, and at some point it's lower than the threshold that we know for a hidden camera, and that becomes the ideal distance. So that's how we figure out where to stand for each object. Now, second phase we'll go through is how we remove a vast number of false positives, because there are many. There can be hundreds per frame. So how do we do that? So once again, we take the laser intensity image. This is the baseline here. And we extract all of the high intensity regions, so connected black pixels. And what we do now is that we feed this to a series of shape and distance filters, as we call them. So I'm going to present only a subset, but one of them, for example, is whether the reflection is too large. Another also uses the knowledge that all lenses are essentially circular because of manufacturing reasons on a lathe. So it tends to be that any reflection is circular. So anything that's square or rectangular cannot be a hidden camera as well, and that's also removed. So the number of other things we do here as well, but basically all of the difficult cases, the really difficult ones, are passed to a deep learning filter. And this is trained over our own self-collected data set, but this is basically a convolutional neural network that runs in real time to remove a vast number of false positives as well, integrating multimodal information from both depth and intensity. And finally, this outputs the reflections that are candidate hidden cameras, and everything else is removed. Now, of course, here I'm really simplifying because there's a lot of information that we fuse across frames and across 3D space, but you can refer to our full paper for more details. So now that we know how LAPD works, let's talk about how we evaluated its performance. So LAPD's hidden camera detection performance is tested against 30 different objects that LAPD has not been trained on before. I repeat again, we have not trained on any of these objects. 21 of these test objects do not contain hidden cameras, and 9 of them do. So across both of these classes also, we were a little bit mean to ourselves. We basically had a bunch of objects that were highly similar across both classes to make our task even more difficult. And here again, like I mentioned, we have a totally separate training set of 10 objects that we designed ourselves as well, and also things that we bought off the shelf. So for each object, we have a total of 3 detection methods that we're testing, both LEPD itself on a Samsung S20 Plus, but also 2 baselines. One is a hidden camera detector, and the other one is just using the naked eye. So LEPD is tested fully end-to-end as an Android app. So we really did run these experiments on a real environment. But for COVID reasons, we test the other 2 methods using Amazon Mechanical Turk. So we record a bunch of videos that are very fair to the participants, and their job is basically to observe them and annotate on an image where the hidden cameras are. We explain in the paper how we make this as fair and in fact biased towards the participants as well. Okay, so we now summarize the results of LEPD's comprehensive evaluation. So LEPD has the highest hidden camera detection rate at 89%, and also the lowest false positive rate of 17%. Also, it accurately determines the correct scan distance for all 30 objects we tested on. That's never seen before. And also it generalizes across multiple lighting conditions and also the different smartphones that we tested. We tested 3 different smartphones. And lastly, it also can operate continually for 2.5 hours on a Samsung S20 Plus, even regarding the fact that it's running augmented reality, machine learning in real time, and all these other things. And also the TOF sensor is running continuously, and this is still true. So in the interest of time, again, we'll only present the first result, the main idea, and let's talk about that now. So once again, the main result from our experiments is that LEPD is outperforming both of the baselines in terms of how many hidden cameras it detects and how few false positives it generates. So recall again that we test this on 30 different objects, and the results are here in this graph, where green bars refer to hidden camera detection rates, and the red bars are false positive rates. So on the x-axis, on the y-axis, we have the percentage of each metric, and on the x-axis, we have on the leftmost LEPD itself, 88.9% hidden camera detection rate and 16.7% false positive rate. And then we have the detector itself in 2 of its modes, which once again, for both of its modes, blinking and continuous LED performs worse. And finally, for just using a naked eye, it performs worst of all. So we outperform all of these methods with LEPD. So given this performance, now we can consider how else we can deploy and extend LEPD in the future. The first thing and the most important thing is that hotels are a massive hotspot for hidden cameras. Now, what we can do instead of manually inspecting everything is that we could just put time-of-flight sensors on cleaning robots, which are becoming increasingly more common in hotels. And these could just automatically scan for hidden cameras through their daily cleaning routine. The other thing we could do is we could also use the smartphone's flashlight as an additional modality to find hidden cameras. And we know this will be really effective because we tried it ourselves a little bit manually, but unfortunately, because of API limitations, we can't do this right now. But if we can do this, and when we can do this, this will be incredibly effective. Lastly, let's talk about a couple of limitations for LEPD. Now, firstly, of course, it's clear that that TOF sensors are not completely ubiquitous yet. So they're on higher end smartphones for now, but they're also penetrating into the space into mid-range smartphones over time. So we expect that this will be better over time. Secondly, also, we use a lot of augmented reality libraries that are external to LEPD for localization. And while this is something we rely on, we expect also this accuracy will improve over time since there's lots of active research in this space. And lastly, LEPD right now requires you to select each object one by one to scan them because the sensor is not that great, so it doesn't have much dynamic range. So we expect this to once again get better as we have better and better sensors with larger and larger bits per pixel and so on and so forth. So we expect this once again to get better with time. What we have right now for LEPD is kind of where we are right now with a proof of concept time-of-flight sensor on commodity smartphones. So in conclusion, LEPD is a system that uses time-of-flight sensors on smartphones to automatically find hidden cameras. And our hope is basically for the census community as a whole is maybe we can look at more interesting uses of commodity time-of-flight sensors. Maybe we can find other similar or completely different use cases that can use time-of-flight sensors in novel means. All right, so thank you very much. You can find a full paper here and any questions. Thank you.
Yeah, thank you, Shreya. It's a very exciting presentation. So I will let you take care of the on-site question first.
Sorry.
Thanks for your presentation. It's really a nice work. And here I want to, I only have one concern. That's how do we consider the ambient light interference issue? In here, you take a bottle as an example, but in reality, maybe the spy camera will maybe fixed at other places like the wall and the ceiling, and these places are near to the strong light source like the TV or the ceiling light. So how do we consider to cancel this ambient light interference? Yeah.
Yes, that's an excellent question about like, so you're talking
Yeah.
You're talking about external light sources, like, for example, like ceiling lights or the TV
Or
itself.
TV light.
Right. The good news is that time of flight sensors operate in a very narrow frequency range. So they're only at 850 nanometers. So any light source that firstly isn't within 850 nanometers just isn't going to matter. The second thing is that they're even more robust than we expect. So even if you take two smartphones, both with time of flight sensors, and you put them back to back and you shine them in each other, they actually don't interfere between themselves. So in fact, this is a really robust system of detecting laser light that is almost key to the smartphone itself. So generally speaking, and we tested this as well, background lighting is not a concern. We tested in sunlight, in bright indoor lighting as well as dim lighting, and there's almost no difference at all between all these situations. So we don't expect background light to be a problem. But yes, thank you for your question.
Thanks. Got it.
Well, is that no on-site question anymore? So if no on-site question, I look at the YouTube and both YouTube and Slack. I'll get one. So Yuan Qingzheng from Hong Kong, he is asking, how long does it take for an ordinary user to completely check a hotel room? That's the first question. And second is, did you test with volunteers with their naked eyes in real world scenarios?
Right, thank you. Great question. Sorry, two questions. One about how long it takes to scan a room, and the other one about volunteers. Okay.
Right.
So when it comes to scanning, basically scanning room, depending on the number of objects that are there, will take some time. Of course, per object, we expect that to take about 30 seconds to scan. So each object will take about 30 seconds to scan. So you need to look at how many objects there are in the room because you're selecting object by object. But I do want to stress the fact that this should be compared to the current state of the art, which is this hidden camera detector that I'm holding. This is also the same idea where you turn it on and you manually sort of go object by object as well. So in general, it will take about 30 seconds per object. And I guess for a room, maybe you can estimate that to take something like maybe 5-10 minutes. Yes. So that's the first question. For the second one, do we use volunteers to test for the naked eye and the detector? So while they weren't in the room physically using the detector and naked eye, because of COVID reasons, we couldn't get all the participants on site. What we did was that we basically recorded a series of videos where we did these scans ourselves very fairly as well. In fact, the paper states that for all of the hidden camera usages, we actually ensure that at least the reflection from a hidden camera is visible in the video. And we put all those videos on basically Amazon Mechanical Turk, and basically all these participants sort of looked at these videos and then decided where on the image the hidden camera was. So they weren't there physically in the room. We basically, as a proxy, we recorded a large number of videos very fairly as well, and we asked them to annotate where the hidden cameras were. So I hope that answers both of those questions.
Right. So I actually got one question from myself.
Yes.
So suppose I'm a hacker. So does it make sense that I just hide my camera behind a mirror? Would that thwart your mechanism?
Right. That's a really interesting question. Actually, so this actually comes out quite often about mirrors and one-way mirrors. So generally, if you have a mirror, what happens is that actually, let me answer your question quickly first. So if it's behind a mirror, should we be able to detect it? I think we will still be able to detect it for a couple of reasons. Firstly is that you still need to expose the lens of the hidden camera. So somehow you have to find a way to insert it into a mirror that still exposes the lens without somehow breaking the glass. But in general, even if you did that, a mirror generally has a very large reflections that are easily filtered out. So the actual hidden camera reflection is generally visible as well. So I don't think mirrors would necessarily pose a direct challenge, but also we didn't test this explicitly, so we don't know for sure, but we did test against multiple kinds of reflective objects. Yes. So
okay, thanks. We got some more questions from YouTube, but maybe because of the time limit, I'll just put them into Slack and let you do it offline. How about that?
Sure, no problem.
Okay.
All right,
okay,
thank you, everyone. Thank you for listening.
Thank you. So let's switch to the second presenter. When Zhiyuan is putting on his slides, let me just introduce him. Zhiyuan Xie is currently a PhD candidate in the Department of Information Engineering, the Chinese University of Hong Kong. He received his BS bachelor degree from Peking University in 2019, and his research interests include smart health system, mobile computing, and Internet of Things. Right, so Zhiyuan, it's your turn.
Okay, thank you. Thank you so much for the introduction. Can you see the screen?
Yeah, go ahead.
Okay. Hi, everyone. Welcome to my SenSys presentation, Ultra Depths, exposing high resolution texture from 2F depth cameras. And I'm Zhiyuan Xie. This is a joint work with my co-authors, Xiaomi Ouyang, Professor Xiaoming Liu, and my advisor, Professor Guoliang Xing. Recently, the time-of-flight or 2F depth camera has attracted significant attention in the research community as well as in the industry. The 2F depth cameras are increasingly implanted in lots of off-the-shelf devices, and the market size of 2F depth cameras is expected to double in 5 years. The 2F depth camera is used to measure the distance between the camera and objects in the scene. However, this kind of depth map lacks a lot of texture. Therefore, as an alternative to the RGB camera, the 2F depth camera has enabled a wide range of privacy-sensitive applications that need to conceal the information while requiring some details simultaneously, such as people counting and surveillance. So we are wondering, can we extract more details or texture from depth maps? Let's first look at this figure. Okay, this is a normal depth map capturing a series of numbers on a paper. We can hardly recognize any texture on this map. And the distance measurement of one row in the depth map is shown on the right-hand side. Basically, in order to show the texture, we need to increase the contrast of different distance measurements so that the details of content can be somehow amplified, just like this figure shows. And then we are able to extract more details of the objects. This is basically the texture we are talking about. To achieve this, we consider to use an additional distorting IR source because the 2F depth camera works with IR light. Okay, so based on this idea, we build the first practical system to expose texture from 2F depth maps. For ordinary depth camera, we will obtain blurry and textureless depth map. By introducing distorting IR source, we upgrade the normal 2F depth camera to an ultra depth system, which can expose high resolution texture from the depth maps. For example, as the pictures in the middle shows, we can clearly see the digits in the ultra depth map, right? While the ordinary depth map shows nothing. With this capability, first, we can augment depth-based applications because we provide textures and more details from ordinary depth cameras. More importantly, this can raise some privacy concerns and can be used to launch privacy attacks. For example, ultra depth can reveal personal identity in surveillance system, which is considered impossible before. If you want to know more about how ultra depth works, let's first take a look at the basic principles of I2F depth cameras. A 2F depth camera emits IR light, illuminates the scene to be captured, and then receives the IR light reflected by the objects in the scene. The reflected light and emitted light have a phase shift due to the round-trip time of flight of the IR signal between the scene and the camera. To calculate the value of phase shift, we collect reflected light in two successive time windows, namely S1 and S2. Using the ratio of S1 and S2, we can obtain the phase shift, and then the distance of objects can be calculated. The distances of all points in the scene make up the entire depth map. Okay, now we have the formula to calculate the real distance d of objects in normal cases. However, the mirror distance tau d will be changed when the distorting IR source is present. Just as you can see here, the formula contains N1 and N2 due to the interference of distorting IR. By substituting S1 and S2, and with some rearrangement, we finally get a formula containing E to calculate the mirror distance. This formula indicates the relationship between the mirror distance tau d and the real distance d, and the expression before d is actually the scale factor of distortion. We can see that E plays an important role in this scale factor, and it determines how distorted the distance measurement is. And the physical meaning of E is the received IR intensity from an object at a unit distance. According to the Lambertian reflection model, E is determined by two key factors, namely reflectivity and the angle of incidence. Now we can clearly see the chain of how the reflectivity and the angle of incidence affect the depth measurement when introducing distorting IR. The reflectivity and the angle of incidence of the object happen to be dependent on the texture. As a result, the distorted depth measurement can expose textures of the scene. In short, our key message here is that the distorted measurement actually can expose texture. Based on the in-depth analysis on distorting IR, we then propose two practical implementations of ultra depths, which differ in how to construct a distorting IR source. The key to impose an effective distortion on the depth map is to introduce distorting IR with exactly the same wavelengths and the same modulation frequency as the TOF depth camera. The most straightforward and convenient solution would be utilizing the IR light emitted by the depth camera itself. So based on this idea, we first propose a reflection-based implementation of ultra depths. We can just simply use a cover board near the emitter to reflect part of the IR light emitted by the TOF depth camera. And then the reflected IR light serves as a distorting IR. In practice, we can easily realize this implementation since there are no special requirements on the cover board's material. Even walls and furniture can be used in the reflection-based ultra depths. Then comes the second implementation, the external IR-based implementation. On the contrary, it utilizes another TOF depth camera with the same model to be distorting IR source. However, a unique challenge here is that the TOF depth camera does not emit IR light continuously. That is to say, it emits IR light of about 8 milliseconds in each period of 33 milliseconds. To this end, in order to implement an external IR-based ultra depth using another time-of-flight TOF depth camera, we need to align the emission time of the two cameras. Luckily, we also observed that the emission periods of different cameras are slightly different, which leads to periodic overlap between the two cameras. When the emission time of the two cameras are overlapping, the received signal of both cameras fluctuates drastically, and vice versa. So, from the view of the attacking camera, the received signal fluctuates periodically. Then the attacking camera can learn when the two cameras are overlapping or not. And we only need to adjust its emission time periodically for the alignment. For the experiment, we first validate the feasibility of both implementations of ultra depths. The first is reflection-based ultra depths. From the figures, we can see that reflection-based ultra depths is quite easy to be implemented. You can see that even walls and desks work very well to construct distorting IR and output good ultra depth maps. Also, the external IR-based ultra depth is robust to the position of the IR source. For example, in the setup shown here, we place the distorted IR source in different locations, and all these locations will lead to relatively good ultra depth output. Then we studied the impact of several key factors in ultra depth design, including the size of the cover board, the distance between the objects and the TOF depth camera, and then the modulation frequency of the TOF depth camera. To evaluate the performance of ultra depth, we actually define a metric HGLCM to measure the level of exposed textures. Basically, the higher HGLCM indicates better performance of ultra depths. As the left figure shows, a larger cover board will always lead to better performance because in this case, more IR light will be reflected back to the camera, right? And the middle figure shows that the performance will decrease with larger distance due to the reduced object pixels. And the right hand side figure shows that for an object at a certain distance, there exists a best modulation frequency that leads to the best performance of ultra depths. We then evaluate the performance of ultra depths in object detection task. Here we use RGB, IR, 2F depth camera, and ultra depth to record the same scene together for the object detection task. For fair comparison, we first convert the 4 types of data to 8-bit grayscale images, and then we apply a widely used object detector, ULV3, on these images. With ultra depths, the detection accuracy from this figure, you can see that it's much higher than the ordinary depth camera. The ordinary depth camera's accuracy is almost 0. Moreover, we can recognize objects as accurately as RGB and IR images with our ultra depth system. We then evaluate the effectiveness of ultra depths in exposing text information. The examples of the captured images are shown here, from which we observe that ultra depth maps can well expose recognizable text information on the paper. The average accuracy shows that ultra depths outperforms IR images. More importantly, ultra depths can even compete with RGB images and a poor illumination, because RGB camera can hardly see anything under the poor illumination. To evaluate the effectiveness of ultra depths for face recognition, we recruit 10 volunteers and record their faces with RGB camera, ordinary depth camera, and ultra depth camera. Then a pre-trained retina face detector is applied, and it turns out no face can be detected for the ordinary depth camera, for the ordinary depth maps, while the face detection rate for ultra depth maps are over 99%. That's why we only have 2 heat maps here for the ultra depths and RGB. From the heat maps shown here, we can also see that the features of 10 volunteers from ultra depths are well clustered. Moreover, ultra depths achieves over 99% accuracy of classification, which is comparable with RGB images. A key takeaway here from this result is that depth images are not considered to preserve privacy anymore, because our technology can reveal a lot of details such as characters and faces. Okay, let's come to the conclusion. In this paper, we propose ultra depths, the first practical system that can expose high resolution texture from depth cameras. We not only provided an in-depth analysis on the texture exposure mechanism of depth cameras, but also propose 2 practical implementations for ultra depths based on the analysis. Our future work will be in 2 directions. First, we will implement software-defined ultra depths to precisely control the texture exposure. Moreover, we will investigate robust defense measures against ultra depth-based privacy attacks. Okay, that's all. Thanks for listening. For more information, please refer to our paper and visit our lab website. And any questions?
Right, thank you, Juan. We'll let the on-site audience give question first.
Okay.
Hi, Suyan. I really liked your work actually when it came out. I saw it as well since it was also time of flight related. So thank you so much. I think it's a really interesting idea, and I hope it moves the field forward. I'd like to ask you maybe what are some of the limitations I guess you can see with this, so that we can consider other things that we can do. Are there any other limitations that you face while designing this system, or I guess any lessons learned? Thank you.
Well, thank you. It's a great question. I think the most limitation of current work is that we cannot precisely control the level of texture exposure. Just like I said in the future work. Basically, we want to apply the in-depth analysis and the principle to further build a software ultra depths, so that we can use this principle to precisely control the texture. And by using the software ultra depths, we can quickly shift the 2F depth camera from the ordinary depth camera to the ultra depth camera, so that we can use ultra depth system to realize basically two functions using only one sensor. So this is basically the limitation I think for this work.
Got it. Yeah, we also face the same issue with the time of flight sensors not having a very limited API, like you said, not much control over things like exposure.
Yeah.
Okay, thank you so much.
Exactly. Thank you. Thank you.
Any other further question from on-site? Right, if no, we have a question from Slack. So again, Yuanqing, so he's asking, do you have any assumptions on the types of papers, inks, or way of printing?
You're asking the assumption of this paper, right?
Yeah, assumption on what kind of paper the images are on, what kind of inks are used to print them. So many other ways of generating the printing.
Okay, so this paper mainly based on as you can see the in-depth analysis before, we actually build this system based on the simplified principle of indirect time-of-flight camera. So this is a basic assumption of my paper. And also, I think we have a lot of assumptions during the system design, and I think we can extend our work to fit more scenarios and more kind of TF systems.
Okay, so we don't have any question from YouTube. So if no further on-site question, I have one from myself. So it seems that this problem is quite in the flavor of computer vision. Do you have any, but I'm not the expert in that, but do you have any further comments on what the computer vision guys are doing in terms of the task you're working on?
Oh, okay. So basically, yeah, I labeled this paper with computer vision because I think it is, the ultra depth output basically is like the traditional RGB images or the IR images, so I think there are some traditional algorithms can be used to apply to the ultra depth output. And if computer vision researchers are interested in this work, they can basically using ultra depth for the RGB and ultra depth fusion, or for some other tasks. I think it is very meaningful to combine the ultra depth data with some other traditional data modality, because ultra depth data modality, I think it is very unique. It's different from depth data, and it's also different from the traditional RGB like data. So it's like that.
Right. Thank you. So
Okay,
I guess we have to move to the next author. Thank you again. So next one, Hanting, you are on site, right? Please get prepared. And in the meantime, so I'm going to introduce. So Hanting Ye is a second-year PhD student at the Embedded and Network System Group of the Delft University of Technology in Netherlands. He is supervised by Prof. Qing Wang, and he's also a Marie Curie PhD fellow in the European project called Enlighten. His research interest includes visible light communication and sensing. So yeah, right. So Hanting, it's your turn.
Okay, thanks for the introduction. Hi everyone. Welcome to my presentation. My name is Hanting Ye. I'm a second-year PhD student. So this work is under the supervision of Dr. Qing Wang. I'm presenting our work, Spiderweb, enabling through-screen visible light communication today. So first, let's get a general picture of wireless communications. With the development of communication, 5G is now being deployed around the world, and the research on beyond 5G networks and even next generation 6G network has already started. This brings a higher demand for the frequency bands. Therefore, visible light communication is considered as one of the promising techniques for 6G network. As the frame span of communication is getting higher, the ability of communication signals to bypass obstacles is gradually weakening. Thus, in visible light communication, an important feature that relates on is line of sight communication. Therefore, visible light signals can be easily confined within the non-transparent boundaries. So let's further talk about some features of VLC. These emitted light for lightning can be used for transmitter to modulate the information on the visible light. And the receiver also uses various photodiodes and the sensors on devices to detect and demodulate the information from the modulated visible light. It has the advantages of high bandwidth, efficient energy, and so on. So because of this, the potential of visible light communication technology has attracted lots of attention, including but not limited to high-speed indoor communication, vehicle communication, positioning systems, secure communication, and so on. Considering that the VLC and the corresponding sensing applications will be deployed on smartphones in the future, we need to consider the evolution of the smartphones. Currently, smartphone screens use narrow bezel and low bezel to increase the screen-to-body ratio. The final goal is to achieve full screen. This trend will not give us space to place ambient light sensors and cameras on the screen. They must be deployed on the screen. So in this paper, we ask this question. Is it possible to place light sensors under the screen to create through-screen VLC systems? So well, surprisingly, the answer is definitely yes. We don't need to sacrifice the full screen designs to boost the VLC deployment on future smartphone. And single RGB LED emit modulated light, visible light to the under-screen color sensor. And the under-screen color sensor can demodulate the information under different screen colors and brightness. Next, I will reveal the secret of the through-screen VLC. Currently, there are two modulation schemes in VLC, intensity modulation and color modulation. Intensity modulation scheme is now widely used in VLC systems. In intensity modulation, VLC transmitters transmit 1 and 0 by turn on and off the LED. For color-based modulation, different bits are represented by different color of the LED. It can achieve higher level modulation to improve communication throughput. Also, there are currently two main types of screen, LCD and OLED. For LCD screen, as shown in this figure, the liquid crystal does not emit light, and the source backlight panel is used as a light source to illuminate the display panel. The backlight panel is usually opaque, and it would become a barrier to block the modulated light. As for OLED screen, it's more like a sandwich structure. An emissive layer is wrapped by the anode and the cathode. The light is emitted from both sides of the emissive layer. When the cathode is made by the transparent material, the modulated light can pass through the OLED and received by the under-screen sensors. In the past, LCD screens are widely used in smartphones and any other electronic products. Currently, most smartphones use OLED screens. This is also the reason why under-screen sensors are popular now. So, however, in through-screen VLC, the screen still brings a lot of challenges for VLC. Firstly, we can say that the screen will attenuate the incident light greatly. Approximately 55% to 70% of the light is lost after passing through the screen. Also, there are two ways for the screen to adjust its brightness. DC dimming directly changes the control current to adjust brightness. PWM dimming changes the number of on and off states of the screen in a unit time. And the PWM dimming is usually used in OLED screen dimming. This brings a significantly impact on intensity modulation. So the PWM, but although the PWM dimming period is unknown to us, the content displayed on the screen can easily be detected. And on the other hand, the screen refresh rate is usually very slow. Currently, in commonly used electronic products, the minimal screen refresh frequency is 60 Hz, and the maximum one is 144 Hz. They are much lower than the sample rate in communication. The communication rate is usually 3000 Hz. Therefore, we can regard screen refresh time as channel coherence time in radio frequency communication. And during this time, the screen's chromaticity interference keeps unchanged. So we want to push the screen VLC on the color domain. Well, I need to introduce the standard color space in the color domain. In 1931, different devices use different RGB color spaces. International Commission on Illumination proposed the standard color space to measure people's color perception. Each screen may have a different color display range as shown in this figure. Also, an IEEE standard proposed a CSK modulation to make full use of the color space. Depending on the operating frequency of the red, green, and blue lights, a modulation triangle is formed within the standard color space. Whether the screen uses sRGB or Dolby RGB, most of its color space is in this modulation triangle. And the constellation symbols should be chosen inside this triangle. Thus, I need to introduce the first challenge. It's about the color pooling effect we found. Now let's see what happened to the screen interference on the color domain. Compared to common VLC, in through-screen VLC, because there is a screen in between, what the receiver detects is the superposition of the modulated light and the screen light. Thus, the received color signal will be pulled to the color point, a color of the screen, resulting in a color pooling effect. As shown in the previous slide, now I explain why is there a color pooling effect. Considering that the transmitter sends 4 CSK symbols to the receiver, and the symbol A is represented by green light, and the symbol B is represented by red light. Firstly, we need to know that the signal of the color sensor is not an instantaneous signal, but an integrated signal. Besides, the screen period is much longer than the sampling signal of the color sensor. Since we don't know the special screen period, it's hard to let the transmitted signal and the screen signal be synchronized. So when we transmit the symbol A, we may detect orange when the screen is fully on. And we can detect yellow when the screen is in the period, including falling or rising edges. We can only detect green when the screen is falling off. But if we send the symbol B with the same color as the screen, the modulated signal won't be interfered by the screen color. Now let's observe the color pooling effect on the color domain. When the screen is fully on, the detected color point is near to the screen color point B. When the screen is fully off, the received color point near transmitted symbol A. When integration time includes rising or falling edges in the screen period, the point we detected falls on the ray between the modulated symbol A and the screen color B. So the color pooling effect brings both challenges and opportunities to the through-screen VLC. Now we have found the color pooling effect. Intuitively, we can use slope detection to demodulate the CSK symbol, since the interfered signal point will fall on the ray due to the color pooling effect. But there is another problem for CSK symbols followed by AAA design rules. When the screen displays read for 8 CSK, the received constellation points of some CSK symbols on read may overlap, like this. In the meantime, when the screen displays yellow-green, even 4 CSK will overlap constellation points on read. So the second challenge is how to design CSK constellation points under color pooling effect. Firstly, I want to introduce the design criteria on distance. Since the received constellation points remain in the original position when the screen is falling off, we should maximize the minimal Euclidean distance among all constellation points. We want to maximize utilizing the distance space in CIE latency 1. But when the screen is on, there is a color pooling effect. At this time, we should separate the rays from each other to the largest extent to prevent two rays overlapping. We should maximize the minimal angle between two near rays. This is our angle, our design criteria on angle to help us fully utilize the angle space. This angle space is based on the screen color point. Well, firstly, I considered formulating an optimization problem to obtain the CSK constellation points. However, the formulated problem is non-conductive and non-convex. Although we can use some approximation and optimization methods to solve this problem, it brings high complexity and time overhead. So we give up this way. Now let's have a look at the spider web in the literature. The structure of the spider web is shown in this figure. Hop is the place for the spider to rest. Radius is composed of long stick lines for the spider to curl on. And the capture spiral is built with stick silk for catching insects. Our constellation design just like selects the most suitable intersection of the capture spiral and the radius to meet the two design principles, distance and angle criteria. It's like we are laying a trap on a spider web, but we are the constraint that only one trap can be placed on each radius line. How to maximize the minimal distance between these traps? Here, I take 8 swap CSK as an example. After obtaining the rays, we continue to find the suitable constellation points on each ray. We follow the building process of a spider web. In the framework with the ray, we draw concentric circles to connect the rays, all centered around the screen color point. The maximum radius of the circle that has an intersection with the modulation triangle. Then we select 8 constellation points we need from all candidate points. In addition to the selected screen color point, we still need to select only one constellation point on each ray. Firstly, based on design criteria on angle, we follow a ray point procedure. We first identify which ray to select the constellation point, then find the best constellation point on that ray. The ray with the smallest number of candidate constellation points will be selected first. Then, based on design criteria on distance, we use the maximum metric to select a point from the candidate ray as a constellation point. The maximum metric maximizes the minimal distance between the currently selected point and the previously selected points. Finally, in preliminary verification, the received constellation points are all shifted to the screen color point due to the color pooling effect. And you can see there are 7 non-overlapping line segments in the result. The next challenge is about the practical issue on implementing through screen VLC system. Firstly, due to the long linearity of the leads, it often requires more than 3-order polynomial fitting to obtain the normalized optical power of different colors. Secondly, Different color of light have different attenuation under the air and the screen medium. We need to compensate for this kind of attenuation. Certainly, because the ADC output accuracy range is limited and the under-screen sensor detects high-intensity screen light and external light, the sensor at the receiver is oversaturation, resulting in abnormal points in the received CSK symbol. We have overcome above-mentioned problems. For the technical details, please refer to our paper. Now I continue to present the implementation of our point-to-point through-screen VLC system. We use 3 independent Arduino Duo to control RGB LED, transparent OLED screen, and the color sensor, respectively. Since the data is transmitted through a serial port to a laptop for single processing and decoding. The comparison of traditional CSK design and our design's web CSK is shown in 2 tables. The minimal distance among the traditional CSK is always larger than the minimal distance under our proposed web CSK. However, in the angle case, there are overlap cases for all traditional 8 CSK and some 4 CSK. In our design's web CSK, we not only optimize the minimal angle between different arrays, but also adopt the optimal constellation based on the detected screen color. Then we conduct experiments with 3 screen brightness, 0, half, and 100%. We can observe that it's impossible to perform data transmission by only use distance detection. Because the bit error rate is close to half. Under our proposed slope-based detection, 4 CSK reduce the bit error rate to below 1/10. And no matter what the screen displays. Most importantly, for our design's web CSK, the bit error rate is lower than 1/1000th, regardless of the screen color and the brightness. The results show that our proposed web CSK is a key enabler for through-screen VLC system. We also evaluate the system data rate. We can observe that the system data rate is increased by at least 300%. This means web CSK can carry more data than the traditional CSK under dynamic screen color and the brightness changes. And the achievable data rate is around 2 kilobits per second. The current bottleneck is the slow response of the low-cost color sensor. The achievable data rate could be significantly improved with advanced color sensors. Now let me show you some more exciting results. The brightness of the transparent OLED screen determines how much the transmitted signal is interfered by the screen. The experimental bit error rate under different screen brightness is shown in this figure. We observe that with both web CSK, the bit error rate gradually increases with a brighter screen. An exception is that when the screen is falling late, the bit error rate is decreased. The main reason is that the screen signal and the transmitted VLC signals are not perfectly synchronized. When the screen is falling late, it's easy to get a priori information that all the received VLC signals are interfered by the screen. So the slope-based web CSK detection can still achieve a significantly low bit error rate. Next, we evaluate the impact of the incident light angle. We can see that the bit error rate performance decreases severely when the angle between the transmitter and the receiver exceeds 30 degrees. On the other hand, the result is still better when the screen is falling late. The reason behind could be that if the screen is falling late, the intensity of the CSK signals detected by the sensors exceeds its output threshold after adding the screen light, thereby can report the detection view. In other words, when the angle is large, the screen light could help the signal detection in through-screen VLC system. We also evaluate the system performance when the transmitter is placed at a different distance from the screen and the impact of the different ambient light conditions on the system performance. The systems works still very well under some harsh conditions. So, well, let's summarize this work. In this work, we propose the concept of through-screen VLC, and one of this is feasibility by prototyping with off-the-shelf devices. We observed the color pooling effect of transparent OLED screen on color-based 6K signals. Based on the above phenomenon, we designed a color-based and spiderweb-inspired SWAP 6K modulation scheme. Through comprehensive experiments, we show that our through-screen VLC systems works very well on the different environments. So thanks for your listening. I would like to take any question now.
Great, so it's a very cool piece of work. So I'll let you handle the on-site question first. Well, is that no questions being raised on site? Right, so I'm looking at both YouTube and Slack. I'm not seeing any questions. So then it's my turn. So I do have one question. So you are using CSK. According to my experience, CSK is much less robust than using the simple OOK. Using OOK, you probably can have a much higher frequency. So maybe reaching a higher data rate. Do you have any further comments on that?
Okay. Actually, OOK is widely. That's a good question. Actually, OOK is widely used in VLC systems for now, and CSK is rarely used in currently VLC systems. And for the beta error rate, although OOK can bring a low beta error rate in most cases, but I think the communication throughput for OOK scheme is still very low compared to CSK modulation scheme. So have I answered your questions?
Yeah, maybe just a further question. I mean, what kind of frequency do you use for your system?
Yeah,
I noticed that. Sorry, I just noticed you have a bit rate of about 2K. Is that true? So I think I'm looking at this figure. It shows, around 2K for 8 CSK and around 2.5K for the 16 CSK. So what are the frequency you are using for both cases?
Yeah, for now there are several limitations on our systems because the first thing is the integration time or the sampling time of the color sensor is very low, like the 125 microseconds to output a value. And then we use I2C protocol to output the sampling value. So the outer rate of the I2C is nearly 250 microseconds. And also we use some other techniques to prevent the inter-symbol interference, like the oversampling technology. So this measures greatly limit our output system data output data rate. Yeah, for now, but I think there's still a lot of potentials for CSK modulation scheme because we can still use in our future plan. We plan to use 2 receivers on the screen, like one photodiode with a faster sampling rate, and one photodiode with a slow sampling data rate. And we can just use the slower sampling rate color sensor to detect the color symbol, and the other faster sampling rate photodiodes to detect the intensity signal like the OK or any other like ppm signals. I think C-scheme modulation scheme is still can be used in future scheme VLC system.
Right. So I just noticed that Renqing has raised another question in Slack. So let me read it. Is it possible to optimize the system performance if the displayed contents, I mean, in color, for example, is known?
Yeah, of course. Yeah, we didn't. I didn't show some other schemes on this slides because the angle space I mentioned is based on the screen color point. For now, I just show the case the screen color point is on the acute. The modulation angle we can use is the acute angle, but we can still use the straight angle or complete angle when the screen color point is on the edge of the modulation triangle or is within the modulation triangle. So we have more angle space to use, and we can achieve higher level modulation, higher level C-scheme modulation schemes.
Right. Okay. Thank you. So I suppose we should move to the next author, next presenter. I mean, so when Yi is trying to put up the slides, let me introduce him. So Yi Zhu is a PhD student in the Department of Computer Science and Engineering at State University of New York at Buffalo, supervised by Professor Qiao Chunming and Professor Su Lu. His research interests are broadly in security and privacy, autonomous driving, IoT, and machine learning. He is especially interested in understanding the security of machine learning in autonomous driving and developing novel techniques to improve its robustness. Right? It's your turn.
Okay. So can everyone see the screen, the slides?
Right. Go ahead.
Okay. Hello everyone. My name is Yi. So I'm a PhD student from State University of New York at Buffalo. So I'll present our paper titled Adversarial Attacks Against LiDAR Semantic Segmentation in Autonomous Driving. So this is a joint work from State University of New York at Buffalo, University of Georgia, University of Virginia, and Purdue University. So recent years has witnessed rapid development of autonomous driving. Many autonomous vehicles has already been operated on public roads. So perception is one of the most important tasks in autonomous driving. The goal of perception is to understand the driving environments using various sensors. So among these sensors, LiDAR is particularly attractive because it can collect dense and accurate 3D point cloud data and provide precise 3D representation of the driving environment. So currently, the vast majority of self-driving cars companies relies on the LiDAR to build their perception systems. So it is important to study its security and vulnerability. In LiDAR-based perception systems, a fundamental task is LiDAR point cloud semantic segmentation, which intends to achieve semantic scene understanding in autonomous driving. The goal of point cloud semantic segmentation is to divide the point clouds into meaningful regions according to human perception and label each point with a class such as road, vehicle, building, and vegetation. LiDAR semantic segmentation has become an important part of autonomous driving and enabled many applications. For example, it can help identify the obstacles such as vehicles, pedestrians, and motorcycles on the roads. And it provides critical information about the boundary of drivable and non-drivable area, such as the parking areas and roadside vegetation. So this road boundary information is essential for vehicle path planning. And in addition, the point cloud semantic segmentation can also be used to reconstruct the 3D environments. The state-of-the-art semantic segmentation models mainly use deep neural networks to process LiDAR point clouds. However, deep neural networks have been demonstrated to be vulnerable to adversarial attacks, when taking images as inputs. The attackers can change the outputs by introducing a small perturbation on the input pixels. So it is entirely possible for an attacker to perform such attacks against the LiDAR semantic segmentation models. So it is essential to investigate the adversarial attacks against these models. In this paper, we conduct the first study on the vulnerability of LiDAR point cloud semantic segmentation. We propose a physically realizable adversarial attacks against LiDAR point cloud segmentation models. Specifically, we propose a novel attack framework where the attacker can derive some adversarial locations in the physical space. And by placing some simple objects called adversarial objects, such as road signs, cardboard at those locations, the attackers can easily fool the LiDAR semantic segmentation models. So we focus on two types of attack scenarios: vehicle hiding attack and road surface changing attack. In vehicle hiding attack, we consider a car parking on the road or the parking lot. The car could be parked by an attacker intentionally, or it could be a car stopped before the traffic lights. So the attacker aims to hide the parked car from the segmentation model by adding some adversarial objects around the car or on the roadside. And in road surface changing attack, we consider a victim vehicle is driving on the road. The goal of this attack is to change the road surface in front of the victim vehicle to other things such as vegetation by adding some adversarial objects. This kind of attack may result in a sudden stop or driving direction changing of the victim vehicle and further cause traffic accidents. We consider several challenges when performing this attack in physical world. Firstly, the victim vehicle can collect consecutive frames of point cloud data when it moves forward and generate a perception result for each frame. Attacking a single frame is not enough to ensure a successful attack goal, so the attacker needs to perform continuous attack for all consecutive LiDAR frames. And also, the attacker usually cannot predict the driving directions of the victim vehicle before performing the attacks, and the victim vehicle may come from different directions. In addition, the searching space in our problem is very large, and the adversarial objects can be anywhere in the 3D space, which brings challenges to find the optimal solutions. And furthermore, when performing the attacks in physical world, it is usually difficult to exactly place the adversarial objects at the derived locations. The location arrows may affect the point cloud scanned by the LiDAR and further affect the attack results. So to address these above challenges, we propose a general attack framework. Before performing the attacks, the attackers first imitate the possible driving behaviors of the victim vehicle and collect corresponding 3D point cloud data in the target driving environments, which is called original point clouds. Then the attacker derives the locations of the adversarial objects based on these original point clouds. So specifically, we represent each object as a random point cluster in the point clouds and keep them random in the whole process. This is intends to find the locations where placing any adversarial objects could achieve the attack goal. The locations are generated in an offline manner. After deriving the locations of the adversarial point clouds, the attacker could find out the corresponding locations in physical worlds and place adversarial objects at these locations to perform the attack. This figure shows the overview of our proposed adversarial location generation model. We introduce a segmentation loss to minimize the distance between the predicted segmentation results of the target points and the target results. And we propose a semantic misleading method to guide the finding of the optimal locations. We first find some reference point clouds, which describe the things that the attacker desires. For vehicle hiding attack, the things has no cars on the road. For road surface changing attack, the things has a lot of vegetation in front of the LiDAR sensor. Then we make the semantic feature of the adversarial point clouds similar to that of the reference point clouds. In addition, we introduce an occlusion loss to guarantee the derived locations are not blocked by any other objects in physical world. So to train the point cloud segmentation model, we use both semantic kitty dataset, which is a public dataset collected from real driving environments, and our own dataset collected using a LiDAR sensor. So as shown in this figure, we mount a LiDAR on the rooftop of a car, and we use the attack success rate as performance measurement, which is defined as the percentage of the points that are classified as a target label in all target points. So table 1 reports the average success rate of the two types of attacks for different segmentation models. This shows that our proposed attack framework can achieve good performance for both two types of attacks and for different models. In figure 8, we report the attack results of a real traffic scenario from semantic kitty dataset. Here we use PointNet as the segmentation model, and we use random point clusters to represent the adversarial objects as marked by the yellow rectangles. And we can see that the cars are successfully hidden by placing these 3 adversarial point clusters, as shown by the gray points. And we also perform the attack in physical world using our testbed. The first and second row shows the vehicle hiding attack. We can see before the attack, the black cars are correctly recognized by the LiDAR segmentation models, as shown by the blue points. And then we use cardboards as the adversarial objects and place them at the derived locations as marked by the yellow rectangles. After the attack, the black car in the 2 scenes are successfully hidden by the cardboard. The last row shows the road surface changing attack. Before the attack, we can see the road surface can be correctly recognized and shown by the gray points. And after the attack, the road in front of the victim vehicle is wrongly recognized as vegetation, as shown by the green points. And in these experiments, we evaluate the performance of our attack framework on consecutive point cloud frames. Table 2 shows the average attack success rate for PointNet in semantic kitty dataset. We can see even when the number of consecutive frames is 30, the average attack success rate for vehicle hiding attack can still be larger than 50%. Then we conduct experiments in physical world. We consider vehicle hiding attack and drive the victim vehicle with LiDAR towards the parked car. Figure 11 reports the segmentation results of 3 LiDAR frames after the attack. We can see the parked car can be successfully hidden when the victim vehicle is approaching the parked car. The average success rate is our 97%. And next, we evaluate the robustness of the proposed attack. To evaluate the impact of different directions, we drive the vehicle with LiDAR approaching the parked car in different directions. In figure 12, we can see the parked car can be successfully hidden no matter which directions the victim vehicle comes from. And to evaluate the impact of location arrows, we choose the same examples from the semantic kitty dataset and shift each adversarial object within a given distance towards a random direction. Table 3 reports the average attack success rate. We can see that even when the distance is 0.3 meters, the attack success rate can still be larger than 50%. And we also evaluate the impact of location arrows in physical world, as shown in figure 13. We change the cardboard's locations randomly within a given distance, and we can see the target vehicle is still hidden from the segmentation model. And to evaluate the impact of different shapes of adversarial objects, we replace the cardboard with 2 traffic signs and a billboard, which has different shapes. As shown in figure 14, the parked car is still invisible to the victim vehicle. And we also study the impact of passing by vehicles. We drive another white car beside the parked car during the attack. And the segmentation results in figure 15 shows that the target vehicle is successfully hidden by the adversarial objects. And next, we evaluate the impact of the victim vehicle speed on the attack performance. We let the victim vehicle drive at different speeds towards the parked car, and we can see the speed has little impact on the attack performance. And as we discussed, LiDAR semantic segmentation can help detect objects on the road. It has been an important step in many state-of-the-art LiDAR object detection models. For example, in Baidu Apollo's LiDAR detection system, a segmentation module is used to segment the foreground points before generating bounding boxes. So our proposed attack framework can follow the foreground segmentation step and may result in wrong object detection results and hide the vehicle from the detection model. So in this experiment, we conduct vehicle hiding attacks against two state-of-the-art object detection models. And figure 17 shows the visualization of our attack against Baidu Apollo LiDAR perception model. After the attack, the victim points are labeled as backgrounds in the foreground segmentation step, as shown by the gray points. So as a result, the car is not detected by the model. And we also evaluate the performance of our attack on the Kitty dataset in table 5. The attack has good performance on the two models as shown by this table. So to conclude, in this paper, we propose a first study on the physically realizable adversarial attacks against LiDAR point cloud semantic segmentation with real-world evaluations. And we propose a practical and effective attack framework. We conduct extensive real-world experiments to evaluate the performance of the proposed attack framework. Thank you.
Thank you. Very nice talk. So let's first take the on-site questions. No on-site questions anymore? Well, I'm checking the online ones at the moment. Okay, so seems that really no on-site questions. And actually there is no online questions either. Then it's my turn. Right, so I have this question about the sensing modality, because as far as I remember, LiDAR is not the only sensor a autonomous car has, right? So it could have a camera, it could also have a radar. So what happens? It's a Tesla which has a radar. Does your mechanism work?
Actually, you're talking about the sensor fusion techniques, like the fusing different detection to provide a more robust ones. So in our proposed attack, we only focus on the LiDAR. So if there's any other sensors to help the detection, I think it's not working. And this is probably our future work to investigate the vulnerability of sensor fusion techniques.
Right. In fact, I'm a bit selfish in the sense that, you know, a few days ago, I was given a talk, and after talk, people were asking about not fusion, but just radar. So suppose you have a high resolution radar, mmWave one. So no LiDAR, no camera. It seems that Tesla is using such a mode, right? So
yeah,
do you have any idea about attacking such a sensing modality?
I think there's already some work that focus on the sensor spoofing, like spoofing the radar, like injecting some radar signals into the radar sensor, and maybe creating the fake objects or shifting the locations. But for the machine learning, I think there's no works to focus the radar machine learning based detection. Yes, but I think it's still possible to, I mean, maybe we can find some way to fool the neural networks from the radar detection.
Right. So then I guess that's the end for this talk, and that's also the end for the session and the end of the whole SenSys for main conference. Thank you. Thank you all, and hope you have enjoyed this conference, enjoyed our sessions. And so hope to see you next time in some other conferences.
Thank you.
Bye-bye.
Bye-bye.
Okay, I think I am now correctly sharing into the official organized Zoom. That one could go down, over there. We just need to make breakout rooms really quickly in the next 4 minutes on their Zoom, which we can do. So there'll be this. 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 It'll be this. So breakout rooms are made now. Why? Am I in the right audio for one of these things? Am I in two Zooms audios? Who even knows at this point?
Oh, I can hear you.
Okay. You can hear me in which Zoom?
I'm only in the old Zoom, in our own Zoom.
Okay, so
I only have one device here. I'll think.
Yeah.
I'm thinking of. I'll just see if I can share a message.
Then I think the new Zoom should be able to hear me too. I might go get an iPad to be in the old Zoom with, because that's going to make my life a lot easier. Of course, you have a low battery. Anything else would have been far too simple. And then here. Need to. Oh, did I just screw this up? This is impossible. No, this is right. This is right. Okay. Great. And so here, where there are breakout rooms, I can now share screen. Before I do that, more. Sound okay. For the folks that are in the room and can hopefully hear me, we will get going shortly. There are still, looks like 7 people in the old Zoom because we are playing Zoom roulette this morning. So it's going to take a moment to kind of get everybody from here to there. So we'll get going in about 5 more minutes, give or take. And sincerest apologies for the chaos. All right, so we have just 2 more people that need to figure out how to move over, and 2 more minutes left in my hastily planned revised start time. So we will keep those 2 2s in line and get going in about 2 minutes. To you in a moment. All right, I think we've got a decent crew who've managed to join online, and a pretty good crowd of people in the room, hopefully as well. So let's go ahead and get going. First, I would like to thank everyone for their patience with a little bit of the technical challenges this morning. I think that is the unfortunate reality of hybrid events, and hopefully it will go smoothly from here. But as we'll discuss in a second, we're going to adapt a little bit again based on the on-the-ground realities in Portugal. So we'll get everything going pretty smoothly here. That said, my name is Pat Nudo. I am one of the organizers of ENSYS this year. With me in the organizing committee here I'm the general chair, that's my title. With me in the organizing committee is Sebastian Bader, our technical programming chair, as well as Colleen Swanson and Michele Magno, our demo co-chairs this year. And with that amount of stalling, I think our last person has moved over, and I can officially welcome everyone to ENSYS at SenSys 2021. So welcome everyone. Thank you so much for joining us, both in person and remotely. Wanted to start with just a short history of ENSYS. ENSYS has been around for a pretty long time now. I actually had the pleasure of going to the very first ENSYS in 2013 in Rome, where I did give a demo. And since then, it's been growing steadily year over year. And I will say that one of the most challenging pieces of chairing ENSYS turns out to be picking the right color scheme, because there's really been a nice, bold and vibrant history of different pieces across here. But it started from something that was really focused on strictly energy neutral systems and morphed into much more of the community for folks interested in energy harvesting, intermittent systems, and a whole lot of really just interesting ways of powering wireless sensor networks and systems more generally. So ENSYS has had the pleasure of being the largest census workshop for the last several years now. And so the steering committee put this together and said, well, you know, it's really nice to have a strong core consistent community. What this also is an opportunity for ENSYS to really grow and start to look beyond census and see if we can't find other venues that make sense to start growing interest in priorities events. So things that are growing interest in ENSYS. No, there we go. Guillaume, I'm sorry, I just muted you. You were at a lot of noise you were coming through with. ENSYS is really a growing interest to the architecture research community, the systems community, and the programming languages community. And so when you have that list of people who are interested in it, we've decided to run ENSYS twice, as you are likely aware this year, once here at SenSys and again at ASPLOS in a couple months hopefully in Lausanne. And so that's how we get this question of how do we preserve our strong core at ENSYS and SenSys and grow the community. And so we adopted this 2-phase model this year, where we're going to have kind of an opportunity for people who might be new to the area to test out an idea, and also enable people who are willing to do the work to put together demos, because it's a lot of work, to sort of double dip and get to present it to two different audiences, once here at Sensys and again at ASPLOS, without having to go through another submission, et cetera, process. So you get sort of two runs of work out of your same demo to help kind of appreciate the effort that goes into putting together a good big demo. So a couple of statistics. We did have 6 demos submitted. We've accepted them all because they all look pretty good. We also had 8 short paper proposals submitted, of which we accepted 5. So in comparison to NSYS last year, this is about 3 fewer submissions. Wondering if perhaps the short paper solicitation was a little off-putting, but hoping that we will see a return to our normal numbers for our second half edition at ASPLOS this year. All submissions received at least 2 reviews, third if there wasn't consensus. We were generally willing to be friendly with people who didn't have terribly much consensus. We don't get breakdowns per workshop, but it looks like there's about 100 people registered for all the workshops at Sensys. So again, a little bit smaller than it's been in previous years. I think in previous years, sometimes Sensys would draw up to 60 people on its own. So I think it's sort of the nature of conferences right now, unfortunately, but hopefully in Sensys and NSYS 2022, we can get everything back together. So with that, I also owe a bunch of thank yous, especially twice over, because all these people had to do twice as much work as they normally would because we're running the workshop twice. And so thank you to our wonderful program chair, Sebastian, our Village and Demo co-chairs, Colleen and Michele. I also like to thank our unofficial sponsorship chair, Colleen, as she's the person who really is responsible for all of the sponsorships for NSYS this year. So giving her the extra title and the extra big thank you there. Our web chair, Jeff Merritt, our wonderful program committee, and our steering committee as well. I mentioned very briefly our sponsors. I'd like to give an extra special thank you both to ST Micro and to VMware. They will be putting together a best demo prize and best demo runner-up with cash prizes. And I'll note that we are going to award best demo at both editions of NSYS this year. So if you would like to kind of tweak and revise your demo between here and ASPLOS, you can get in the running again a second time around, as well as any new demos that might come as part of the ASPLOS edition. So with that, I want to talk a little bit about today's agenda. NSYS is at its heart a workshop. And so as a workshop, it's something where we would hope that discussion is highly valued, it's encouraged, and discussion can be kind of tricky sometimes in hybrid settings. So we've really tried to arrange the system to have a lot of the hybrid stuff where we're trying to keep both audiences together, biased up front. And then in the second half of the day, we're going to split into an in-person and remote track. So I'm going to talk a little bit more on this slide about exactly how we're going to do that based on some updated information on what things look like on the ground in Portugal. So what we're going to do is we're going to take advantage of everyone sort of being online and in the same room to show everyone's demo videos right in a row right after this. That way everyone gets a chance to see each other's demos and really everyone has opportunity to see each one of the pitches. And then immediately after this, we're going to switch to sort of a optimized for remote in-person interaction. And what I mean by this is we'll open breakout rooms for every individual demo. We're going to ask folks who are on the ground in Portugal with in-person demos to be focused on people in their breakout room, people in the Zoom, people remotely attending their demo for that window of time. And then when it moves over to the coffee break and people start wandering around and there's a little more chaos and things like that, we'll go ahead, we'll close the breakout rooms. We'll have at that point just remote interaction or in-person interaction. And at 5 p.m. Portugal time, or wherever that may be in the world, we'll start the independent workshop sessions for the people who are presenting papers, either in person or remotely. So that's kind of how we're going to work through the day. Does that make sense to everyone? If there's any questions, please jump in the chat, or frankly, just unmute yourself and ask. But I wanted to kind of give this slightly update to the world and make sure that people get a sense of what's going on here. All right. Yeah. So other quick logistics, please do be patient with us. This hybrid is hard and we really are trying our best. There is the SenSysBuildSys Slack you can use for real-time communication, or while we're here, please go ahead and use the Zoom chat here as well. And this really should be updated to say that we're now using this Zoom. But that's okay. And so one last time, I wanted to kind of leave the sponsors on the screen for a moment and give everyone one last chance to ping if there were any questions or issues that they had. Otherwise, I will roll into presenting our demo videos for the conference right about now. Okay. So we are going to do demo video presentations in the order they came in this sheet, which I believe was roughly the original order. And so we'll go ahead and start with the energy aware batteryless Bluetooth low energy device. And please do let me know if there's any issues with the audio or video quality as we start working through this part of the process.
Hello everyone, I am Ashish Sultania. I am going to present the demo on our prototype of energy-aware batteryless BLE device that is powered by ambient light sources. The batteryless node loses its power supply when its capacitor voltage drops below a turn of voltage. This intermittent power supply can be observed more in an energy unaware solution because then the device always tries to execute the task as soon as they are scheduled. But then the node can experience large latency to successfully execute them. However, the same can be avoided by first checking the capacitor voltage before executing any task and later decide whether to execute them or delay a bit to gain more energy. We consider an example use case of monitoring temperature and room occupancy in BLE mesh network. The prototype setup includes 3 Nordic Semiconductor produced blue boards. Those supports BLE communication. The first one is the USB powered mesh node. The second one is the USB powered friend node. And the last one acts as a batteryless energy aware low power node. This low power node reads the capacitor voltage using a voltage divider circuit. We use a small capacitor of 1 millifarad whose voltage is measured by the multimeter and can be charged by the EPIS power management board, which harvests energy using a small solar panel. A Philips smart bulb controls the harvesting power. The Nordic board is attached with an LED, buzzer and IR sensor. For the use case, the low power node sends ambient temperature data to the mesh node at a fixed interval of 10 seconds. It also captures and notifies the IR motion detection event. On receiving 5 such messages, in return the mesh node sends a command to turn on the LED or the buzzer. All incoming messages are first temporarily buffered at the friend node, and based on the available energy, the low power node periodically polls the friend node to receive those messages. Later, it executes the command as received. Now let me show you the terminal of the mesh node and the friend node. The multimeter view shows the capacitor voltage in real time. Once the capacitor voltage reaches 3.67 volt, the BLE low power node will be powered. It will then send the friendship request and continue to send the temperature value periodically to the mesh node. Now the friendship is established with the friend node and the low power node has started sending the temperature data to the mesh node. Meanwhile, I will manually activate the IR sensors at an interval of 15 seconds. The capacitor voltage is dropped on each activity. The low power node also polls at interval of 25 seconds. Here the friend node returns the friend update message mentioning no data is buffered. Once the mesh node receives 5 temperature values, it sends a command to make a buzz sound. Now it can be observed that one packet is queued at the friend node. The latency of this packet also includes the waiting time due to the periodic pole interval time. Now the packet is sent to the low power node and you will hear the buzz sound. I activate the 5th IR sensor detect, and now again the friend node stores the command to light up the LED. Turning on the LED consumes a bit more power, but low power node didn't go below the turn off voltage, which is 2.8 volt, and you can observe that. It can be observed that the energy aware low power node maintains the on state, and smaller the capacitor size used, the faster the charge and discharge cycle. Thank you.
All right. Whoa, 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 whoa. Thank you very much. Next up is going to be the demonstration of an energy-aware task scheduler for batteryless IoT devices.
Hello everyone, my name is Adnan Shahabovic and I'm a PhD student at the University of Antwerp. Today I would like to present and demonstrate my work, which is related to an energy-aware task scheduler for batteryless IoT devices. Then let's start. Tiny battery-less IoT devices that depend on the harvested energy from their environment provide a promising alternative for sustainable IoT vision. Instead of batteries, these devices use small capacitors as energy storage, which together with the unpredictable and dynamic harvesting environment results in the intermittent on-off behavior of the device. As the traditional computing models cannot handle this behavior, in this demo I will present and demonstrate an energy-aware task scheduler for battery-less IoT devices based on task dependencies and priorities, which can intelligently schedule the application tasks, avoiding power failures and maintaining forward progress. In our case, dependencies are designed as a parent-child relationship, where each task can have one or more dependent child tasks that are selected and executed based on different constraints such as task periodicity, required number of samples, or data availability. As we consider the energy awareness in our scheduler, the required capacitor voltage threshold for each task must be calculated, and only when this value is reached, the task will be executed. It is important to note that our scheduler takes care of all the necessary data by storing them in non-volatile flash storage. For the evaluation purposes, we have implemented an IoT sensor application composed of 5 tasks: temperature measurement, store the temperature values, calculate and transmit the average temperature using the BLE mesh communication, and in the end, confirm the transmission by briefly turning on LED, after which an application cycle ends. Let's see how our experimental setup is designed. There are 2 blue boards produced by the Nordic Semiconductor that support the BLE mesh communication. This is the USB-powered mesh node that acts as a receiver node. And this is the batteryless low-power node on which the application and scheduler are implemented. It is powered by the environment emulator, which acts as a virtual capacitor and is able to emulate a wide range of energy harvesting and storage configurations. In the end, the smartphone on which the NRF mesh application was installed is used to provision BLE devices and establish the connection between them. Now let me show you how the validation of our scheduling approach looks like. The graph provided by the environment emulator keeps track of the capacitor voltage behavior for the full time of the experiment. Below, you can see the terminal of the USB-powered receiver node that shows the proof of received messages, and with that we can calculate the number of successful executed application cycles in the end. In this case, the 4.7 millifarad capacitor and the constant harvesting current of 17 microamperes are considered. Before each task execution, the device waits until the required voltage threshold is reached. The most power-hungry task is the LED task, which consumes the highest amount of energy and takes much more time to complete compared to the other tasks that we considered in our application. In this case, the device needs to sleep for a longer time in order to reach the required voltage, which is in this case, with this configuration, above 2.9 volts. With the properly defined voltage thresholds for each task, it can be observed that our scheduler will stay above the turn-off voltage, which is equal to 1.8 volts, completely avoiding power failure. In the second scenario, the harvesting current will be varied throughout the experiment. We switch the harvesting currents every 35 seconds to check if our energy-aware task scheduler can react to environmental changes. In first 35 seconds, the highest harvesting current of 85 microamperes is considered, after which it will be switched to 17 microamperes. In this case, the device is able to execute only one task cycle, as it needs more time to charge and reach the required voltage thresholds. In the end, as harvesting current increases again, the device is able to execute more tasks, as thresholds now can be reached faster. It can be observed that our scheduler is able to react and adapt the execution to environmental changes. Also, with the properly defined voltage thresholds for each application task, our energy-aware task scheduler can keep the device on during the full experiment, completely avoiding power failures. In the end, I would like to mention the three main goals of my future work. The first one is related to energy predictions, which can determine more accurate after how much time the scheduler will have enough energy to execute tasks instead of testing different values. The next one is related to real-time keeping, which can help us to keep track of time and deadlines across power failures. And the last one is to make our scheduler more intelligent in terms of storing data decisions, where it will be able whether to use volatile or non-volatile memory based on the energy conditions.
Awesome. Thank you very much. I see a couple of chats here. But it looks like they're mostly questions related to the demos, which is great. Folks are encouraged to go ahead and take advantage of the chat mechanism to talk with the presenters. So next up here is going to be RF power transmission, energy harvesting for self-sustaining miniaturized sensor nodes. Looks like this one is
Hi, welcome to my demo presentation about RF power transmission, energy harvesting for self-sustaining miniaturized sensor nodes. So let's first get to the motivation for this work. Smart things are taking over the world, and devices, sensors are continuously increasing in complexity and increasing in functionality. But at the same time, they meet big challenges. The size of batteries and the energy of batteries is limited by the design size of the device, for instance. Of course, the energy consumption can be reduced by using intelligent strategies such as duty cycling or such as smart wake-ups or other things that I imagine will be heavily featured in these demos. But there is also another possibility, and it is to harvest energy. And RF is one energy source that can be controlled and can be designed for. So it can enable the permanent powering of devices with a known energy budget. That way, the battery can be reduced or even eliminated while maintaining the maximum functionality for these devices. So let's get to these designable parameters. What can we actually control? Of course, we can control the power level, which is just restricted by regulations. We can control this, the frequency. We can control the transmitting and receiving antenna gain and sizes. But we can also control the number of transmitters and increasing that way the diversity, and also control the distance that the transmitters and receivers are placed from each other, in this case in a static environment. So starting from these constraints, what is the actual power that we can transmit in the real world? Well, up to 2 meters of distance, using a 3-watt transmitter and assuming well-aligned antennas, we can get up to 2 milliwatts of power at the receiver's antenna output. Of course, these 2 milliwatts we cannot use fully. We have to first transform it to a DC current that our device can actually use. And this work concerns itself mainly with how this transformation is occurring. Now, of course, practice is different than theory, and in this case, we can see what are the actual real-life measurements for commercial antennas. And from this slide, we can see that if we get to very small integrated antennas that have, in this case, a PCB area of just 7 centimeters squared, the received power is very poor and low. So the goal for actual use of rectification circuits in real life is to optimize the efficiency for these low received powers, because in most applications the power will be in the range of -3 to 3 dBm and not much higher than that. Now we come to the most important part of the demo, which is the circuit that we have been actually designed and compared and evaluated. And as you can see, there are a lot of different advantages and disadvantages from different design approaches. So for instance, the distributed system is extremely good at low power, so having an efficiency of 57% at minus 10 dBm of received power, which allows energy harvesting systems to work either with very small antennas or at great distance, while other designs have very good efficiency at more medium amounts of powers. But the best way to see how design is actually performing is to compare it with real life example of a product that already exists. A good point to start our comparison is to a commercial device such as the PowerCast P110B, and it is designed to harvest at 950 megas, just like the circuits realized as part of this demo. And the maximum measured efficiency for the realized devices is much higher at 0 dBm than the commercial one. So one of the realized designs has an efficiency that is 40% higher than the commercial device. As the people that are in person will be able to see, the efficiency also of these devices in real life scenario is very high, so up to multiple meters of distance, enough energy can be transmitted to light up an LED independently of objects in the way. So this is all for my presentation, and I hope to see as many people as possible in the demo, in the real life demo.
Hi,
welcome.
Fantastic. Thank you very much. I have a paper a couple students did for my class last quarter that I'm going to have to send you. I think you're going to enjoy it. It's going to complement your work pretty nicely, but we'll talk more at the demo session. Coming up next, we have a battery-free long-range wireless smart camera for face recognition. Let's get this one going.
Hi everybody, and welcome to my presentation. Today I'm going to introduce a battery-free long-range wireless smart camera for face recognition. I'm Marco Giordano, and I'm a member of the Center for Project-Based Learning at ETH Zurich. Let's start introducing the project's goal. Nowadays, there are many miniaturized cameras that are used for tasks like surveillance, monitoring, and controlling access. However, they rely on batteries with only a few hours of operation time. This is why we focused on a battery-free, long-range wireless smart camera for face detection that relies on energy harvesting to achieve very long-lasting battery lifetime. Let's picture this scenario. There is a need to monitor which people comes in and out of a door, and the camera can be connected to line because cabling can be very expensive. Also, having a battery-powered device cannot be a viable solution since battery has to be changed every few days. Our solution is to use energy harvesting to achieve a potentially infinite lifetime and use a long-range wireless communication to report accesses in real time. Let's have a look at the sensor node. As computing element, we choose the Maxim 78000. It is a novel Cortex-M4 and RISC-V microcontroller that embeds a neural network accelerator. We choose it because the inference times can be speed up to 500 times the one of a Cortex-M4, and of course we use it for our neural network-based facial recognition. The energy harvesting is handled by the BQ25504 from Texas Instruments, and we choose it because it features a maximum power point algorithm. The wireless communication were handled by the LoRa SX1261, and we choose the LoRa protocol because of its long-range capabilities and low power consumption. The camera is the one embedded in the MAX 7000 feather board, and it is from OmniVision, the 7692. Here we show the neural network architecture deployed on our sensor node. It has been optimized with a neural architecture search for facial recognition, and it has to be efficient as well as high accurate. We managed to achieve more than 95% of accuracy with less than 40,000 parameters and an inference time on the Maxim chip of less than 1.4 milliseconds. It has been trained on the Cerebral dataset, but since there have been very few images per subject, around 20 to 30, that has been augmented, both in terms of exposure and also image has been rotated. Here we have an overview of the power consumption. So we start powering up the sensor node, initializing the peripherals, and go in low power mode. Then, if a button is triggered, the node is woken up from low power, the camera is turned on, and an image is captured. Then the neural network is run, and the end result is sent via LoRa communication. After that, the node is sent back to low power, as well as the LoRa transceiver. Concluding, here there is a demo of our sensor node. Please enjoy the video.
Welcome to our demo of our long-range wireless smart camera for face recognition. As you can see, here there is a sensor node with a MAX 7000 chip, the solar panel array, the LoRa module, and the energy harvester with a capacitor bank. When I'm going to press switch number 1, the camera will take a picture, run a neural network, and send the end result, so just 1 byte of data, to the computer that will display my photo, hopefully, from a database. Let's see if it works. And indeed, this is me.
I would like to thank you for your attention, and I hope that you enjoyed this presentation. If you have any further questions, please don't hesitate to contact me at the email you can find in this slide. Again, thanks a lot and have a nice day.
Hello, I am Guillermo Marcano, a second-year PhD student at UC San Diego, and this presentation is for a demonstration on powering an e-ink display through power harvested from soil bacteria. As an introduction, power is a perennial challenge for real-world wireless sensor network deployments. Infrastructure and maintenance costs can become prohibitive at large enough scales, possibly preventing the deployment of some very large networks. In recent years, there has been renewed interest in harvesting energy from extremely low power sources, both novel and old, due to improvements in energy harvesting technology. My research involves the use of soil microbial fuel cells, or MFCs, as a low power but long-term power source, due to the low cost of the materials required to build MFCs and their very low maintenance requirements. For a brief background, MFCs were first described in 1911, outlined on the figure on the left. Since then, a lot of research has focused on aqueous MFCs, like the design on the right, due to their ability to simultaneously generate small amounts of power and treat the wastewater used to feed the cells. Experiments in the 1980s also demonstrated that aqueous MFCs, when supplied constantly with fresh water, can last for years. Earlier MFC designs required the use of toxic chemicals, known as mediators, to facilitate in the electron transfer from bacteria to the electrodes. But around the 1990s, new bacteria were discovered that are able to do the electron transfer directly into electrodes without mediators. Many modern MFCs take advantage of these electrogenic bacteria to simplify cell design. My research focuses on soil-based MFCs, where water concentration is lower. One advantage of soil MFCs is their extremely simple construction. Both of these images show soil MFCs constructed out of 2 carbon felt electrodes, soil, titanium wire, and some amount of water. All of these materials are relatively inexpensive, and cells are straightforward to construct. Prior research has demonstrated that the bacteria responsible for a lot of the electrical generation come from the Geobacteriaceae family, and these are abundant in all types of soil in our planet. The biggest challenge with MFCs in general is the low power produced by them. In our experiments, we have measured power generation as high as 100 microwatts and down to 1 microwatt and below per cell. Additionally, there are a lot of factors that may affect bacteria power production, including, but not limited to, oxygen levels, temperature, and carbon content in the soil. This demonstration repeats the experiment done for a workshop paper that I will present in LPIoT 2021 at Mobicom, showing the feasibility of harvesting with off-the-shelf components, as well as the problems observed with said components. For our original experiment and this demonstration, the general experimental setup is shown on the left, and a picture of it is shown on the right. The ModWatt is the soil MFC, which is the cylinder on the left, with the energy harvester connecting to it and the breadboard where the supercapacitor is. The red board on the bottom is the aptly named breadboard microcontroller, and the e-ink display is a small screen sticking up vertically from the breadboard. The other red system on the far right is a rocket logger, which we use to measure the voltage and current of the experiment. As the complete experiment takes hours to complete, I will only be demonstrating that we can drive an e-ink display with a supercapacitor that has been charged overnight from my ModWatt, and then I will show the live feed from a rocket logger to show the charging behavior. These graphs show the complete experimental data taken over the course of almost a full day. At the beginning of the experiment, the ModWatt had been allowed to rest without any load attached. The supercapacitor then slowly charged over the course of almost 13 hours to its peak of 2.6 volts, at which point harvesting stops due to the ADP 5091 changing behavior and trying to operate in synchronous mode, which is unable to function and only succeeds in slowly draining the supercapacitor charge for the next 3 hours. Eventually, the voltage drops enough that the energy harvester switches back to its original mode and recharges the supercapacitor to 2.6 volts. On the right is a zoomed-in portion of the graph on the left to highlight the behavior of the energy harvester. The small spikes on each crest are the MPPT algorithm sampling the open circuit voltage, but the algorithm overestimates the amount of power available, slowly depleting the MFC. Once the MFC voltage drops below the harvester's cutoff voltage, the harvester stops and waits for its cold start voltage of just under 400 millivolts before starting again. These are the voltage and power measurements of the supercapacitor and the electronic components of the experiment for a single e-ink display refresh cycle. While e-ink displays are thought to be low-power devices, that is only because their steady state does not require energy. E-ink display refresh cycles are long and relatively energy expensive. For example, the full refresh cycle of this particular e-ink display consumes around 55 millijoules of energy over the course of 5 seconds. Even so, our supercapacitor only drops around 150 millivolts in a time frame, indicating that there is enough charge for multiple refresh cycles. In summary, while MFCs provide low power, over time this energy can be harvested to enable intermittent large energy events. However, current commercial off-the-shelf energy harvesters do not harvest this power efficiently due to the unique characteristics of these cells. And that is the end of this presentation. I will be happy to answer any questions in the Q&A section.
Awesome. Thank you so much. And apologies for hardware mute between here and the last one. I did want to compliment the previous presentation on the brave moment of hope that it works in the video. I appreciate that very much. And I have questions I'm waiting to ask them about this 1 byte magic picture and exactly how that works during the question and answer session. Similarly, this last video, the harvester stuff is pretty funky, and I encourage people to come check out what's going on and understand why commercial energy harvesters actually kill bacteria. And our coming into our last demo presentation here, a simulation and prototyping toolkit for airflow energy harvesting in vehicles. I'll get this going right about now.
As sensing and computing elements become inexpensive, low power, and miniaturized, mobile devices become ubiquitous. A significant detriment to the proliferation of these devices is the limitations in battery technology. Airflow energy harvesting presents one promising solution to this problem in various contexts. In this demo, we present a simulation and prototyping toolkit called Exergy, which is designed for airflow energy harvesting in vehicles. The Exergy toolkit consists of a desktop simulator, and a power conversion and management hardware system, and a software library for embedded system integration. To explain the features of Exergy, I'm going to walk you through the steps on how to create a self-sustainable wireless camera systems. In this design task, we need to consider three major requirements. First, the system should be able to generate 800 milliwatts, which is the power demand of the camera system. Second, the system should be self-powered at a speed of 20 miles per hour. And lastly, we wanted to install this system to the roof of the sedan. The first step is to select the vehicle type in an Exergy simulator. This simulator can support sedan, SUV, heavy truck, motorcycle, and bicycles. The second step is to design the simulations. You can choose either a real-world driving scenarios or a static driving speed. You can adjust the size of the wind turbine. We'll use a default value 4 inch here. And you can enter the power demand of the target system, which is 800 milliwatts. And then the final parameters of the simulation is the location of the system, which is the roof of sedan. And you can see the movable point, which is a red color dots. You can also select the top, right, or left area of the surface. Once you complete the design of your simulations, you can move to the third step, the execution of the simulation. You can start the simulation by clicking the Run Simulation buttons. It will return 4 results: driving speed and the wind speed at the location of the system. And when it comes to the power, it visualizes the power demand and then the estimation of the harvested power. As a final step, Exergy simulator analyzes the results in a descriptive format. Again, you can compare the power demand and then the expected power. It confirms whether your target system would be self-powered or not. In case the system could not harvest enough power, the simulator suggests ways of improving the performance of wind energy harvesters. After completing the simulations, we can start to manufacture the system with the Exergy hardware approach. Exergy includes a bracket with a strong magnet and 2 power management circuits, lithium polymer battery, LED, and custom built propeller, DC motor, wires, and pre-programmed ESP32 camera modules. The first step is to interconnect the propeller with the DC motor to convert the rotational energy to electricity. You can then connect a buck booster DC-DC converter to the DC motor. After that, the power manager needs to be connected. It can control the power path, charge the lithium polymer battery, gauge the battery level, and regulate the voltage. Before moving into the next step, you can confirm the system operations with LED. You can then connect the battery and the pre-programmed camera modules. This is the final outcome. For evaluations, we check the wind speed through the anemometer. As you can see on these screens, the system was able to transmit the video signals while charging the battery from the power harvested in the wind turbine.
Very cool. Thank you very, very much. I have some questions for you as well, but we will catch up with that in the breakout sessions, which are going to be coming up next. And so I want to just kind of write these down once. So first, for our folks who are on the ground in Portugal, if you could start heading towards your demos, start getting set up. And also, please do go ahead and join the Zoom. We want to prioritize the first half of this demo session for people to visit you remotely, and the second half of the demo session for people to visit in person. So I'm going to say the prioritize remote viewing breakout. So there is, if you are in the Zoom, I will open breakout rooms in just a moment here. And you should, the Zoom client, be able to choose which breakout room you would like to go to. There should be one name for each of the demos that you saw. I encourage folks to go check out the different demos, see what is going on at all the different places. Should be, what time is it in Portugal? 16. There we go. And then at 1700, we will split sessions for paper presentations. Please join the Zoom meeting to select demo breakout rooms, and the Zoom meeting is available at tinyurl.com/nsys21. Okay. Nice and big. And so I'm just going to fill a little bit more air to make sure that the folks that are on the ground in Portugal have a second to get over to their demos. The folks that are doing remote demos, I would encourage you to, at the very beginning, pop into some of the in-person demo breakout rooms, take the opportunity to talk to them a little bit as well, check out their questions, and then after 15 minutes or so, so from 16:15 through 1700 hours Portugal time, pop back into your own breakout rooms here or there. But it is kind of tricky sometimes when you are both presenting a demo and attending to get the opportunity to see other people's demos. So I would like to kind of give the guidance to everyone to prioritize the demos on the ground in Portugal for the first 15-20 minutes. Head out those, check out those opportunities, and then we can go check out other opportunities, the rest of the demos throughout the remainder of the session. And then at 1500 hours GMT, that's going to be 9 a.m. for me here at US Pacific time, elsewhere in the world. We will split into explicit split sessions. The folks that are on the ground in Portugal for in-person paper presentations, all the in-person demos will form one mini workshop, and those of us online will form the other mini workshop, and we'll go through each of our paper presentations and workshop discussions there. So that's the plan. With that, I think we've had just about enough time that I will go ahead and open the breakout rooms. And I will tell you that you again can click hopefully in the bottom of the Zoom screen to go to any breakout that you would like. I will leave this shared so that folks can have this URL. And again, please do pop into different breakout rooms. Please take advantage, ask questions of folks elsewhere, and then we will be good to go. All right. So with that in mind, if there are any issues, please do contact us via Zoom chat here, via Slack chat. But otherwise, please go start popping into breakouts, and we will see you all a little bit later. Looks like some people have already headed into some of the breakouts, and that's going pretty good. So Do be a little patient as people on the ground get into the breakout rooms, but please pop into breakouts and chat with some of our demo presenters and check out some of the demos.
इंग्लिश तो बोलने से ही आती है इसलिए वो बंदा कहता है जब आप एक बंदा ढूंढे जिसके साथ आप बोलचाल हो आपका आप बोलती नहीं आपको आती भी नहीं मुझे वो सीधे बदले अब देखिए पहले बंदे से जरा मुश्किल बात हुई है मेरे से दूसरे से बात जब की थोड़ी सी आसानी हुई है तीसरे से जब बात की है तो और थोड़ी सी आसानी हुई है कुछ होता है ना कि टेंस को यूज करना या फिर क्या नाम है प्रोनाउंसिएशन उन चीजों की जो होती है ना थोड़ी रफनेस वो नीट हो जाएगी हाँ वो नीट हो जाएगी वैसे बोलचाल में उसकी इतनी जरूरत नहीं है नहीं उसको भी मेरी अच्छा उसको भी थोड़ी बहुत मेरी समझ आ रही है और मुझे भी वो तो वो दर्ज करते हैं ना पाकिस्तानी हाँ एक आधा लफ्ज जो है ना उसको समझ आ जाता है तो वो पिक कर जाता है वो पिक कर जाता है क्या और बीच में वो इतना पॉज है अब ये बेल्जियम का था लास्ट वाला बंदा इससे पहले वाला जो था वो कोरियन था उससे पहले वाला अमेरिकन था सबके एसेंट ही डिफरेंट है ये अब इंडियन था आशीष इंडियन को तो ज्यादा समझ आएगी उन्होंने अपने प्रोजेक्ट डिस्प्ले किए हुए हैं अपने वहाँ पे लैब्स में अच्छा ज्यादा देर ना तुम ब्याह करो सामने सोच रही है बैठने से आज नहीं ना लगो गर्मी लगे एक साइड चलाए पीछे रखे हैं आगे ना लगे इतना तेज चल रहा है थोड़ा पीछे करके जाती है नहीं अपना हमारी लाखों जी और गपशप जी आए ना और नहीं यार जितना लगा है तलाश करी गया वो पिछला जो था ना वेबिनार वो भी उसमें भी उन्होंने पर्सन टू पर्सन इंटरेक्शन कराई हुई थी दो दो तीन तीन लोगों की कि आपस में आप डिस्कस करें ये भी ऐसे ही था डिस्कशन हो रही थी दो दो तीन तीन लोगों की बोली एवं वायरलेस स्मार्ट कैमरा फॉर फेस रिकॉग्नाइजेशन अभी लोग वापस नहीं आए उन रूम्स से
Hi, buddy. Hi.
un messaggio privato. Combo Wombo Demo.
Sì, com'è andata? Alla grande.
Qua, qua adesso
È possibile avere una demo?
it is
Certo.
connected. Adesso lo stai powerando con RF o?
I went to the wrong room. I'm so good at this.
Hey Pat.
Room, qua. Room.
Cazzo.
That's how everyone is doing it. But if you have a pen drive, you can pass it. If you have a pen drive, I think passing the presentation to that computer will be easier. If you want to use your computer, you can use your computer as well. Share your screen. Okay. Just join the session on Zoom, turn off your mic and your sound, and you use the stage mic. Okay. Then it's better to switch off. No. So you can enlighten us. Sorry, from both of yeah, yeah. Okay. Yeah, it's okay. It's okay. Was okay. We don't. The focus are not. I think your camera is better. There's a later already. Portrait mode or landscape? Whatever. Yeah. Thank you very much. Yes. Yep. Okay, so the one reply that maybe there is their own we do this session here or they will do remote this split was not agreed by but the program was like this before we discussed 1 week ago. Okay. Okay, so maybe there was. You tell me what to do. They should tell me, but we do how we do. So we do in this way. So the person track is here. The meetings organized to go in Zoom. We do it. So we do how was all the conference done. And then what do they want to do with this remote? They didn't tell me, so we don't care.
Okay. So we proceed as planned.
If they reply in time. Who is presenting? You are also presenting. Okay. So let's start with this to finish. Okay, so no hay stickers. Let's try to protect the people at least.
All right, welcome back to the main remote session, everyone. I think we're going to give it just until about 5 after before we get going with our first presentation. That'll let folks that are figuring out the different Zooms, figuring out how to move between spaces, And so we ran demos right to the end, a brief biology break and whatever else folks might need. So we will get going at about 5 after in about 3 minutes.
Do I have to press any buttons?
No, it's turned on.
Okay.
They're close to finish now. I already asked this question. They're close to finishing.
My PhD?
Yeah.
Maybe 1.5 years.
Okay, but when it's going to then joke, yeah. Okay, I don't see it.
He's officially retired this summer.
Exactly.
Yes,
but you can
but he
continue.
has 1 more year for wrapping up some
Okay.
papers, one of which
I
will
thought
be-
you need to close a bit to the.
No, most of the group will conclude their PhD.
Yeah, but you
event.
can rest it.
There's a bit of flexibility. So right now, so on the 1st of December, I'm starting my 4th year. So it's good that I have a little bit more time. Yes.
Good. I will exploit that in around. I like a lot of you know that he
Yes.
sent me in Ghana. They call him to do this Ghana lecture
Oh,
for.
yes, yes, I heard about
Because when
this.
we want to go, you go and be old. Okay.
It's a very cool
Yeah,
opportunity.
I
It's
like a
super
lot.
nice.
You know, it was my PhD. I did a visiting PhD in 2008.
no,
I was
I did not know.
in G. I don't remember the name, the number, but it's the latest. Before was a door there. I don't know if it's still there. It's the really last.
Oh, I did not know. That's so cool.
Yeah.
He's
I
a
was
great
working with
professor.
people that are not anymore there. I was working with,
All right, folks, it is just past the hour, and it does look like the juggling Zooms might make it challenging to do split track. It's not entirely clear how that's going to go. My hope was that we could keep ourselves on this Zoom, and I think we're a small enough crowd that we might be able to just adapt to perhaps a single track session, just everyone staying together. And then we can just sort of alternate our originally planned scheduling here. And so we could probably start with the originally planned remote track or the originally planned in person. It looks like Naomi has already sharing her screen and ready to go in person. So we might start with Naomi and then go over to the autonomous energy sharing and synchronization of battery sensor networks, then reserve, then persistent timekeeping, then designing a general purpose platform. And we'll keep it all in one big single hybrid track if that's going to end up working out. So I think that is going to be the easiest thing to do, given the way that hybrid has worked out. And so with that, I am probably going to hand things over to Naomi and invite you to go ahead and start your presentation whenever you are ready.
Would you like to say something or no?
Yeah, maybe I can. I just confirm it because it was audio a bit bad. So I think we have now the first presentation in person. That is Noemi Sticker from ATH Zurich that is presenting joint energy management for distributed energy harvesting system, and she's ready here, and you can start.
Yeah. All right, thank you. So hello, everyone. I'm Naomi, and I've had the pleasure of attending ENSYS for a couple of years now, really immersing myself in this energy harvesting domain. Now, I've seen and I've done it myself. We argue that energy harvesting systems, they scale better and they have lower maintenance costs than their battery-based counterparts. Of course, beautiful advantages. And I would argue that these advantages also make them very suitable for distributed systems. And so thinking about distributed systems and energy harvesting, we start by investigating individual energy harvesting systems, and we do that with a lot of great work. And I think we should also consider multiple of them together to really see and exploit this scalability possibility. And so this is what we argue and start doing in this work. We propose to use multiple energy harvesting nodes in a single application, and for this then jointly optimize their limited resources. So for the scenario we envision, there are, of course, multiple energy harvesting systems working jointly in a single application. And you might find this in different domains, say, for example, the control domain or monitoring. So to give you a bit of a more explicit example, if we want to do automatic building control, we can sense the state of the building with multiple nodes, energy harvesting nodes, collect this data and use it to, well, control the building. Our work then, of course, in this example, focuses mainly on the distributed energy harvesting systems. Now, I know that there are a lot of different, say, ways of looking at energy harvesting systems. There are people who do intermittent research. For the time being, I'm focusing on energy neutral systems, and they, in a sense, plan their energy usage ahead of time. They decide how much energy to use and how much to save in their energy storage for later on. Now, naturally, if you have a couple of them, they can, well, plan independently. They can use various amounts of energy in the same time window. But what if we actually need data from all of the nodes to draw any benefit from the data? And what I mean by this is, say you have 4 or 5 different sensor nodes, and they're sensing their environment. If one of them senses a lot more frequently and uses more energy, in such a scenario, I would say, okay, this is not extremely beneficial for this single application, that we have this one node that does a whole lot more. So then what we can really do for this single application where they're all working together for is somehow the minimal energy across all of the nodes that we can use. So we're somehow following and we're dictated by the smallest energy usage that we're planning. I call this the common energy usage across all nodes. And what then happens when we do energy management for all of the nodes individually is we're not really thinking about this. And this might then lead to suboptimal performance for the application. And this is where our work comes in. So we propose to jointly manage the energies of all nodes and then also manage the application's performance. And we propose to do this really in 2 steps. So in the first step, we do the separate energy management. So each one of the nodes really optimizes its own resources and performance. You might have seen a lot of work also at NSYS on this topic, and we then use this in the second step where we jointly optimize all of the nodes and all their resources together. We use the first step or the solution of the first step in the second as constraints and can ensure that we can only improve on what we got in the first step. Now, the concept here is that we can use the energy storage to move around when we're using how much energy. So you can decide to save some for later on and use it then, right? The idea with the joint energy management is to coordinate between the nodes so that they can use as much as possible at the same time. And with this, then we optimize where this data, for example, would flow into the single application. So we applied this also in a small indoor harvesting scenario like we would have in the building control that I mentioned before. And we see that simply by considering all of the nodes together, we can really improve what we're doing with the nodes and how this application can perform. In the small example we highlight, that's by 28%. We're not changing any of the factors around it. So no increases in solar cells or energy storages. We're just looking at, let's say, the whole system and optimizing it. And so this is somehow considering a bit the distributed nature of what we envision for the energy harvesting systems. And taking this a bit further, I would like to, for this discussion round, invite you to consider what we really need to address to move towards these large-scale energy harvesting systems, because they're somehow uniquely positioned for such systems, right? We have the scalability and low maintenance costs that really make them uniquely suitable for this. And it's not so clear what type of challenges we still need to address in order to be able to have such systems. Now, when we then move on and we actually build them and they're functioning properly, hopefully, I think it would also be important to consider what type of performance guarantees we need to make or we would want to make so that we can eventually, hopefully, see energy harvesting solutions in the embedded systems mass market, something that is not as widespread, I would say, as it could be. And I believe that with these few discussion points, I would like to open up for, I'm thinking, the intended discussion or possible intended. Pat knows better. Okay, Pat, I will hand back over to you.
So we are on plan B, plan C, plan D at this point. But I would like to open up to a little bit of discussion after each paper, because I think there is some value to that. So I would invite, we're a small enough crew that I think people on Zoom are welcome to just unmute and pop a question into the room, or people in the room are welcome to walk up to the mic and we can use, reasonable back off style approaches. But I'm happy to sort of kick off the discussion a little bit with your very wonderfully charged word in that second bullet point of guarantees. Guarantees is a really, really, really strong word. And so what is your thinking with the word guarantee, and what level of guarantee do you want? What level of guarantee do you want to be able to make with energy harvesting systems? What do you think is reasonable?
So for me personally, In this context, I would say that performance guarantees for me don't really mean that we can say we always, no matter what, have a certain type of performance, but rather, given the environment, we can do the following with a certain percentage of, let's say, definity. And it might also go in the direction of some already published work that I've seen on, system failures within a certain period of time. So it's not performance guarantees in the strictest sense of I will always have this, or I will always be able to guarantee the following behavior, but rather maybe also probabilistic analysis. So
how do we bubble that up to applications? Because computer scientists are notoriously bad for not actually handling failure cases, right? No one actually checks if malloc fails. No one actually checks if their sensor reading returns error, right? They just, how do we get this up into the mindset of people who are building applications on top of things, that computing is getting less reliable, not more?
Well, by discussing it, right? By raising the point, hopefully, eventually, we will start thinking about, my system should not only do what I say it does for the 5 minutes until I have my collected data and I can publish, but maybe also go a bit beyond this. No.
I do want to invite other people to pop in and speak up as well.
Sorry, could you repeat that? I
just wanted to make sure other people know that they can unmute and say words.
Yes,
as well. It's not just me.
Also here, I'm happy to hand over the microphone to someone who has something they would like to share. But
I have more to comment than a question maybe on this last point that Pat mentioned, because I think this guarantees is quite interesting. Of course, this is very dependent on what kind of application scenario you're working on, but I've been working the last years quite a lot with process industry, and they want guarantees. I mean, they want to know that their sensors are delivering values in at least minimum guaranteed intervals. And I think it's an interesting point of discussion to think about what is needed for that. So I don't know. I think I mean, there are two ways to think about, I think, at least, and one is a selection of source, especially if you have applications where there are multiple sources that you can use. I mean, choosing sources, for example, that are defined by the application or the machinery that you have. And the other one is, of course, how do you predict how much power you get so that you at least can evaluate if you can give some certain guarantees, which I believe are two things that are not looked at sufficiently enough at the moment in research on energy harvesting.
Building on that, for the last point, I think some sort of usability. So what if you could take a system and, if it's a solar system, deploy it, and then after, some limited calibration period, basically the system can inform you, given the patterns I've seen so far, I can guarantee, X frames per second from this time to this time. And then after that, we'll go down to this frames per second. So basically kind of the system figuring out, given the constraints, what can it deliver given the power source available at that moment. And additionally, being able to kind of swap between different power modalities to get an idea of, okay, so maybe solar won't work in this location, but if I put in like a kinetic harvester, maybe that will work better for this situation, given what I want to do. So kind of a more interactive user experience for fine tuning these systems, and that's not even fine tuning. It's kind of more fundamental. I think that's what's necessary to take this to mass market. That and playing better with batteries. People aren't going to like it if things stop working without sunlight, without wind, etc. So, systems that put energy harvesting as the first line of defense and then have a fallback battery, I think are going to be critical for adoption.
Yeah, so I think that type of system design where you have a backup battery just in case, it certainly helps with deterministic, let's say, application patterns or moving towards that. But so possibly from a research perspective, it removes some of the trickiness, but possibly for the mass market, it helps because I would assume consumers are still very much in the mindset of, I want deterministic behavior, and I'm not particularly happy when things, well, unexpectedly or expectedly no longer power on, right?
Yeah, I think there still are research questions too, though. Like, for example, the batteries there are kind of in the worst case, but you can have these, pieces of information of, how, is the system 100% harvesting? Is it 90% harvesting? If so, given that it's harvesting 90%, what is the anticipated replacement timeline of the backup battery? Can you leverage unexpected bursts in energy to charge the battery back up, so that you kind of, get an amortized, you're back up to 100% renewable? I think those are all pretty interesting questions to look at from a research perspective. I don't know what you think.
Sure. No, so maybe small commercial break then for a colleague of mine. He did some work on the optimal use of a backup battery, and he essentially optimized over the lifetime of the backup battery. But I don't think he necessarily went as far as to give estimates or evaluate then the lifetime of the battery itself. But this would probably go in that direction then. And it possibly also helps using backup batteries and energy harvesting systems when looking at applications where we need a certain minimum of energy to do just the bare minimum that the application requires. So maybe, yeah, there's some possibilities there.
Awesome. I think this hits right about the perfect timing to break down to 5 different quicker Q&As. So I'm going to move us on to our next presentation. Alessandra's asked if I can play the pre-recorded video as a presentation, and then we can do an extended Q&A with them once we're on. So I'm going to take over the screen share really quick here. And then we go to the video link, and somewhere on the screen is a big play button.
Hi everyone, my name is Alessandro Torrisi, and I'm a passionate electronic PhD student at the University of Trento. And together with Sinan Ildirim and Davide Brunelli, I'm presenting you our work on autonomous energy status sharing and synchronization for batteryless sensor networks. Let me jump into the context of this research. As we all know, tiny electronic platforms are pervading the world. As electronic circuits are becoming more efficient and especially smaller, limitations due to batteries are emerging. Thus, batteryless devices are so special. But relying only on sporadic harvested energy introduces frequent power failures. Thanks to intermittent computing, firmware, and hardware design, devices can restore the computational state after a power failure. But what if a power failure occurs during data transmission? Let's think about a simple scenario with two batteryless nodes. A quasi-fully charged node wants to transmit to a neighbor. If the neighbor is in a low energy status, the data exchange will fail, bringing to a packet and especially precious energy losses. On the contrary, if a neighbor has sufficient energy, the data exchange succeeds. Prior works considered during communication, the nodes are fully powered. So we raised the challenge, and the last year we presented TRAP, our transiently powered communication protocol. To the best of our knowledge, we also propose to include a ultra-low power mechanism to synchronize nodes, enhancing the TRAP capability. Based on the energy status information with a periodic update of the energy level, TRAP guarantees the communication and avoids packet losses. We exploited the RF backscatter to update the node's energy status, while we use the visible light communication for synchronization. TRAP protocol enables the communication between transiently powered devices, knowing the node's availability to transmit or receive the data. When a node has enough energy and wants to transmit a packet, it listens to the backscatter channel. If a high energy status is received, the communication can be initiated with the guarantees of energy availability from both ends. On the other hand, if a low energy status is received, the communication is postponed, the packet won't be lost, and the precious energy is saved. To periodically update the nodes, we use a second infrastructure widely present in indoor scenarios, the visible light communication. We transmit a synchronization pulse, which is processed by an ultra-low power circuit without the MCU intervention, which fires the energy status transmission in a specific time interval, different for each node, preventing energy status collision. Here is briefly presented a typical communication scenario with three nodes. After the VLC synchronization pulse, each node delays the energy status update. When all the nodes completed the energy status update, the data communication can start. Here, as an example, node 1 and node 3 transmit a high energy status, thus they can securely exchange data, while node 2 is out of the games and it has a low energy on board. With that being said, I thank you for the attention and I'm open to any question.
Oh, that's me, me very large, but Alessandro, I'm happy to let you have the first word on anything you'd like for people to discuss and chat about a little bit.
Hello, guys. Can you hear me?
Yes.
Yes. Okay, perfect. So I thank you again for the opportunity in being at SenSys workshop. This is a very nice experience, and it is very, very nice to participate also, if not in present, but virtually. That it was not that a problem, let's say, to follow the breakout rooms and enter in discussion with the guys. So yeah, if you have any question, I will be happy, let's say, to discuss about these new ideas on synchronization and energy status update.
Can you summarize for us some of kind of the future work and open problems?
So the future work or the problems, sorry?
Future work and open problems. So kind of given what you have now, what are the next steps? What are the most burning questions that you have?
Yes, the idea that we develop, let's say, stop with the trap with the capability of synchronization. So typically a node knows when he will receive the energy update from the neighboring. What we can do next is, for example, predict the energy level of a node and when it will be available for transmission, and maybe save some energy on our application, for example, to perform other tasks rather than waiting for a communication or waiting for a neighbor to be available for a communication. So this is a possible open point. Then we also wanted to develop a little bit of the hardware. And in particular, we would like to enhance our synchronizer circuit, first of all, to being more robust to noise interference and other stuff, so better synchronization, but also in the delay circuit with some programmable capability, for example, which would be very, very interesting.
Hi, I have a question. So first, I would like to thank you for doing this type of work. It's very refreshing to see Batteria's work for focusing on communication. So thank you. I had a question regarding, let's say, different possibilities for synchronization. You used backscatter. Have you considered using something like a wake-up radio, where you can use another RF channel to just have an always-on listener, so that you can receive these types of messages of when there's enough energy to perform communication? And yeah, is it something that you would consider? Why yes? Why no?
Yes, we would like to consider also backscatter and other kind of wake-up signals, let's call it like that, or synchronization signals. For example, light flicker, as proposed also from other colleagues. And the idea is that we would like also to try to implement a possible multiplexer, let's call it like that, a multiplexer for clock sources. When available a possible clock source, it multiplexes to this clock, and then it aligns all the nodes. This would also be interesting because we just focus for this paper, for this contribution to visible light communication, as we already have a sort of very simple setup to synchronize nodes, and we merge this setup to our previously made, let's say, backscatter receiver. But of course, there will be the possibility to use, for example, backscatter or a wake-up radio receiver, let's say, to synchronize node as well. And this, I think, will be also a very nice future work or future development of our idea, let's say.
Great, thank you.
Okay, so for the room, there is no more questions. I don't know if there is any question from the remote. Otherwise, we can pass to the second presenter in person is ready here. Pat?
Yeah, I think that it looks like Zoom is quiet now. So let's go ahead with the next presenter in person. That feels good. I believe the next up should be Reserve, the remote attestation of intermittent IoT devices.
You can go there.
So can I share this now? Sebastian, I don't know. Sorry. You want to open a YouTube? No browser. No, it's fine. No, just sorry. Yes,
Just one last minute of getting stuff wired up. I think this is one point where the remotes trump the in-person, right? There's no dongles, there's no wires, there's no complicated projector setup. You just click that magic green button. We've all gotten a little too used to over the last year and a half.
Join without video. Can I minimize it? Yes. Hello, everyone. Thank you for being here. I'm Masum Rabbani, and I'm going to present our work, RESERVE, Remote Attestation of Intermittent IoT Devices. This is an ongoing work and a joint collaboration between KU Leuven, DTU, VUB, and Leiden University. First, I will discuss about the current state of IoT security and a brief overview of remote attestation. Then I'll discuss our protocol RESERVE, and then I'll continue discussing the working mechanism of RESERVE, and then I'll conclude with conclusion and future work. So first, we'll look into the next slides that how remote attestation can be fit into the current state of IoT securities. As you all know, IoT devices are low-cost, tiny embedded devices that is designed specifically to perform a certain task. And often these devices is resource constant and doesn't have sophisticated security measures. And attacks like this, for example, Stuxnet or JeepHack or Mirai botnet exploited these same vulnerabilities that present in IoT devices. So now the question is how to detect malware. So one obvious choice is malware detection. That's true. But the problem is how to guarantee the device which is potentially malware infested is telling the truth. On the other hand, remote attestation is a security protocol and it's already established and used by both academia and industry. And in remote attestation is the security protocol that runs between one trusted party called verifier and a potentially untrusted party called prover. And the goal of the verifier is to verify the trustworthiness of the prover or the IoT device, as you can call it. So now in this slide, I'll give you a very high-level overview of how remote attestation works. So in remote attestation, verifier and prover already shares a key, and verifier knows the expected
hash values of the software digest of the prover. This hash digest is basically the hash value of the software of the IoT device. And prover depends on this trusted component that you can see in the green mark, is also known as trusted execution environment. And this component is act as a hardware root of trust for remote attestation. During attestation, verifier sends challenge to the prover. And upon receiving the challenge, the prover perform the hash operation over its untrusted software. And the trusted component is actually the component that perform this hashing operation. Once this hashing operation is done, prover sign the hash digest with the challenge and sends back to the verifier. Verifier, on the other hand, also perform the same task, because as I mentioned earlier, verifier also knows the expected hash value of the prover. And then once verifier receive the signed result from the prover, it matches the received result with the computed result. And if this matching operation works, that means the prover in question is legitimate, else otherwise. So, however effective, remote attestation is an atomic process. And the reason for that is once remote attestation start, it doesn't end in the middle. So the reason for is to guarantee that there is no malware or adversary that can evade that operation. And the second one is like, no matter what, it's an overhead operations. So whenever a device wants to perform this kind of security protocol, they have to stop the regular work and then run this work separately. So it is an overhead. So thus remote attestation in its current form is not suitable for intermittent systems. To address these challenges, we propose reserve. So to the best of our knowledge, reserve is first remote attestation protocol designed for intermittent IoT devices, which is lightweight. And in reserve, the remote attestation can accommodate the interruptibility. So that means we can stop remote attestation in the middle based on the available energy budget. So in reserve, every device is bootstrapped by the network operator during offline phase. And every IoT device is divided into checkpoints. Checkpoints also indicates the module of software. As in reserve, we thought of dividing the IoT device software into different modules. And every module also indicates a standalone unit. And it is also the minimum unit that remote attestation should run uninterruptedly. So during attestation, the device perform attestation of one of these modules and send the result back to the verifier. So now I will discuss the working mechanism of reserve. So first, a device first immediately after waking up will perform its regular or intended task. And then it will perform, once the regular task is done, it will perform the attestation. So in this case, according to the picture, it is the module 1. So attestation in reserve is a self-triggered process. So the IoT device will perform the hash operation over its module. And to guarantee freshness, it will concatenate the timestamp with the attestation result. So it is also another way to prevent replay attack or some kind of adversary that try to evade by giving the old attestation, legitimate attestation value. And then the IoT device using a secure pseudo random number generator will generate a number. And that number actually indicates a line of code in the module that is being attested at that currently. So in this case, as you can see, the green patch in module 1 is the secure patch or the checkpoints where a device will store the line number and the line of code for that particular module. And then the device will concatenate the attestation result, which in this case is the attestation of the module 1 and the output of the regular task. And before going to sleep mode, it will send the attestation result to the verifier. And in round 2, the first 3 operations, the execution of a regular task, the performing the hash operation over one of its modules, and then storing one of the line of code of that current module that is being attested is same. However, it includes one of the new modules. So first 3 tasks of every rounds in attestation is identical. The difference is in round 4. As I have mentioned earlier, in first round, the device store one of the line and the number and the line of code of that number. And that was stored in M1 Warrig or the checkpoints. And in this current round, the device will check the stored line with the current state of the line in the previous module. So as you can see in the yellow, it will check the state of that stored line using Hamming distance. And then the device will concatenate the regular output, the attestation result, in this case is the module 2, and the Hamming distance result of the checking of the line of code. So step 4 and the concatenation of Hamming distance is the new step that will be followed with the other modules. And again, similarly with round 1, before going to sleep mode, the device will send this output to the verifier. So to conclude, Reserve is a lightweight and novel RA scheme that is designed specifically keeping in mind the intermittent IoT devices. It can detect malware and also partially guarantee security of the module that has already been checked. And in our future work, we would like to implement this remote attestation security in intermittent IoT devices. And as I mentioned earlier, this is our ongoing effort, and we are trying different cryptographies, lightweight cryptographies that can be fit with this low energy budget of intermittent IoT device. Thank you. Any question?
Thank you for your talk. I think it's a very interesting topic and a possible new application for intermittent systems. I wanted to ask you if you already had, so I know your future work is the implementation on the real device, but do you already have an inclination of roughly how much energy you would need to run all of those even lightweight cryptographic algorithms? And do you know if it can fit within the normal bounds of what is currently used in intermittent devices? So average of microwatts, for example.
Yeah, thanks for the question. So to be honest, we don't have the actual data of this in terms of joule or microwatt for the cryptographic operations. However, we are trying, like we were trying this lightweight cryptography that recently for the NIST, and we also try some hashing operations that is designed only for IoTs. And to be honest, so far, it's very difficult to incorporate them into intermittent system because, of course, because of this sudden power failure and all. And also we have to keep in mind that we should not prevent the device to perform its regular operations, because when it's wake up, so it has to do the intended task, and then the available energy budget we are trying to use for attestation purpose. So currently we are trying to find out this kind of power error model. So where we kind of keep tracking how much energy is left and what kind of cryptography can fit into that available energy budget. But again, to keep a track on power our model, it's again kind of draining the available energy. So it's like kind of a trade-off for us. But so far, to implement remote attestation on intermittent system is a bit challenging. But we hope that we could have something in future.
Can I ask a question if possible?
Yeah, sure.
Okay, I'm Sinan. Thank you very much for the nice presentation. I just would like to ask, like, do you have a kind of motivating example in mind? Let's say, I mean, an application scenario where your solution will be really useful for an intermittent system, let's say.
So we are kind of aiming those gas or electricity usage monitors sensors. So in office buildings, that those sensors generally works whenever you, for example, open up a water pipe. So that kind of small systems we are keeping in mind for the first implementation.
Okay, so also you are, I mean, excluding the communication related problems, right? You are just focusing on that remote attestation part, but you assume like there's a kind of notion of communication, right? Which is safely going on between the devices.
Yes, currently at this stage, we are excluding the communications because to be honest, in IoT, we thought of using 6LoWPAN or that packet size of 120 kilobyte. But at this stage, it's we are not including that energy for communication. Mm-hmm. But definitely, when we'll complete the implementation, we must include the communication because that's the backbone of for the getting the attestation result back with the regular operation.
Okay. Okay. Thank you very much for the answers. Thank you.
So I also had a question. Every time we start talking about long-term kind of issues like attestation of firmware or other provenance of data or whatever with IoT devices, start to think about the longevity. And particularly for intermittent systems, these are these things that we would like to dream are going to have lifetimes on the order of decades rather than years, because we're not battery bound anymore. So when you start worrying about cryptographic operations and you start thinking about something that might be in the field for 20 years or more, we start to have to worry about the security of the cryptography over the long term. So I guess my question is a little wandering, but it gets to the question have you thought about what the long-term plan is for a device with a fixed set of hardware that would want to do these kind of attestation primitives as time moves forward?
If I understood it correctly, you kind of asking like after what will happen after 20 years if we are using, for example, implements cryptography based on today's standard.
Yep.
Okay, so post-quantum kind of thing.
Maybe not post-quantum, but in that approximate direction, yeah.
To be honest, at this stage, it would be very naive for me if I comment on that. But first of all, we are struggling to implement SHA kind of because it's too energy hungry. And to be honest, at this current state, we cannot really implement SHA2 or even SHA3. So we are really looking for lightweight cryptography, this NIST-1, the Zodiac, and other version. So I guess I'm afraid that I cannot comment on that, like what kind of cryptography we will implement that can at least give us a sense of comfort for at least it will be safe for 20 years or more. But hopefully, this is actually our first work in this domain of intermittent system. Mm-hmm. We actually found out that there are a few work or ongoing work that actually talks about security in this regard or remote attestation in this perspective. So I guess if the community start thinking from now, so hopefully eventually we'll come to kind of this kind of security implementations in near future, I hope.
Awesome. And I would maybe want to raise this later and so people can start noodling it a little bit. I think it's going to be an important question for our community that advocates for our long lifetime sensors, what we want to do about cryptography in long-lived devices eventually. But we can kick that to our open discussion at the end. I'll let other folks who have questions about the immediate presentation jump in. While people are looking for questions, I might jump in and start preparing the next presenter here as well. Our next presentation is another remote presenter. Both authors are online, but they've asked again if I can share their pre-recorded presentation with the audience here today. So are there any other questions for the previous speaker, or should we move on to the next presentation? And folks can just unmute and chat. You don't need to, it's a small enough audience, we'll make it work. Okay. Well, thank you very much. And I think we'll jump forward then to persistent timekeeping using harvested power measurements. And if I hit the play button here we go.
Hello everyone, I am Eren Yıldız from Ege University. In this presentation, I am going to show our recent work on persistent timekeeping using harvested power measurements. Intermittent computing systems rely on ambient energy sources such as solar, thermal, or RF to power the system. However, the limited ambient energy causes frequent power failures. The device loses processor and peripheral states, including the timer subsystem. Therefore, a battery-free sensors cannot keep time tracking due to power failures. This case causes critical shortcoming for the time-sensitive application. Prior works have proposed mainly two methods to keep the time tracking problems. The first one relies on the remanence characteristic of SRAM, and second one relies on discharging characteristic of a dedicated capacitor. However, both of these solutions are environmentally dependent. Therefore, the designer has to be aware of the ambient energy characteristic to fix the size of the capacitor and SRAM region size. If the energy characteristic of the ambient changes, size of the capacitor or SRAM region must be resized. Because in the lower ambient energy, the timekeeper must measure a longer time. For this measurement, a bigger size capacitor or SRAM region is necessary. Second, increasing timekeeper capacitor size to measure longer time causes high energy consumption. Another shortcoming is the need for startup time after each reboot. Because to make a new measurement, the capacitor must be discharged or the SRAM region must be refreshed. And using capacitor or capacitor series like CHRT and HALC increase the hardware size of the device. In this work, we propose a software solution, SUKI, which depends on the prediction of capacitor charging time rather than depends on capacitor discharge time. SUKI estimates power outages time for short-term stable ambient. SUKI consists of online and offline paths. SUKI requires experimental measurements to build the charging characteristic of the capacitor. For the offline part of SUKI, we measure the charging time considering the various power levels. Then we calculate the theoretical constant power according to the charging time. In the final step, we build a relationship between measured and theoretical power using a regression model. In the online part of the circuit, the ambient power is collected via ADC of the device. Then it is stored in a buffer. After taking the average of the power samples in this buffer, circuit estimates the charging time using the regression model. When evaluating circuit, we use an RF energy harvester as a power source, a 50 millifarad capacitor to supply microcontroller, and MSP430FR5994 as a microcontroller. For the offline part of the circuit, we used Arduino Uno to collect ambient power samples and measure the charging time of the capacitor. To ensure different power levels, we changed the distance between transmitter and receiver. We settled the receiver on 4 distinct points between 100 to 150 centimeters. To show the effect of buffer size that stores power samples, we change the buffer size from 1 to 100. When the buffer size is 1, Squid uses only current power for estimation. When it is 100, it takes the average of the current and 99 previous power samples. Then it estimates time using the average value of the power samples. Since the ambient energy is short-term stable, the accuracy is increased with the buffer size as shown in the figure. Squid can reach a 1 to 3% average estimation error. The prediction accuracy of Squid improves with power failure numbers. Squid takes samples after each power failure. After a few power failures, Squid estimation gets closer to the average charging time. Finally, we evaluate the energy consumption of Squid. Squid needs an ADC measurement for each power failure. Similar to the capacitor-based solution, we compare the energy consumption of Squid with the capacitors given in custard. Squid can decrease energy cost up to the 10 times. As future work, we are planning to implement different adaptation strategies like adapting the sampling frequency to respond to change in the energy harvesting environment. The supply capacitor size is one of the main factors affecting the charging time. We leave the evaluation of Squid with small supply capacitor as a future work. In addition, we plan to perform detailed measurements for CHRT and custard to present a solid compression. Furthermore, we are planning to test Squid using various harvesters such as solar and thermal. We will also incorporate better power prediction models to improve the estimation accuracy of Squid.
Great. Thank you. Go ahead. Go ahead.
Okay, thank you. I can take the question if you have.
I do have a few, but I want to let people in the room or elsewhere on Zoom chime in first. While people are thinking about it a little bit, one question that I did have was a little bit, if you could talk about the stability of the incoming energy harvesting rate that you expect. How important is it that it's a consistent amount of power coming into the system for this to work how you expect?
Okay, we are designed the circuit for short-term stable ambient. For example, RF transmitters, if the receiver and if the distance between the receiver and transmitter is constant, the transmitted power is also be not constant, but it is will be stable. And if we change the distance, the stable energy, the ambient energy will be changed. So we designed the circuit with for this stable energy scenarios, but it can be adaptation with the environmental energy level changing, because circuit takes power samples from ambient after each power fails, and it store in a buffer, the power samples buffer, and taking the average of the buffer, it estimate the time. When the power level in the ambient is dramatically changed, circuit take samples from new ambient and store it in a buffer, then estimate then take average of the buffer and estimate time. But the changing of the environmental energy level cause a estimation error of circuit. In a future work, we are planning a new adaptation strategies for this case. If the environmental energy level is extremely changed, circuit detect the extreme changing, then it decide it will clear the power samples buffer and take multiple power samples from new ambient, and it can estimate a reliable, it will give a reliable estimation for timekeeping.
Thanks. So I have a follow-up. It's not so much a question as a comment. It's cool work, interesting, very useful. And kind of on that note of less predictable power supplies, definitely very interested in seeing what happens, how well this approach would work with something like solar that's very different for the environment. And it would be super cool if you were able to get some results on that in time for the second iteration. I would be looking forward to seeing that. If you could, get that for ASPLOS, that would be really, really awesome.
Sorry, I have a question. You've been mentioning power measurements, but I don't think I heard how you do this. Is it just, you mentioned ADC somewhere in the slides, is just sampling the voltage of the solar cell, and from this you estimate the input power, or how do you do this?
Okay, for this first evaluation, we used PowerCast P2110B evaluation board. This board has a one auxiliary resistors to give power level of the ambient. So we use, for example, we send a signal to receiver, and receiver start to draw the incoming current from auxiliary resistor, and we use voltage of this resistor and to predict the environmental energy level.
Okay, so a shunt resistor to measure the current, and times the voltage, you have the input power.
Yes.
I see. All right, thank you.
I also have a short question. I was wondering about, do you base the charge estimation on the capacitor, the theoretical capacitor size, or is there some sort of calibration for the exact capacitance the capacitor has?
Okay, could you repeat the question? Sorry.
I guess your charge rate, that will vary depending on the size of your capacitor, right?
Yes, yes.
So is that your estimation, is that based on the theoretical size that, I mean, basically you get from the data sheet, or is that based on some sort of calibration process that you
yes, yes, I get it. Squid has occurred two paths, one of the offline path and one of the online path. When the offline path, we take the power samples from the ambient, and we measure the charging time of the capacitor. If the capacitor size is increased, or we use a huge capacitor, then the charging time of the capacitor will be increased. So we collect this power samples and charging time, then we calculate the theoretical power according to the measured charging time, and we build a relationship between measured power from the ADC of the microcontroller and a calculated theoretical power from the formula. Then we build a relationship between this these two power type. Then via a regression model. Then we use this regression model in an online path. We take a power samples from ambient and use we are using this regression model to calculate the theoretical power, and the formula that constant power charging time of the capacitor. We use this equation to calculate the charging time of the capacitor with the calculated theoretical power.
Great, I see. Have you looked at how do you think there would be an effect on based on the
sorry, I think so there is here is almost closing, so I think we can leave this question for remote. Do we have another presentation? Because I think we should close very soon.
Oh, yeah, we do have one more. I'm sorry, I thought you had until the 30-minute mark. But we do have one more. I remember we can continue the discussion online after the room closes, but I do want to then jump to our last presentation. It's actually a kind of an exciting capstone presentation in a way that it is a capstone piece of work. It starts to say that we are mature enough as an energy harvesting community that we can have more general purpose platforms. Nirani, I see that you're online. Would you like to give it live, or I'm happy to play the video that you sent in as well? If you'd like to play it live, holler. Otherwise,
yeah. You can just go ahead and play the recorded video. That'd be fine.
Okay, I will do that right now then. Thank you so much.
Hello everyone, I am Nurani, presenting our ideas on designing a general purpose development platform for energy harvesting applications. This work has been done in collaboration with my colleagues at the University of Virginia. Over the past few years, researchers have been working on developing platforms that support designing a variety of applications on top of them. Energy harvesting research is in dire need of more and more such platforms that enable independent, rapid, and modular design of applications. However, looking at today's battery-less systems, we see that most of the platforms are built for a specific application in mind. First, you choose an application, design the system to fulfill the goals, lay out the hardwares, and after that, test and debug to verify if it works or not. While this seems to be the straightforward way to go, this causes significant delay in the design and development phase. However, as the design is fine-tuned for a specific application, it performs pretty well for that. For example, let's consider the case of event-driven applications, where it is assumed that both the sensor and the availability of energy would be triggered by the same external event. If this relationship breaks, however, it becomes difficult to capture events reliably, which is what is captured in this diagram. If we translate a platform outside of its intended application, it loses its ability to perform better. That means choosing an optimal design point that could achieve reasonable performance across a different set of application requirements is a hard task to go. That different applications requirement could be the nature of sensing, for example, periodic or event-driven, or long-running, or other application requirements needing from the wireless connectivity or sensing granularity. Now, to work towards a general purpose platform, we ask what makes designing such a design platform difficult. One reason could be some applications are more suited for intermediate applications, whereas some might be able to handle the longer research times of the storage. Understanding the boundaries and leveraging where we could incorporate benefits from both of these techniques could enable a wide range of applications. At the same time, current platforms do not have a reusable hardware and software interface that can be leveraged by developers while designing such systems. On top of that, oftentimes when decisions are made at design time, it is not reevaluated properly at the runtime, leading to suboptimal performances. To work towards a general platform, we suggest architectures and designs that promote independent development of applications as well as the power management. This would require building platforms that are reusable and modular, that provides a distinct interface that can be leveraged by application developers, and also designing software tools that abstracts complexities and offers useful and general set of APIs that can be incorporated in the application code to enable faster development. Such kind of architecture would allow developers to build applications quickly without the need for building everything from scratch, the hardware and the software layers. As an attempt towards that, we are developing a platform that allows different applications to be integrated with the power supply module. The power supply itself incorporates a lower power processor that keeps track of the dynamic energy at runtime. The application processor could leverage this architecture and query the low power processor to ask for different energy related parameters such as capacitor voltage, the optimal sampling rate, etc. Now, as a discussion starter, we would like to think more about what are the other properties of a general purpose application development platform that designers could think of. With that, I'm thanking the audience, and I would look forward to discussing more. Thanks. Thanks.
Let me try to strategically leave your discussion prompts here up on the screen for everyone, and I'm happy to invite questions or comments from anyone in the audience. So I can kind of kick things off a little bit. Your middle bullet point there talks about the isolated general hardware-software interface between the two sides of the piece here. And I'd like to hear a little bit of what you think higher level software needs to understand about the underlying hardware. Like if you want to adapt your application, or what kind of, it wants to be isolated, but they need to have some sense of what's happening above and below. So how do you imagine the interaction between these things across this barrier?
Yeah, thank you so much, Pat. That is actually a very interesting, like a very, very important question. When we started building the platform, we also asked the same question. Like, do you need to know, like, as an application developer, that what kind of harvesting sources you have? Like, do you need to know that, okay, I'm harvesting from solar or TEG or kinetic or anything like that? The answer might be that you could worry about that, but we are kind of like pushing for designs where you can isolate knowing about that to a different module where when you're writing the application code, we wouldn't necessarily need to know the low level details, but at the same time, we would at least like to know the high level parameters like, okay, what is the stored energy at this moment? Or if I have this much energy, how could I schedule my tasks? If knowing that is what would enable faster development, I am hoping that would be a more way going forward, because the more you like hide like complexities of designing like different kind of hardwares, the more better it works for application developers. But at the same time, there are scenarios where knowing that would be helpful. So yeah, so this is that's my comment for now.
It's still a hard question, understood. It looks like there's someone standing at the mic in the room.
Yes, I have a question, and I'm not sure if you saw maybe the keynote from Luca Motola yesterday. At some point, he proposed to try to do things in a more standard, or to try to do testing and the design of energy harvesting-based systems in a more standardized way. And he mentioned examples from the wireless domain where you have test beds and you can do easy, let's say, tests that allow you to compare between different protocols in a more standardized way. I wanted to get your thoughts maybe on this, since you're trying to have a generic platform to design these types of systems. I'm hoping this would be coupled with some way for generic testing of these systems. So how do you think we can maybe test with different energy sources, as you're trying to do it with isolation and minimize the dependencies between one system and the other? And how can we do this in a reproducible way and in an accurate way, this testing?
Thank you so much for the question. I didn't attend the talk, but I could understand like the idea of the question is like, how would you make sure that when you're testing these designs, you ensure that your other environmental parameters are same? Is that like the gist of the question? Or
Yes, it's part of it. So I'm not asking about, let's say, emulating environments accurately, right? That's a separate question. But how can you, let's say, test modularly this type of generic design in a way in which you can compare different, let's say, configurations and try to find which configuration is optimal for different parameters? You showed a graph with 2 axes and one being optimal where that was better on both, right? It could be that there's another metric later on for another subsystem, and you would want to test for this, right? So how do you handle a generic platform, and how can you test it in a reproducible and accurate way?
Yeah, thank you. I understand the question. That is kind of like one tricky thing. Like even if you want to make the platform general enough, but you would also want it to be customized. So for example, like your applications would be different from each other, like the periodic or event driven, their metrics of like performing good would be different from each other. But if there is a way to quantize that and say that if you like cross a minimum threshold, you have higher utility. Like if you could like bound these like requirements under same umbrella, maybe that would be something something that we could look forward to. But at the same time, that would be a kind of tricky, because when I was like drawing and thinking about the graph, I was also only thinking about the event-driven applications, but that is not the only applications that exist in an IoT domain. But thinking about like, if we could come up with a global metric that would capture this variability of applications, that would be something that I can definitely think a little bit more about going forward.
All right, thank you. It's an open question. There's no right or wrong answer. So thank you.
Okay, thank you.
So I think Colleen is double booked now, but she had a couple interesting comments in the chat saying that, it feels like good defaults with an ability to do advanced configuration is the dream, where you could be source agnostic by default, but power users could optimize. And so sort of following that thread a little bit, do you have an instinct for what a good default might even look like? Like what, like that's actually, it's the dream, but like what might a good default be?
True. True. That is why we started like thinking about like indoor harvesting from indoor sources, which doesn't have like very high variability, but still some amount of variability. But maybe a platform that would allow you to at least test across different modalities would be something to at least shoot for generality. But yeah, yeah. Let's see. We are actually going to work on that. So that's something I'm looking forward to.
Yeah. I guess well, following on the thread though, is like, is it a survey of applications? Is it a survey of users that are on top of these things? Is it a survey of people in this community? How do you even begin to scope that out? Might be something that we could push through more here. I guess is 5 minutes until they get kicked out of the room there in Portugal. So we probably need to come towards some wrapping up and some conclusions here.
That's something that I was also thinking, like, I find it hard to actually like compare these against like existing platforms when you do not have like a quantifiable metric of like showing that this works generally across different applications. So yeah, if we could discuss more about that, that would be really helpful.
Well, we all look forward to the extended submission to NSYS at ASPLOS with more answers to some of these questions. And so with that, I do want to, because I know there's some pressure on the Portugal side to get things wrapped up, move towards closing NSYS at SenSys. Thank you to everyone for accommodating our crazy hybrid situation. I think it worked out hopefully somewhat mostly okay. And that's about the best we can ask for right now, I think. We will be sending out a couple of surveys immediately after in the next day or two here. One for people to vote on best demo, where there are indeed cash prizes. So do vote and vote for the best demo, not just your friends. And we'll also be following up a little bit with plans for NSYS at ASPLOS. We really hope that we can bring some of the folks that have been excited in this community for a while to bring some of the excitement about energy neutral energy sensing systems to a larger and different community. I think this can be really, really valuable and powerful for folks. Finally, I'll open the floor really quick if there's anything that people would like to talk about right now in a 4-minute long NSYS business meeting about what we could do to make NSYS Erasmus successful, or NSYS itself as we run forward in the future, more successful things we'd like to see happen with NSYS, etc. It's an open floor until the floor is not ours anymore.
Okay, so thank you very much, Pat, in general, all of the organizer and all the people that stay here until longer, also the technical support we stay a bit longer, but it's fine. Yeah, I think we can close it. I don't know if there is any further comment, or otherwise we can close here. Okay, thank you very much. See you around. Bye.
See you in Switzerland, everybody.
Thank you. See you in Switzerland.